Part 1. Space. Chapter 1. An explosion in silence. Imagine yourself on a distant volcanic island. Warm, cloudless nights. The surrounding ocean resembles a calm lake, with only gentle waves lapping at the white sandy shore. Silence. You lie on the beach, your eyes closed. A rich, sweet, exotic scent emanates from the warm, sun-heated earth. Peace reigns all around. Suddenly, a wild cry in the distance makes you jump, staring into the darkness, and then silence again. The creature that cried out has quieted. Perhaps there is nothing to fear. The island may be dangerous for someone, but not for you. You are a human, the most powerful among predatory animals. Soon, your friends will arrive to share a drink with you. Besides, you are on vacation, so you sink back into the sand and focus on thoughts worthy of the status of Homo sapiens. Myriads of tiny lights twinkle in the endless night sky. Stars, visible everywhere even to the naked eye, remind you of the questions you asked as a child. What are stars? Why do they twinkle? How far away are they? And now you ask yourself, will we ever know the true answers? Sighing, you stretch out again on the warm sand and push the silly thoughts away, thinking, does it really matter? A tiny falling star silently streaks across the night sky, and just as you are about to make a wish, the most unusual thing in the world happens. As if in response to your last question, 5 billion years flash before you in an instant, and you suddenly realize that you are not on the beach, but floating in space. You can see, hear, and feel, but your body has vanished. You are incorporeal. You are pure. And there is not even time to wonder what has happened. To scream or call for help? The most peculiar of all possible situations. Before you, at a distance of hundreds of thousands of miles, against the backdrop of tiny distant stars, a fiery mass burns a deep orange color. It spins and moves toward you. It won't take long to understand that its surface is a molten mass, and what you are seeing is a planet, a molten planet. You are struck by this thought, and a question arises. What monstrous source of energy could incinerate an entire world like this? But then a massive star appears on your right, and its size, colossal compared to the planet, is simply astounding. It too spins. It too moves through space, or it seems to grow. The planet, now much closer, looks like a tiny orange ball next to a giant sphere that continues to grow at an incredible rate. It is already twice as large as it was a minute ago. The sphere shimmers with red fire and violently ejects streams of plasma heated to 1,000,000 degrees, dispersing through space at speeds that would make even the gods envious. All you can see is its monstrous beauty, and indeed, you are witnessing one of the most astonishing events produced by the universe. And still, there is no sound. Complete silence surrounds you. Its sound does not travel in the vacuum of space. Of course, a star cannot grow indefinitely, yet it is growing. It has already exceeded all imaginable sizes. The molten planet cannot resist the forces that are destroying it, scattering into dust. The star, unaware of this, continues to grow, increasing from its original size 100-fold, and then, quite unexpectedly, it explodes, scattering its insides across space. A shock wave rolls through your ephemeral essence, and then only dust remains, dispersing in all directions. The star is gone. It is transformed into a remarkably colorful cloud, now spreading through interstellar space at a speed that even the gods would envy. Slowly, very slowly, you come to your senses, and after realizing what has just happened, your mind strangely clears. The horrifying truth: the dead star was not random. It is the sun, our sun, And the molten planet that vanished in its rays is Earth, our planet, your home, the vanished home. What you witnessed was the end of our world, not a fictional prophecy from some dubious source that has survived to this day, like those of the Mayan Indians. A real, tangible end, the very one humanity has known since it came into being, 5 billion years before what you have just witnessed. Just as you intend to gather these thoughts together, your mind immediately returns to the present, back into your body, on the beach. Your heart races wildly, and you sit up, looking around as if waking from a strange dream. Trees, sand, sea, and wind, all are in place. Your friends are approaching. You can already see them. What happened? Did you doze off? Perhaps what you saw was a dream. A chilling wave of emerging questions begins to spread throughout your body. Could a dream be reality? Will the sun really explode one day? And if so, what will happen to humanity? Can anyone survive such an apocalypse? Will even the memory of our existence vanish into cosmic nothingness? And once again, raising your eyes to the starry sky, you desperately try to understand what has happened. Deep down, you know it was not an illusion, even though your mind has returned to the beach, to your body. You realize that you truly traveled beyond your time, into a distant future, witnessing what no one will ever be destined to see. Slowly inhaling and exhaling to calm yourself, you suddenly discern strange sounds, as if the wind, waves, birds, and stars are whispering songs audible only to you. And unexpectedly, you understand what they are singing about. It is both a warning and an invitation. If they whisper of the possible futures, then only one path will allow humanity to survive the inevitable demise of the sun and most other catastrophes. The path of knowledge, the path of science, a journey accessible only to humans, a journey you are about to undertake. Another cry pierces the night, but this time you are unlikely to hear it. Like a seed already beginning to sprout in your mind, you feel a passionate desire to discover what is known about the universe. Once again, humbly raising your gaze to the sky, you now look at the stars with the eyes of a child. What is the universe made of? What is nearby Earth? And what lies beyond it? How far can we look into space? What is known about the history of the universe? And has it existed while the waves gently lap at the shore? And you wonder if anyone will ever explore these cosmic mysteries. The twinkling of the stars seems to draw your body into an unconscious state. You hear the conversation of your approaching friends, but strangely, you feel the world around you differently than just a few minutes ago. Everything seems richer, deeper, as if your mind and body are part of something much larger, far greater than anything you have ever thought before. Your hands, legs, skin, matter, time, space, a web of force fields surrounds you. The veil of existence you are not even aware of has lifted from the world, revealing a mysterious and unexpected reality. Your mind longs to return to the stars, and you have a sense that an extraordinary journey awaits you ahead, one that will take you far from the familiar world. Chapter 2. The Moon. If you are listening and building, then you have already made a journey 5 billion years into the future. By any measure, a good start. So, you should be sure that your imagination is working well, even perfectly, because imagination is all you need for traveling through space and time, matter and energy, to discover what is known about our reality from the perspective of the early 21st century. You did not ask for this, but you are fortunate to see what fate awaits humanity and all life on Earth if nothing is done to understand how nature works in order to survive in the long term, to avoid being swallowed by a raging dying sun. Our only chance is to learn how to take our future into our own hands, and for that to happen, we must decipher the laws of nature itself and learn how to apply them wisely. To be fair, there is a lot of work ahead of us. However, in the following pages, you will find perhaps everything that science knows so far. A journey through the universe. You will discover what gravity is, how many atoms and particles interact without touching each other. You will find that the universe is mostly made up of mysteries, and that these mysteries have led to the emergence of new forms of matter and energy. And then, when you familiarize yourself with what is already known, you will leap into the unknown and see that some of the most prominent theoretical physicists today are working on explaining some very strange realities of which we are a part. The picture will be completed by parallel universes, multiverses, and additional spatial dimensions. After this, your eyes will likely light up with the knowledge and wisdom accumulated and utilized by humanity over millennia. But you should prepare yourself. The discoveries of recent decades have changed everything that was previously considered true. The universe is not only immeasurably larger than expected, it is also infinitely more beautiful than any of our ancestors could have imagined. And since we are on this topic, here's another piece of good news. You will find out just how much we humans have made ourselves different from all other forms of life that have ever existed on Earth. And this is great, considering that most of them are already extinct. Dinosaurs ruled our planet for about 200 million years, while we have been doing the same for no more than several 100,000 years. They had enough time to begin exploring their environment and clarifying some things for themselves. They did not do this and went extinct. Today, we humans can at least hope to detect a threatening asteroid in advance to try to change its trajectory. Thus, we already have some potential that the dinosaurs did not possess. It may be unfair to assert this, but looking back, we could link the extinction of the dinosaurs to their lack of awareness of theoretical physics. At this moment, you are still on the beach, but the memories of the dying sun are still fresh in your mind. You do not yet have much specialized knowledge, and, to be honest, the twinkling dots in the sky seem to completely disregard your existence. The life and death of earthly beings mean nothing to them. It seems that time and space operates on scales that your body cannot grasp. All the time life has existed here on Earth likely lasts no more than a blink of an eye for the distant shining gods. 300 years ago, one of the most famous and brilliant scientists of all time, British physicist and mathematician Isaac Newton from Cambridge University, who gifted us with the law of universal gravitation, was searching for a definition of time. For him, there was ordinary time, felt by all of us and measured by clocks, and absolute time, a property of God, unchanging and eternal. From Newton's perspective, the infinite line of human time, stretching backward and forward into infinity, is but a moment. He saw it immediately. Although you are not a god, when you look at the stars while a friend silently pours you a drink, the grandeur of the task ahead begins to weigh heavily on you. Everything seems too vast, too distant, too strange. Where to begin? You are not a theoretical physicist, but on the other hand, you are not one to give up. You have eyes and a curious mind. As you lie on the sand, you focus on what you see. The sky, mostly dark, with stars scattered across it. And between the stars, the naked eye can discern a dimly glowing band. Whatever the origin of this color, you know that the band is called the Milky Way. Its width is about 10 times that of the full moon. In your youth, you looked at it many times, although not so often lately. Gazing at it now, you realize that it is noticeable enough that it must have been known to your ancestors since time immemorial. And you are right. The irony is that people have discussed its nature for centuries, but only now do we know what it truly is. Although the light pollution from artificial sources makes the Milky Way invisible in most populated areas, its presence on your tropical island is overwhelming. Just as the Earth rotates, as night falls, the Milky Way moves across the sky from east to west, much like the sun's path during the day. The possibility that humanity's future lies somewhere out there, beyond the edges of the earthly sky, begins to feel real in your mind. Mesmerized, you ask yourself if it is possible to see everything that exists in the universe with the naked eye. And you shake your head. You know that the sun, the moon, some planets like Venus, Mars, and Jupiter, a few hundred stars, and the hazy strip of whitish dust known as the Milky Way do not fit into the concept of everything. There are mysteries hidden beyond the visible field among the stars, just waiting to be unraveled. And if you were given such an opportunity, what would you do? Of course, you would start by exploring the night sky from Earth, and then get carried away, venturing as far as possible. And then, as strange as it may sound, your mind truly begins to detach from your body, soaring upward toward the stars. A feeling of spinning, like dizziness, overwhelms you, and your body and the island remain below, rapidly shrinking in size. Your mind, in the form of an ethereal essence, rises and flies eastward. You have no idea how this has happened, but you find yourself much higher than the tallest mountain. A richly red moon hangs suspended on the distant horizon, and in far less time than it takes to say this phrase, you leave the Earth's atmosphere, traversing 380,000 kilometers of space that separates our planet from its only natural satellite. From space, the moon appears as white as the sun. Your journey of discovery has begun, just like that of dozens of people before you. You reach the moon. Your ghostly form walks across its surface. The Earth has vanished behind the lunar horizon. You are on what is called the dark side, which never sees our planet. There is neither blue sky nor wind, and not only do you see far more stars overhead than from anywhere on Earth, but they do not twinkle either. This is because the moon lacks an atmosphere. Space begins just a millimeter above the surface of the lunar soil. Not a single rain or storm has washed away the scars of craters that enhance the surface. Everywhere, like frozen memories of past impacts and meteors. And the barren soil, as you approach the side of the moon facing Earth, magically fills your eager mind with stories of history and birth. Your gaze falls upon the Earth beneath your feet. What cruelty! About 4 billion years ago, our young planet collided with another, the size of Mars, resulting in a massive chunk being torn away and sent flying into space. Over the following millennia, the debris from this catastrophe gradually formed into a single sphere, orbiting around our world. Thus, the moon was born, the very one on which you now stand. If this were to happen now, such a collision would be more than enough to wipe out all forms of life on Earth. But back then, our world was dead. Even if we were to think of something catastrophic, without that impact, we would have neither a moon to light our nights, nor the constant tides. And life as we know it probably would not exist on our planet. So, as the blue Earth rises above the lunar horizon ahead of you, you understand that cosmic-scale catastrophes can be both for better and for worse. Your home planet, as seen from here, is the size of 4 full moons combined, and the blue pearl floats against the backdrop of the black, star-studded sky. The true scale of our world in the cosmos has always been and will continue to be a shocking spectacle. You continue your journey, watching as the Earth grows in the lunar sky. And although everything seems so safely swampy, you know better than to trust the apparent calm. Time has a different meaning here, and considering the ongoing changes in the terrain, cruelty seems inevitable. The craters, like scars covering the surface of the moon, are nothing but reminders of that cruelty. Hundreds of thousands of mountain-sized chunks drifting in space have likely bombarded the moon for centuries. They must have struck the Earth, but our planet's wounds have healed, for it is alive and hides its past deep beneath the ever-changing soil. Nevertheless, in space, you suddenly feel that despite its capacity for healing, it is fragile, almost defenseless. Your home world is nearly defenseless. Not entirely. Now it has us. It has you. Collisions like those that led to the birth of the moon are mostly matters of the past. Today, there are no wandering planets threatening our world. Only asteroids and comets remain, and the moon partially protects and shields us like a shield from such calamities. However, danger lurks in the star. As you gaze at the blue images of Earth in the dark sky, a strangely bright glowing sphere suddenly rises behind you. Turning around, you find yourself face to face with the star, the brightest and most violent object near our home planet. We call it the Sun. It is located 150 million kilometers from our world. It is the source of all our energy. As your mind fills with the immense light emanating from this extraordinary cosmic lamp, you leave the moon behind and fly toward our home star, the Sun, to discover why it shines. Chapter 3. The Sun. If humanity could somehow gather all the energy emitted by the Sun in just 1 second, it would be enough to meet the energy needs of the entire world for about 500 million years. As you approach closer and closer to the star, you realize that the Sun is far from being as large as you saw it 5 million years later on the eve of its demise. However, it is enormous. For comparison, if the Sun were likened to a large watermelon, the tiny Earth would lie 43 meters away from it, and you would need a magnifying glass to see it. You are now just a few thousand miles from the surface of the Sun. Behind you, Earth is now just a bright dot. The Sun ahead fills half the sky. Bubbles of plasma burst forth everywhere. Billions of tons of hot matter are ejected right before your eyes, passing through your ethereal body, and in the Sun's magnetic field, enormous loops appear, seemingly arising by chance. The scene is, to put it mildly, unusual, and you, animated and fascinated, become curious. What is it that Earth lacks that makes the Sun so special? What makes a star a star? Where does its energy come from? And why on earth must the Sun one day perish? To find answers to these questions, you dive into the most unpleasant place you can imagine, the very heart of the Sun, hidden more than 500,000 kilometers beneath its surface. For comparison, the distance from the surface to the core of the Earth is about 6,500 kilometers. As you dive headfirst into the burning furnace, you remember that everything we breathe, see, touch, feel, or explore. And even your own body is made of atoms, the building blocks of everything in existence. They are the bricks and Lego pieces of your habitat, if you will. But unlike them, atoms do not have rectangular shapes. For the most part, they are round and consist of a dense spherical nucleus surrounded by tiny electrons that rotate around it. However, atoms can be classified by size. The smallest atoms are hydrogen, and the second largest are helium. Combining these two elements gives you about 98% of all known matter in the universe. This is certainly a lot, but still less than in the past. 13.5 billion years ago, it is believed that these two elements accounted for nearly 100% of all known matter. Nitrogen, carbon, oxygen, and silver are examples of modern elements that are not hydrogen. They must have emerged later. How they did so, you will now learn. You dive deeper and deeper into the sun. The temperature steadily rises, becoming mind-bogglingly high. At the end of the journey, it reaches 16 million degrees Celsius, perhaps even more. All around you are numerous hydrogen atoms, although they are stripped bare, surrounded by energy. Their electrons have separated, melted away, leaving only exposed nuclei. They are packed so tightly against each other due to the pressure exerted by the star on its own heart that they cannot even move. Instead, they are forced to fuse together, forming larger nuclei. You witness nuclear fusion occurring right before your eyes, the creation of large atomic nuclei from smaller ones. Once formed, the heavy nuclei that leave the food that birthed them combine with lonely, detached hydrogen electrons, becoming new, heavier elements: nitrogen, carbon, oxygen, silver. To initiate nuclear fusion, the creation of heavy nuclei from light ones, an immense amount of energy is required, and it is provided by the crushing force of the sun's gravity, which effectively pulls everything around it inward. Such a reaction cannot occur naturally on the surface or inside the Earth. Our planet is too small and lacks sufficient density, so its own gravity cannot cause the Earth's core to reach the temperature and pressure needed to trigger nuclear fusion. By definition, this is the main difference between a planet and a star. Both are cosmic objects of rounded shape, but planets typically have small rocky cores, sometimes surrounded by gas. Stars, on the other hand, can be viewed as enormous nuclear fusion facilities, and their gravitational energy is so great that they are compelled by their nature to form matter in their centers. All the heavy atoms on Earth, all the atoms of the chemical elements necessary for life, as well as the atoms of your body, were once created in the hearts of stars. As you fill your lungs with air, you inhale them, touching your own skin or someone else's. You are touching stardust. You once wondered why stars like the sun must die and explode at the end of their lives. And here is our answer. Without such an end, there would only be hydrogen and helium around. The matter that makes us would not always seem to be locked inside immortal stars. Earthlings would be born, and life as we know it would simply not exist on our planet. Looking at it this way, and realizing that we are not made up solely of hydrogen and helium, that our bodies, the Earth, and everything around us also contain carbon, oxygen, and other elements, we conclude that our sun is a second or perhaps even a third generation star. 1 or 2 generations of stars must have exploded before their dust became the sun, the Earth, and us. So what caused the demise? Why are stars doomed to end their luminous lives in a spectacular explosion. One of the remarkable properties of nuclear fusion is the enormous amount of energy required to initiate it, the weight of an entire star, and then it releases even more energy. The reason may seem surprising, but when you observe what is happening right before your eyes, there is no choice but to accept it. When two atomic nuclei fuse into one, a large part of their mass disappears. The resulting nucleus has less mass than the two nuclei that created it. It is as if mixing 1 kilogram of vanilla ice cream with another kilogram of the same ice cream yields not 2 kilograms of ice cream, but less. This does not happen in everyday life, but in the nuclear world, it occurs all the time. And, perhaps fortunately for us, the mass is not lost. It is converted into energy as a result of the exchange described by Einstein's famous equation, E or mc2. You may be familiar with it, but allow me to clarify for accuracy that the equation E or mc2 represents energy, E, and mass, m, while c is the speed of light. Thus, the only equation in the book literally means that mass can be converted into energy, and energy into mass. In everyday life, we are more accustomed to exchange rates for converting one currency into another than for converting mass into energy. Therefore, to understand that E-REMC2 is a favorable deal for nature, imagine the same exchange rate at John F. Kennedy Airport for converting 1 pound of initial mass into US dollars received for it. The energy exchange rate here is C2, where c is the speed of light. Thus, for 1 pound, you would receive $90 million billion. Allow yourself to notice. What a wonderful deal. Essentially, this is the best exchange rate in nature. It is evident that the missing mass in each individual nuclear reaction is quite small. But every second, the heart of the sun fuses so many atoms that the amount of energy released is enormous, and it has to go somewhere. So it is pushed out into space, away from the core of the star, in every possible way. Eventually, the energy of nuclear fusion is balanced by gravity, which pulls everything ejected back into the core. If gravity were the only participant in the reaction, the sun would begin to collapse. Nuclear fusion is accompanied by the release of vast amounts of light and particles in a swirling, glowing soup of nuclei and electrons known as plasma. This emission of light, heat, and energy causes stars to shine. The sun, being a star, is not a large fireball. To keep a fire burning, oxygen is required, and although the sun does not produce it along with other heavy elements, there is not enough free oxygen in the airless void of space to create any kind of fire. Striking a match there would never ignite anything. And the sun, like all the stars in the sky, is simply a bright sphere shining with plasma, a hot mixture of electrons, atoms stripped of some of their electrons, so-called ions, and atoms without electrons, bare atomic nuclei. As long as there are enough small nuclei to compress the heart of the sun, its gravity and nuclear energy will remain in equilibrium. And we are incredibly fortunate to live next to a star in such a state. In fact, this has nothing to do with luck. If our sun were not in such a state, we would not be here. And as you now know, the sun will not remain in equilibrium forever. One day, the supply of atomic fuel in the core of our star will run out. On that day, the emissions of energy from the core of the sun outward to balance gravity will cease. Gravity will initiate the final stage of the star's life. The sun will begin to collapse and become denser until nuclear fusion reactions restart, but this time in the core, closer to the surface. The synthesis will not balance gravity, it will overpower it, and the surface of the sun will be pushed outward, causing the star to dim. You observe this process during your travels into the future. The final energy release will herald your demise. Russia in space represents everything created by the sun throughout its life, and simultaneously, other, heavier elements, such as gold, are formed there. Eventually, these atoms will mix with the remnants of other dying stars nearby, forming enormous clouds of cosmic dust that may, in the distant future, become the foundation for the growth of other worlds. By estimating the amount of hydrogen remaining in the core of our star, scientists have been able to determine when this catastrophe will occur, and the results indicate that the sun will explode in approximately 5 billion years from now, plus or minus 3 days. Chapter 4. Our Cosmic Family. Now your knowledge of the sun makes you more informed than anyone who lived before the mid-20th century. All the light reaching you daily comes from atoms produced in the very heart of our star, part of their mass transformed into energy. However, Earth is not the only celestial object benefiting from solar energy. In the blink of an eye, your mind leaves the bubbling, molten surface of the sun and, like a hawk, surveys the surroundings. 8 bright points move against the backdrop of seemingly motionless distant stars. These points are planets, and in this matter-filled sphere, they are too small to dream of one day becoming stars. 4 of them are the closest to the sun, resembling tiny rocky worlds. The 4 farther ones are primarily composed of gas. They are tiny compared to the sun, but giants next to Earth. The largest of the 4 small rocky planets, although all were born from the same cloud of dust from long-dead stars. But apart from Earth, none of these worlds and none of their hundreds of moons are potential refuges for future humanity. They are all bound by the gravitational forces of the sun and will all vanish with the final explosion of our star. Salvation, if it exists, must lie much farther away. Realizing the urgency of the search, your mind races into the infinite distance to look at what lies beyond the sun's influence. Along the way, you will visit the distant relatives of your planet, the giants of our cosmic family. You are now 3 times farther from the sun than Earth. Mercury, Venus, Earth, and Mars, the 4 small rocky planets near the sun, are left behind. From here, our star appears as a shining object, the size of a halfpenny, lying at arm's length. If Earth were located here, an atypical July afternoon in the United Kingdom, for instance, the hottest day of the year would feel colder than the coldest winter in Antarctica. Sunlight dims more and more as you move away from our star. You pass by chunks of rock that have remained since the earliest days of our planet's formation. These mostly potato-like asteroids together form what astronomers commonly refer to as the asteroid belt, an enormous ring encircling the sun, separating the 4 small terrestrial planets from the world of giants. The asteroids are quite scattered, and as you fly through the belt, you realize that the chances of colliding with one of them are slim. Many human-made satellites have crossed it without incident, leaving the asteroid belt behind. You fly past Jupiter, Saturn, Uranus, and Neptune, gas giants, enormous planets with relatively small rocky cores hidden deep beneath their turbulent atmospheres. All these planets appear magnificent due to their rings, although Saturn's rings are significantly larger and more beautiful than the others. You regard them with the respect that these giant worlds deserve. And even if they are not suitable for life, beyond Neptune, the farthest planet orbiting the Sun, you do not expect to encounter anything more, but instead discover another belt made up of clumps of dirty ice of all kinds and sizes, which are likely again byproducts of the birth of our solar system, when its current members formed from the residual dust of long exploded stars. This belt is called the Kuiper Belt. From here, the Sun looks like the size of a pinhead, just one of the stars in these distant regions. Hardly any warmth reaches you, but there is some movement here. Periodically, due to collisions or other perturbations, one or several of these dirty snowballs are ejected from their quiet, distant orbits around the Sun, being drawn towards our star. They slowly reach warmer areas, beginning to evaporate as they move toward the Sun's radiation, leaving behind long tails of tiny icy rocks sparkling in the darkness. Such an asteroid becomes one of the celestial wonders known as comets. In November 2014, the European Space Agency's Philae lander touched down on one of the comets to study its surface, delivering a spacecraft there. A probe currently sent after it is observing the transformation of the comet's outer layers into gas as it approaches. Like poor Pluto, which recently had its planetary status revoked, sending it into the category of dwarf planets, it has now also become part of the icy belt, along with at least two other dwarfs named Haumea and Makemake. It is amusing to think that Pluto, along with its moon Charon, is so far away, and that it takes such a distance in space to complete one orbit around the Sun that less than one of its own years passed from the moment Pluto was discovered as a planet to the moment it lost that title 76 Earth years later. It really took astronomers several decades to see that its size is only a quarter that of the Moon. Poor, dirty brown Pluto, which you are now flying past, is certainly not affected by its new classification, and soon you leave it behind, heading further away from the reliable protection of our shining star. Along the way, you encounter more dwarfs and comets, and even yet undiscovered and frozen worlds. But your attention quickly shifts entirely to the giant sphere that encompasses everything you have seen so far. All the planets, dwarf planets, asteroids, and comets you have considered are located within a more or less flat disk, at the center of which shines the Sun. But what you are observing now is of an entirely different nature. An extensive region of billions upon billions of potential comets forms a vast spherical cloud that truly seems to occupy the existing space between the Sun and the realm of other stars. This area is called the Oort cloud. Its size is astonishing. It defines the boundary of our star's dominion, encompassing all members of the cosmic family known as the solar system. Leaving it, you fly into uncharted territories, aiming for what you believe to be the closest star to us. It was discovered in 1915, 100 years ago, just as scientists began to understand our universe. Its name is Proxima Centauri. Chapter 5. Beyond the solar system. Your body is still resting on a beach somewhere on our planet, but your mind is now at a distance from Earth that no human-made object has ever reached. As soon as you cross the edge of the Oort cloud, you leave the solar system, entering the realm of another star. Crossing this blurry line, perceived by you as a boundary, you see how some comets distant from the solar system change their orbits, transitioning from a curve around the Sun to a curve around another star. The star we are now approaching, Proxima Centauri. Proxima Centauri belongs to a family of stars known as red dwarfs. It is much smaller than the Sun, about 1/7 its size and mass, and has a rich red hue, hence the name. Red dwarfs are quite common. Scientists even believe they make up the majority of stars in the sky, even if we cannot see them. As you approach it, you continuously observe the star undergoing dramatic changes in brightness and ejecting vast amounts of hot matter in a rather chaotic manner. Let's see if there are any planets around this main red dwarf. You do not notice any. What a pity, partly because it would not just be comfortable to live on a planet orbiting Proxima, but civilizations that develop there would have the opportunity to plan a very long-term future. When our star, the Sun, explodes, Proxima will not change one bit, as far as we know. It will continue to shine, as it does now, for about 300 times longer than the current age of the universe, a long time by any measure. In Proxima, whose size is much smaller than the Sun, the tiny atomic nuclei merge into larger ones many times more slowly. Size matters in stellar terms. The larger the star, the shorter its life. And for the planets orbiting them, distance is crucial for having liquid water on their surfaces and being able to support life. In our understanding, a planet should not be too cold or too hot. For this, it must be located neither too close nor too far from the star it orbits. The habitable zone around a star, allowing liquid water to remain on the planet's surface, is called the Goldilocks zone. What if you were to discover another red dwarf with an Earth-like planet orbiting at just the right distance? Then it could resemble our beloved world. Existing while always feeling a bit guilty for entertaining such a thought, you turn to look at your home solar system, your world, expecting the sun to outshine all other bright points in the sky. But this is far from the truth, and the colossal cosmic distances suddenly strike you to the core. If you were not a pure mind and a true cosmic traveler, how long would it take to send a message home from here? If you had brought an interstellar mobile phone with you, you could try calling friends from each stop to share your discoveries with them. Mobile phones convert voice into signals transmitted at the speed of light, making Earth communication feel instantaneous. However, in space, distances are usually too vast, and nothing seems more instantaneous. Light takes about 1 second to travel from the Moon to Earth, and the same amount of time in the opposite direction. So, if you were there and asked a friend on Earth if he could see you through binoculars, his answer would return to you in 2 seconds. Things are worse with the Sun. Light covers the distance between Earth and the Sun in 8 minutes and 20 seconds. Communication becomes more challenging, as the response to a question will take over 16 minutes. But the Sun is relatively close in cosmic terms. A call from where you are, near Proxima Centauri, will reach a phone on Earth in approximately 4 years and 2 months. So any answer to your question will not reach you for at least 8 years and 4 months. You have only reached the 2 closest stars to Earth after the Sun, but you feel so far from home that you begin to search for some landmark to avoid getting lost. Remembering the beautiful Milky Way, seen from the beach of a tropical island, you look around for the cloudy white band of light. To your surprise, you also find that it now resembles not a narrow straight strip, but an inclined ring, with some parts brighter than others. And you are somewhere inside it, realizing that if the Milky Way appeared as a band from Earth, it was because most of it was hidden by the Earth beneath your feet. Without much thought, having found no planets, you set your course straight for the brightest part of the Milky Way, unknowingly. You are currently moving toward the center of a cluster of about 300 billion stars, a cluster known as a galaxy. Chapter 6: Cosmic Monsters. If you think about it, there must be something unusual at the center of a cluster of 300 billion stars. Take Earth. At the center is the densest, hottest, most aggressive place within the earthly realms. Take the solar system. At the center is the Sun, the densest, hottest, most aggressive place within the solar system. This may not prove anything, but it certainly suggests that there is something equally large at the center of the galaxy, something truly very large. The rapid movement of thought leads you to fly past several tens of millions of stars, some much larger than the Sun, doomed to live significantly shorter lives, while others are tiny, ready to emit light for unimaginably long times. You fly through star formation regions, clouds of dust littered with hundreds of exploded stars, and stellar graveyards waiting for the moment of merging to become regions of star formation. And now you are near the center of the galaxy, whatever it may be, and suddenly you stop. Right in front of you is another ring, a rotating, colorful ring of dispersed matter. Looking closer, you notice that it is made up of gases, billions of asteroids and comets moving around a source of bright, powerful light resembling a fluffy donut. What is happening here? What are these orbiting asteroids, ice chunks? Looking around a bit more closely, you see what seems impossible. In the orbit of the ring, not only debris is moving, but also stars. Entire stars, not planets, but stars themselves, moving rapidly. As of 2015, one of them is actually the fastest known object in the universe. It is called S2, or Source 2. Scientists have observed that it completes a full orbit around the donut in 15.5 years. Considering the distance, this means the star is flying at an astonishing speed of 17,700,000 kilometers per hour. But how can this be? What kind of monster possesses enough gravitational force to hold such a lightning-fast object? And is it possible to create such a force? Imagine a marble and a bowl. If you spin the marble in the bowl too slowly, it will immediately fall to the bottom. If you spin it too quickly, it will fly upward in a spiral, breaking something in the kitchen. But if you spin it just right, it will circle for a while at some distance between the bottom and top of the bowl, neither flying out nor falling to the bottom, until friction turns its speed into heat and slows it down. Now imagine that the marble is the super-fast star S2, and that there is an invisible bowl holding it in orbit around what lies in the glowing donut. In space, there is no friction, so the star has no reason to lose energy. Thus, based on S2's speed, we can imagine the shape of the bowl, and therefore the mass lying at its bottom. This rather simple calculation has been performed by scientists many times and always yields an incredible result. To create the gravitational field necessary for S2, the power needed to prevent it from being ejected far into space requires a mass of more than 4 million suns. So it would indeed be an enormous star. But we have one problem. There are no visible stars within S2's orbit. You can search for them as much as you want, but you will find nothing. To discern from Earth what kind of object with a mass of 4 million suns is holding S2 in place, scientists have constructed telescopes capable of detecting specific types of radiation invisible to our eyes, namely ultraviolet radiation, or for more impressive images, the second most powerful type of X-ray radiation known to us. Using such a telescope, the object is still not visible, but bursts of energetic light occurring within the ring at some tiny spot are noticeable. What holds S2 in orbit is not only not a star, but far from being as large as it should be. So, essentially, scientists have only one explanation for what must be hidden there. It is a black hole, and moreover, a supermassive one. Scientists named it Sagittarius A, but from Earth, it is impossible to study a black hole reliably, and it is hidden between it and our planet by clouds of dust and gas. Unlike scientists, you are very close. If you are curious about what causes the bursts of energetic light detected by ground-based telescopes, you can find out. It is quite understandable that being near an invisible monster makes you feel somewhat unsafe. Who knows what such a black hole is capable of? What if it swallows your mind, and then it may never reunite with your body? Or perhaps it will be trapped inside, doomed to wander there far from home. What if, as they say, there is a secret passage within it, a door leading to another universe, another reality? In hesitation, you examine the billions of tiny particles of dust, these small objects that make up the bright ring. A moment later, a huge potato-like asteroid flies past you at a speed of 1 million kilometers per hour. You watch it closely as it races through the ring. It breaks apart into tiny pieces of molten matter, burned by the friction caused by the dust of the ring. Just like small asteroids entering Earth's atmosphere, become shooting stars and burn up entirely before reaching the surface of our planet. Thus, the asteroid disappears long before it reaches what lies inside the donut. As you look around for further events, a much larger object flies toward you. Not just a large asteroid, but a big, shining, furious star, like S2, but much larger. I wonder, will it burn up too? Will it manage to pass through the ring? You see it racing toward its fate, entering the donut at an angle. Now it is inside the ring, out of sight, but it soon reappears, having completed half its orbit. Strangely, it appears distorted, as if some mirage caused by some otherworldly force has altered its shape. It continues to fly downward, seemingly under colossal pressure. Planet-sized chunks are breaking off its surface. You try to remain calm, telling yourself there is nothing to fear, but you cannot help it, and your mind suddenly feels so tired and heavy, at the door of catastrophes of mind-boggling scale. Until now, you have been a disembodied being, indifferent to the forces governing the universe. But that is no longer the case. Succumbing to heavy thoughts, you fall under the influence of gravity, completely at its mercy. Against your will, you are pulled inward, sucked into the depths, as if sliding down an unseen but slippery slope. You cross the ring of hot matter and approach the fallen star, being torn to shreds. Finally igniting, it bursts into a blazing stream of sparks of white-hot plasma, spiraling downward and dragging you along toward the still invisible black hole. It goes without saying that your worst fears are confirmed. Hundreds of billions and billions of tons of plasma fall with you. Your heart races as you spiral down faster, 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 until death with immense force ejects you outward. The remnants of the star transform into extremely powerful streams of what seems like pure summer air. You, confused, wonder if you just slipped into a parallel world inside the black hole. But soon, you realize that no, and that you are moving away from the massive monster. Ejected or repelled by the giant black hole, you emerge anew, already far away, like a marble spinning too fast in a bowl. You and the dust of the torn star have been ejected from the black hole without ever reaching its depths. You fell inward too quickly, and you were flung outward, like from a slingshot, long before reaching the invisible monster. The same happened to the star, and its matter transformed into two jets of the most powerful energetic radiation known to humanity, X-rays and gamma rays. One jet shoots upward, the other downward, sending light not only into the yawning space between the stars of the Milky Way, but also much farther, toward vast cosmic voids. The speed of these jets is astonishing, as is yours. One of them catches you and whisks you past millions of stars, like a giant finger with a ring of the Milky Way pointing the way. Perhaps the time to jump into the black hole has not yet come. Or maybe nature wanted to show you even more wonders of the universe before allowing you to face the black hole. Whatever the reason, your pulse normalizes and your thoughts clear again, freeing you from the grips of gravity. You are far away and once again enjoy complete freedom of movement. Nevertheless, you follow the jet for a while, observing where it leads, and soon notice something strange happening. The surrounding stars seem less and less numerous, until soon there are none ahead of you. Some sources of light still shine in the distance, but in reality they are much farther than anything you have seen so far. Strangely, the ring of the Milky Way has also vanished. Trying to understand where it has gone, you look down and gasp at the sight of the most extraordinary scene of your life. No human being or human-made object has ever been privileged to witness such a spectacle. As a result of observations of Earth, several images of the vicinity of the black hole you just escaped have been obtained, but this is not about it now. If you were to call Earth from your current location, the response, if it comes, would take more than 90,000 years to reach you. You are above the Milky Way, above your galaxy. If, gazing at the night sky from a sandy beach, you believed it stretched to the end of the universe, now you see that it does not. Far from being everything, the Milky Way is nothing more than an island of stars lost in the darkness of a vastness of much greater scale. Chapter 7. The Milky Way. The first humans to venture into space returned awestruck by the beauty of our planet and its tiny size in the ocean of darkness. But that was just the beginning. What you are looking at now is even more astonishing. You knew that the Milky Way is a galaxy, but only now do you see what that truly means. It does not matter whether you are above or below it. A cloud in the night sky of Earth, looking nothing like clouds at all. It resembles more a thick disk woven from gas, dust, and stars directly beneath you at such distances that it would take light tens of thousands of years to traverse them. 300 billion stars scattered, bound together by gravity, rotating around a bright center. If you imagine the solar system with its planets, asteroids, and comets as our cosmic family, Proxima Centauri as a neighboring star, then the Milky Way can be viewed as our cosmic metropolis, a thriving city of 300 billion stars, one of which is the Sun, intertwined in the void in a whirlwind dance of clusters of stars, dust, and gas. Scientists call them galaxies, and just as our star was named the Sun, the Milky Way has become the name of this noteworthy galaxy. In our galaxy, 4 enormous bright spiral arms, separated by patches of darkness, swirl around the center, where they meet a yet brighter bulge of gas, dust, and stars, hiding a black hole beneath it, from which you just escaped. From where you are, only the jet of energy bursting from it is visible. The month you have traveled, if you are struggling to grasp what exactly 300 billion stars are doing together, do not worry too much. In fact, no one can fathom that mystery. But if upon returning to your tropical island, you try to explain to your friends what you saw from above, numbers will not help. Instead, suggest they take a square cardboard box 1 meter high and fill it to the brim with coarse sand from the beach. Now ask them to fill 300 such boxes with the same sand. There are as many stars in our galaxy as there are grains of sand in all these boxes combined. Then ask your friends to fly to London, dump the contents of these 300 boxes onto Trafalgar Square in the shape of a disc, and draw 4 spiral arms on it. Now suggest they climb onto the shoulders of Nelson's monument. What they will see will resemble the 300 billion stars of the Milky Way lying before them. And if you tell your friends that before they poured out the sand, you had previously marked a yellow dot on one grain and asked them to find it, they will understand how difficult it was for your mind, hovering above the real Milky Way, to figure out where the sun is, let alone the 100 times smaller Earth. Finding an unknown star is hard, but star hunters are still continuing their challenging work. While hovering above the Milky Way, your mind nevertheless has an advantage over your friends. You can picture all the photographs of the night sky ever taken by humans from Earth in space and compare them to what you see. For years, scientists have created a map of the stars in our galaxy, and never leaving the Milky Way, have had a fairly accurate idea of where the Sun and Earth are located within it. To compare images of the night sky, efforts must first be concentrated near the galactic center, close to the bulge and the black hole, where everything is so bright, beautiful, and filled with energy. Isn't it natural for a species like ours to gain a privileged position? Isn't it logical, considering our importance, and quite fair for the Sun and Earth to be part of the galactic splendor? No, it is illogical. The solar system is located about 2/3 of the way between the black hole at the center and the edges of the galaxy, somewhere on one of the 4 bright arms, a completely unprivileged spot. And, continuing to salt your wounds, you now observe that everything is vast compared to us. Even our galaxy itself is quite insignificant by cosmic standards. Turning your face to what remains to be visited out there, beyond the Milky Way, you notice several glowing clumps, apparently marking distant corners of the universe. I wonder, are these clumps stars? They seem too blurry, too distant. Are they? Or could they also be galaxies? And can they be seen with the naked eye? The answer to the last question is no. On Earth, every time you looked up at the night sky, all the twinkling stars you ever saw belonged and still belong to the Milky Way galaxy, the spiral disk you just observed. All of them, even those stars that seem to be quite far from the whitish band crossing the night sky, are not an infinite sphere, but the final disk and the Earth are not located at its center, but closer to the edge. Consequently, different parts of the sky look very different, filled with stars, just as the view of the night sky varies in different places on Earth, as each one faces a different part of it. It turns out that the Earth's axis is tilted in such a way that the southern hemisphere always looks towards the galactic center, while the northern hemisphere looks in the opposite direction, where there are significantly fewer stars. As a result, the northern sky is quite dim compared to the southern sky, as seen from the beaches of a tropical island. What is called the Milky Way is merely a small piece of the galaxy, a band containing hundreds of millions of stars that are too distant to be seen individually. At night, The overall glow forms a hazy ribbon, and when you gaze into the distant unknown, trying to focus your sight on the most mysterious places, you suddenly realize that all these clusters of light appear just as blurry as the Milky Way, and they too must be galaxies. While you ponder this, another galaxy suddenly rises before you, and you are astonished. The edge of the galaxy emerges from below the horizon, but quickly begins to grow. This is the Andromeda Nebula, our galactic elder sister. It is so vast that it is hard to believe that humanity took so long to discover it. Viewed from Earth, the Andromeda Nebula covers about 6 times the area of the night sky compared to a full moon. But it is so far away that despite the billions of stars it contains, the naked eye can only see a thickening at its center, and it appears tiny. The first person to notice it, whose written accounts have survived to this day, was the outstanding Persian astronomer Abd al-Rahman al-Sufi, around the end of the first millennium, over 1,000 years ago, when many people around the world spent their short lives fighting each other, devising elaborate torture devices, and fearing the end of the world. He observed the stars. Al-Sufi, one of the greatest astronomers of the golden age of the Abbasid Caliphate, described the thickening at the center of the Andromeda Nebula as a faint cloud of light. He had not yet had the opportunity to learn that this was another galaxy. He did not even suspect that the concept of a galaxy existed. In fact, such knowledge emerged about 1,000 years later. No one knew about galaxies as separate clusters of stars until the 1920s, thanks to the research of the Estonian astronomer Ernst and the American astronomer Edwin Hubble. They were the first to notice the vast spaces separating other groups of stars from the Milky Way, making them independent, fully fledged objects. The Andromeda Nebula is the closest cosmic evidence that the Milky Way is not the entirety of the universe. Looking at it, you realize that the Milky Way, with its grand spirals of billions of stars, is swirling around each other. And now you know that all galaxies in the universe are engaged in a cosmic ballet, where the dancers are solitary shining islands made up of billions of stars, moving within the darkness of cosmic emptiness. You scan the cosmic horizon, overwhelmed by extraordinarily strong feelings, as your mind begins to scan the Milky Way, the Andromeda Nebula, and others, both distant and near galaxies. At this moment of enlightenment, everything around you suddenly becomes visible. Tens, hundreds, thousands, and millions, hundreds of millions of galaxies. They form groups of various sizes everywhere, peculiar thread-like structures crisscrossing the visible universe. Who would have thought just a few minutes ago, and it had been hours, that you were lying on the beach on vacation? Now, the entire visible universe resides within your mind. You have reached such a vantage point that the points amplifying the universe are no longer individual stars, but groups of galaxies, each containing thousands of galaxies, in turn formed by hundreds or billions of stars. And the Milky Way is just one of them. As you contemplate this astonishing picture and its individual fragments, you cannot shake the thought that you have no less of a problem finding your home galaxy than searching for the sun in the Milky Way or a peppercorn in Trafalgar Square. Nevertheless, you release your mind and race at the speed of thought, observing the swirling, dancing galaxies tearing apart and colliding with each other, and the disappearance of tiny ones, simply swallowed by their gigantic neighbors. But now, is it worth worrying? In an instant, you return to the Milky Way. The Andromeda Nebula is above you. It is immense, and perhaps it too will one day merge with the Milky Way. These two galaxies are, of course, moving somewhere relative to each other, but something else is happening. Upon closer inspection, you suddenly jump in place, realizing that the Andromeda Nebula and the Milky Way are actually falling towards each other at an astonishing speed of 100 kilometers per second, leaving only 4 billion years until their collision. They will begin to merge 1 billion years before the Sun explodes. Barely recovering from the horrifying thought of how humanity might avoid such a fate, you breathe a sigh of relief. Galaxies are so vast, and there is so much space between stars that a collision of galaxies is unlikely to cause stars to crash into each other. There is certainly some risk, but for now, you will have to come to terms with this thought. At this stage, it is perfectly normal to share Copernicus's depressive philosophical views. You might even wish to live several millennia ago, when the Earth was flat, feeling like the center of the universe for the obvious reason that we, humans, considered ourselves special. How comforting it was to believe that everything revolved around us, and even angels spun some magical wheels attached to a cosmic clockwork, making the stars and the sun rotate. Why, for heaven's sake, did the Polish mathematician and astronomer Nicholas Copernicus ruin our peace by proclaiming that the sun does not revolve around the earth? Who asked the 17th century mathematician and astronomer Galileo to find out that Jupiter has moons that do not revolve around the earth, or that the sun is, for that matter, as they revolve around Jupiter itself? And what of the Epic of Hubble? What is it to Anacina's sport? What, besides the fact that they were right, the incomparable Copernicus and Galileo, would humanity seem doomed? And perhaps worse, I would never have written this book. You would never have embarked on a journey through our cosmic surroundings by the power of thought, let alone venture beyond them, as you intend to do. And, between us, it would be a shame if all the beauty unfolding out there remained unseen, unexplored, or worse, visible only to other intelligent beings from their own distant cosmic perspective. And again, the question arises, since we are touching on this topic, and the sizes of the visible universe begin to drown in our minds, do aliens really exist? Are there, among these billions and billions of star groups shining in the dark-covered universe, red dwarfs like Proxima Centauri, surrounded by their own planets? Do double stars illuminate habitable worlds or other Earths? It is hard to believe that we are alone in this gigantic universe. If we are alone in the universe, it seems like a terrible mistake of the cosmos, wrote American astronomer cosmologist Carl Sagan in 1985. And still, 30 years later, no one on Earth knows for sure whether extraterrestrial life exists. It is exciting, yet simultaneously terrifying and full of possibilities. But so far, we are only talking about possibilities. However, all of this may change very soon as our telescopes begin to discover more and more new worlds. I, for one, sincerely hope that some form of other life exists. Even in the darkest periods of chaotic human history, some people heroically challenged religion, asserting against all odds the probable existence of other worlds. The Italian Catholic monk Giordano Bruno, for example, was burned alive in 1600 for daring to voice the legal thought that there are countless suns and countless Earths orbiting their suns. He died in agony for his beliefs. Today, despite the fact that, in my opinion, there are too many people, even in the most developed countries, who would rather pretend to be deaf and blind than confront those unsolved mysteries and facts, we are informed, and better than any inquisition. Potential Earth-like planets have been found, and Giordano Bruno's views have been repeatedly confirmed, albeit relatively recently. Humanity has known of the existence of planets like Jupiter and Venus for centuries. This is a fact. But for the first time in history, someone actually saw a planet orbiting a star that is not the Sun only 20 years ago. Then, in 1995, two Swiss astronomers, Michel Mayer and Didier Queloz, discovered a giant world they named 51 Pegasi b, which orbits a star located about 60 light-years away from us. Discovered by Mayer, this planet is uninhabitable, but only because it is too close to its star. Nevertheless, following their discovery, this planet began to reveal several new similar worlds each month until their search was sent to a specially designed satellite, Kepler, launched in 2009. NASA's astronomical satellite, one of them. To date, more than 6,000 candidates for planets have been discovered, with about 2,000 confirmed planets orbiting distant stars. Some of them belong to binary systems, meaning they orbit two stars. And soon, news channels expect many more surprises. To distinguish these planets from Venus, Jupiter, and other planets of our solar system, they are commonly referred to as exoplanets. By the way, about a dozen of the 2,000 exoplanets are potentially Earth-like, and at least 3 of them, including Kepler 442b, whose existence was officially confirmed in 2015, bear a striking resemblance to our Earth. All these other worlds may indeed turn out to be barren, but they may also harbor life. Frankly, I am willing to bet that direct or indirect signs of extraterrestrial life will be found within the next 2 decades or so. Perhaps on one of the discovered candidates, or perhaps on some yet undiscovered ones. Modern technology is practically ready to detect signs of biological activity in the atmospheres of such distant worlds. It would be wonderful to make such a discovery. The truth is that so far, all exoplanets discovered are within the Milky Way galaxy, which means they are relatively close to Earth. Planets that could exist in other galaxies are too far for any telescopes to detect, even though there may be hundreds of billions of them. The Andromeda Nebula, for instance, could very well be teeming with life. It is the largest of all the galaxies surrounding us, and very close in galactic terms. Of course, not in human terms. A call made right now, from Earth to one of its billions of stars, will take approximately 2.5 million years to reach it. So if we want to make contact with someone, it's better to find a worthy question in the appropriate language. Chapter 8. The First Wall at the End of the Universe. So, what size does the visible universe have? And if one could fly somewhere infinitely long, how long would the flight take? Is there any limit? Well, as someone is bound to ask you this question sooner or later when you return to your body, it's better to figure it out now. You confidently choose the first direction you come across and race towards it. As soon as you begin to distance yourself from your home galaxy, you immediately realize that the Milky Way is part of a small group of 54 galaxies, gravitationally linked to each other. Scientists have named it the Local Group. It encompasses a sphere with a diameter of about 8.5 million light-years. The Milky Way is the second largest galaxy in the group, while the Andromeda Galaxy is the largest. Beyond lie other groups of galaxies, some of which consist of several hundred galaxies. These large clusters are much larger than our group and are called galaxy clusters. Moving forward, you fly past a supercluster containing tens of thousands of sparkling spiral and elliptical disks made up of countless stars, gravitationally bound to each other and to the walls of space-time. These superclusters form mind-bogglingly large-scale structures. Leaving everything familiar behind, looking at the universe from other positions, you realize that you will have to revise your relative size in the scales of the universe once again. Your eyes, ephemeral being, are wide open. You turn around, peering everywhere, examining sources of light in all possible directions. There is no concept of up or down here, no difference between left and right. You are now more than 1 billion light-years from Earth, and billions upon billions of sparkling galaxies are scattered across the impenetrable darkness. The nearby and distant galaxies, groups of galaxies, their clusters, superclusters, and each other are separated by such vast distances that they are far greater than all the paths you have traveled so far. It is hard to believe that the Milky Way is just one of these points, and yet you know that what you see is not a fantasy, but a known fact to humanity. Nevertheless, whether it is true or not, the thought of saving Earth already seems devoid of any meaning. Why? Doesn't it all seem irrelevant? It is entirely natural that the thought of abandoning everything and allowing yourself to drift forever in the extraordinarily beautiful grand reality becomes quite tempting. Why not spend your life here? Perhaps this is precisely what scientists in their laboratories dream of. While you contemplate the idea of whether or not to return to ordinary life, strange feelings begin to wash over you, filling your mind with new energy once again. Why? Everything you see, wherever you travel, is what humanity understands by the word universe. In one way or another, you are traveling through the universe captured in the human mind, so all its vastness is contained within the limits of the human brain, if such limits exist. How surprisingly reassuring it sounds, but it is a comforting thought that brings you back to being a human among beings capable of directing thoughts at the distance of a glance and far beyond. Scanning the surrounding cosmic landscape, you wonder, is it possible to encompass even more? Can your mind grasp even more? Whatever the fate of Earth may be, you decide that knowledge is better than ignorance. Your virtual heart races again with curiosity, and you desperately surge forward, flying past thousands of millions of subsequent galaxies. As always happens, you quickly become accustomed to everything, and even the grand universe soon ceases to shock. What felt like despair just a second ago now seems to have transformed into joy. Here and there, you observe colliding galaxies, the transformation of stars into superstars, supernova explosions momentarily overshadowing billions of their brothers and sisters throughout the universe. Everything moves around. You are incredibly fortunate to witness its staggering scale and inhuman beauty. Without looking back, flying forward, you are now 10 billion light-years from Earth. Your mind continues to soar further, to 11 billion light-years from Earth, 13 billion light-years, and this number keeps growing. In delight, you search for the end of the universe and find none, but your mind slows its flight considerably. The number of galaxies around decreases, and the stars that comprise them seem larger. They are colossal in size. Frankly speaking, some of the stars you have spotted are hundreds of times larger than the average star of the modern Milky Way. You continue to push forward, albeit at a slower pace. The number of light sources around catastrophically diminishes, and at a distance of approximately 13,500,000,000 light-years from Earth, almost all of them disappear. You stop. Have you reached what you were searching for? Does the universe actually have an end? You recall discussing this question a couple of times with friends before a joint trip to a tropical island, but you never gave such thoughts any real significance. And now you wonder if you thought about whether it is possible to fly away from Earth in the universe forever and continue to see galaxies. Well, since you are traveling through the universe based on observations from Earth, let me point out the following. Telescopes have shown us everything. There is undoubtedly a limit to what we can and will be able to see with light. Your mind has not yet reached it, but it will soon. At this moment, it is traveling through such distant places in space-time that the first stars have not even been born yet. For this reason, the place you are crossing is called the cosmic dark ages. Any radiation emanating from here takes 13.5 billion years to reach Earth. Then, during the 800 million years of this era, the first stars began their work of transforming small atoms of hydrogen and helium into the matter from which other planets and stars are made. This was the first generation of stars. Our Sun is a second or third generation star. Continuing to fly forward in anticipation of the darkness that has forever set in, you suddenly reach a point from which no light penetrates. This surface appears to be a wall in space-time. Beyond it, the universe is not dark. It is light impenetrable. You stop right before the wall. Extend your virtual hand forward, cautiously checking what lies beyond it. Goosebumps run down your non-existent skin as soon as you touch what feels like a gigantic amount of energy. The energy is so dense that you suddenly realize why light cannot penetrate there. It is the same as lighting a torch inside a wall. Beyond the surface you are facing, light exists, but cannot spread freely. What you have reached is not a figment of your imagination. These are the most distant places visible through telescopes. This is a place in space and time where our universe became transparent. No light from beyond it, no light that came before this moment in the past, will ever reach Earth in a straight line. No beam of light has ever been captured by any telescope until now. It took theoretical physicists many decades to understand what this means. Eventually, as you will see in the next chapter, they came up with a rather original solution to make sense of it all, and this idea is called the Big Bang Theory. For now, however, it is necessary to accept the fact that you have just reached the end of the visible universe. This surface has been discovered and mapped by telescopes, the surface of the wall that no light can cross. It is called the surface of last scattering. But as you begin to understand how strange and unexpected this sounds, everything around you disappears, and you find yourself on the beach of your tropical island, gazing at the night sky. The stars are still here, as are the trees, the sea, and your friends, and they look at you strangely. You sit down on the sand and tell them about the extraordinary journey you have just made. The sun is dying. We need to find a solution to the problem. The universe is maddeningly vast, and the wall is far away. There is a wall marking the transition from light impermeability to the dark ages. Your friends' strange looks turn into concern. They help you to your feet, walk you to your villa, and in response, you hear the suggestion that the grilled shrimp might not have been fresh, or that the alcohol was too strong. A few hours later, the rays of the rising sun begin to dance in the east, bouncing off the dust in the Earth's atmosphere, particularly the blue part of the spectrum, spreading around and obscuring the cosmos. Lying in bed, early in the morning, to the sound of birds singing, you open your eyes and see the silhouette of one of your friends nearby. Apparently, they have been running alongside you all night. Perhaps it was all a dream, you wonder. Did your mind really travel through the cosmic expanses? When your friend hands you a glass of water and asks how you are feeling, and the fresh morning breeze gently brushes your forehead, you smile, thinking how damn good it is to be back on Earth. And then you smile even wider, and deep inside, you know you experienced something special, something not made up, that everything that happened is true, and that you were lucky to see it without the need to learn. For many years, for some unknown reason, you have seen the universe as it is known today. Relieved by your smile, your friend gets up to bring you breakfast, and as soon as he leaves, you immediately try to capture the experience so you won't forget it, and you cannot shake the feeling that this is just the beginning of a very strange adventure. Sitting in a hammock made of palm leaves and watching the waves flickering on the shore, you recall Earth as you see it from space, spinning around the sun, a tiny blue dot. You remember other stars, billions of stars swirling around the central black hole, lurking near the center of the Milky Way galaxy. Then the Andromeda Nebula comes to mind, along with about 4 dozen galaxies that make up the local group, as well as other groups, clusters, and superclusters of galaxies scattered far into infinity and beyond. No, not to infinity, but to the dark ages, the truths, the surface of last scattering, beyond which light no longer propagates. And you know that whatever direction you choose on your journey, you will ultimately encounter this wall. It sounds as if, on a much larger scale than one can imagine, Earth is at the center of a sphere, the boundaries of which are marked by a wall. Those within the sphere could very well be the entirety of the visible universe ever reachable by humanity. Absorbed, and you are, if you are passively looking ahead towards the horizon. If the surface of last scattering surrounds Earth, then Earth must be at the center of a sphere bounded by a wall. It sounds logical. But then, it follows that Earth is indeed at the center of the visible universe. Stunned, not believing yourself, you shake your head and mutter that this is nonsense, utter nonsense. Yet, you know you have seen it, and if you gathered your resolve, you could return and take another look at all this nonsense. Yes, you will return, but from a different position. Very soon, as a preparation, let me say that what you have seen, the surface of last scattering, is not the end of the story. Beyond it, there are at least 2 other surfaces with walls around them. The first is the Big Bang itself. The second conceals its causes. By the end of the book, you will traverse the entire path to the second wall and venture beyond it. But for now, relax. After all, you are on vacation, and your friend has returned with breakfast. But while you are busy eating, I will help you organize your impressions. Part 2. Understanding Cosmic Space. Chapter 1. Law and Order. Have you ever tried to jump into an abyss from the top floor of a skyscraper? Probably not. Why? You would already be dead if you dared to, and so would everyone else. So how do we all know this? The answer is simple. As mysterious and profound as the reasons are for which the human mind has already managed to conquer Earth and a small part of the sky by day. The reason you were able to embark on a journey to the stars in the first part of the book is related to nature and its laws. Regardless of how educated we are, whether we love science in school, or whether we are scientists, if we look deep within ourselves, we all have an intuitive knowledge that there are certain laws in nature that cannot be violated. And if someone jumps from too high a place, they are doomed to fall and be smashed to bits. For thousands of years, separating us from our hunter ancestors, many men and women have been in constant search for these laws, and they have managed to find some. Today, the field of claims for the continued unraveling of the quest and the further unveiling of nature's mysteries is called theoretical physics. And the door, this majestic building that is constantly under construction, is about to open before you for the continuation of the journey. It is quite possible that this building arose when the English astronomer, physicist, mathematician, and natural philosopher Isaac Newton created a new language, the language of mathematical analysis, that allowed him to describe almost everything that can be sensed by human senses. You know that if a person, regardless of whether they are male or female, steps into an abyss, they are more likely to crash than to float in the air. Formulas have been defined. Once it becomes known how to account for falling, Newton's formulas tell us where and when it will end. The same formula determines that the moon makes a complete orbit around the Earth in almost 28 days, while the Earth orbits the sun in a year. This noteworthy formula is called Newton's universal law of gravitation. Thanks to it, Isaac Newton is still considered one of the greatest minds of all time. You don't need to be a scientist to guess that discovering such a law makes one feel like a genius. And Newton would certainly have been very pleased with himself. However, strangely enough, instead of throwing feasts every night, as I would have done, he preferred to verify his correctness and began testing whether his law of gravitational attraction truly deserved the title of universal. Scale plays a significant role here because, as you have already discovered in the first part of the book, Earth is not that large compared to the universe. There is not a little. What is true for a tiny speck may not be true for a galaxy. In times past, there were no experiments on Earth that could prove the formula wrong or disprove it. An arrow, for example, always falls to Earth, and so would a mountain if someone were to drop it. But what about larger scales? For instance, in places where gravitational effects are more noticeable than on our planet. To answer this question, one must leave the confines of Earth. And since you have already explored the nearby universe, you know that the most obvious, simple, and, moreover, the brightest place to conduct experiments is the Sun. Chapter 2. Restless Mercury. The gravitational pull of our star, the way it attracts you to its surface, is about 28 times stronger than on our planet. But the Sun is far from being the most gravitationally powerful star you encountered while exploring the cosmic space in the previous part of the book. Black holes, for example, are much more powerful. Nevertheless, the Sun far surpasses Earth, and experimenting with it is much easier than with black holes. So does Newton's formula work on our star just as it does on our planet. And how can this be tested? As you have seen, the solar system consists of 8 planets. Ranging from the most distant to the closest to the Sun are Neptune, Uranus, Saturn, Jupiter, Mars, Earth, and Venus. It may be worth taking a closer look at how they move through space and checking whether they are attracted to the Sun, as Newton's law suggests. Thanks to many astronomers who preferred observing stars over the joys of family life, humanity has obtained an accurate description of the orbits of some planets since Newton's time. The answer seems too good to be true. Considering how planets interact with one another, all the mentioned planets indeed move according to Newton's formula. What a relief! The formula has proven to be universal. Newton's mother must have been very proud of her child. But wait. Observant readers have surely noticed the absence of one planet in the list provided above. We named only 7 out of 8 planets belonging to the solar system, omitting one, the closest to the Sun, experiencing the strongest gravitational pull from the Sun, Mercury. And it is with Mercury that a tiny problem arises, a small discrepancy. Nothing significant, so trivial that it is not taken seriously, yet it is still considered. For several centuries after Newton's works were published, this small discrepancy changed everything humanity knew about space and time. Mercury is not particularly impressive. It is only slightly larger than our Moon, being the smallest planet in the solar system. It is a rocky planet with battered asteroids, covered in craters. It is unlikely to disappear over time. Mercury has no atmosphere, and no weather will smooth out its irregular scarred shape. In short, Mercury is not the kind of planet one would choose for a vacation. It takes 59 Earth days to complete one rotation on its axis, meaning one night on Mercury lasts a month on Earth, followed by an equally long day. Whether day or night on Mercury, conditions are hellish. During the day, temperatures can reach 400 degrees Celsius, only to drop to minus 180 degrees at night. Newton was unaware of such details, and probably could not even imagine how harsh Mercury really is. However, we now know how it is. According to Newton's formula, the trajectories of all planets around the Sun should resemble slightly compressed circles. As I mentioned earlier, Newton's calculations for all planets perfectly matched and continue to match observations. If planets could leave trails behind them, each would trace an elongated ellipse in the sky, repeating this path year after year, almost unchanged, as Newton calculated. But then there's Mercury. Mercury's orbit spirals in on itself, and like an egg spinning on a table, Mercury does not retrace the same path twice. This primarily occurs due to the influence of other planets. They pull tiny Mercury toward themselves every time they come close. As Newton guessed, it is mainly due to this, but not entirely. The discrepancy is tiny, but it exists. Imagine the distance traveled by the second hand on an old-fashioned clock, both the big and small hands, in just 1 second, and divide that segment into 500 parts. 1/500th is the angle by which Mercury's elliptical orbit deviates from Newton's calculations. Over the past century, it may seem incredible that such a tiny deviation could be noticed at all, without forcing scientists to wait hundreds of thousands of years. But it happened. Moreover, we now know that there is no way Newton's formula could have predicted it, let alone explained it, because it does not conform to the aspects of gravity that Newton could even imagine. Newton's equation establishes how objects attract each other, but says nothing about what gravity actually is. Poor Newton and many other scientists spent a considerable amount of time trying to understand where it comes from, whether it is a property of matter that causes objects to pull together, and if so, no visible or invisible elastic rope between our feet, the ground of our planet, or between Earth and the Moon, has ever been discovered. And what about a magnetic tether? As you can see, magnets do not stick to our feet when we try to hold them because our bodies are electrically neutral. Thus, gravity cannot be a magnetic force. So what is it? And why should stubborn Mercury, the smallest of the planets, differ from all the others? Newton died in 1720 without finding an explanation. 188 years passed before someone suddenly came up with a rather strange new idea. Chapter 3, 1915. A positive aspect of research in physics is that when observations do not align with theory, it is first assumed that they are incorrect. Then the experiment is redone, and if repeated attempts stubbornly yield incorrect results, it is checked. What if some unknown scientist anticipated such an outcome using an alternative theory? If the answer is still negative, it is reasonably assumed that we have no idea why nature behaves this way. The safest option in this case is to try everything. Obviously, this includes even the most absurd ideas, and I must say, it is a very entertaining endeavor. As we will see later, the ideas taken today to explore how our universe came into being are worthy of the best examples of science fiction. As the royal astronomer Sir Martin Rees once remarked, good science fiction is better than bad science. Overall, most of these ideas are indeed entirely wrong, but you never know for sure. It is important to search and see what comes of it. So far, this approach has worked quite well. Thus, Newton's formulas were used for nearly 2 centuries without any problems. And, to be honest, the hitch with Mercury did not significantly impact the lives of most people. But then scientists came along with completely nonsensical ideas about gravity. Imagine space, with the sun and Mercury revolving around it, and forget everything else. They are alone in the universe, a small rocky planet orbiting a huge shining sun, surrounded by emptiness. Now let's remove Mercury and the other planets, just to understand that nothing remains. What if gravity has something to do with this remaining nothingness? That is, the very fabric of the universe, whatever it may be. To explore what might happen in this case, let's return to the sun. Let's consider the thought. If the fabric of our universe can be influenced, one of the simplest actions the sun could take would be to bend it. How? Well, imagine a heavy ball resting on a stretched rubber mat. The rubber will sag under the weight of the ball. If you then rub the rubber mat with soap, anything that ends up on it, even ants that get too close, will slide down toward the ball due to the sagging. For the ant, this effect might feel like attraction or gravity. Clearly, if stars and planets were lying on soapy rubber, I hope we would have noticed by now. Thus, the fabric of the universe cannot be a flat, solid rubber mat. However, it could be an invisible 3- or even 4-dimensional fabric. And regardless of what this volumetric fabric is made of, why not imagine it wrapping around the matter contained within it? Certainly, not just on a flat plane, but in all directions, like a sphere immersed in an ocean surrounded by water. If we take this idea seriously for a moment, gravity would simply be the result of such bending. Every time something falls, it does not fall due to a force pulling it down, but because it slides down the invisible slopes of the fabric of the universe until it hits the ground, or some object preventing further descent. I agree, but why not give it a chance in the end? And how would objects move through the universe according to it? For all planets, including Mercury, geometric calculations using this theory yield exactly the same results as Newton's, which is both reassuring and interesting. So what about Mercury? The person who came up with this nonsensical theory of curvatures discovered that in the universe he described, the flattened circle of Mercury's orbit should rotate around the Sun, deviating from Newton's calculations, and thus deviating by an angle corresponding to approximately 1/500th of a second on a clock every century. Amazingly, for more than 15 decades after Newton's death, no one was able to figure this out. But he did, and was right. Gravity suddenly ceased to be a mystery. It is the bending of the fabric of the universe caused by the objects contained within it. Newton did not see this, and no one noticed it before. And today, we are still trying to understand all the implications of such a perspective. Stephen Hawking often says, "I wouldn't compare the joy of discovery to sex, but the pleasure of the former lasts much longer." A glance at the photographs of the person who solved the Mercury problem seems to prove his assertion. His name is Albert Einstein, and the theory we just presented, linking matter with the local geometry of the universe, is called the general theory of relativity. This theory was first published in 1915, 100 years ago, and it took scientists some time to realize that Einstein had inadvertently made a revolution in our understanding of everything. Contrary to everything that was believed before him, he discovered that the universe could not only have a shape, but was also dynamic, meaning it changed over time. Since stars, planets, and everything around them move, the distortions they create in the fabric of the universe move along with them. And what is true on a local scale around these objects may very well be true for the universe as a whole. In other words, even if Einstein himself did not believe it, he discovered that the universe could change over time and have a future. And if something has a future, then it could also have a past, and therefore a history, and perhaps even a beginning. Before Einstein, it was thought that our universe simply always existed. Now we know that this was a mistake, at least in our current understanding, and we have believed so for an entire century. Thus, regarding the knowledge of the universe we live in, it is 100 years old. Chapter 4. Layers of the Past. The journey through the known universe undertaken in the first part somewhat resembles a walk through the forest of a tropical island, where you were struck by the beauty of the local trees. After such a walk, you could certainly return to your villa, call your friends to the table, and tell them how wonderful it was to stroll and breathe in the fresh ocean air. But then your friends might calmly ask you, why do trees grow? Why and how are they green? And why do they look the way they do, rather than otherwise? If we imagine the universe as a forest, what can we find there? Instead of questioning the freshness of the food or the shrimp, what fundamental questions should you ask your friends? Are there any other methods for understanding the universe besides empirical ones? And if we are being serious, is it even possible to travel through it? How do you feel about the last question? The answer is simple. In a physical body and on a spaceship, no. As far as we know today, traveling through space and time, except by the power of thought, does not seem possible. No carrier of information can move faster than the speed of light. So what your mind did in the first part was essentially a flight over a frozen three-dimensional map of the unknown universe, a reconstruction obtained from gathering all the images taken by telescopes that have ever existed on Earth. You might argue that you saw everything in motion, that it was not a still image. Of course, Let's say the picture appeared almost frozen. And now, what conclusions can be drawn from it? If the laws governing the evolution of everything, the next morning, after returning from a virtual journey of the mind, when your friend on duty at your bedside left for breakfast, intuitively knew that everything was still out there on the street, even when they could no longer see it, did you not start to imagine that he had dissolved into thin air, gone back in time to hunt dinosaurs, and returned with a roast prepared for you from Europe? That would certainly be quite cool, I admit. But they are passing by for the same reason it is unreasonable to jump into an abyss or throw oneself out of a window. The main reason why that will never happen is very difficult to articulate and prove. But if we want to try to unravel the mysteries of the universe, we must accept a few things. So, our first assumption or postulate. More or less, we can understand nature even beyond what our senses suggest. To realize this, we should henceforth consider that under similar conditions, nature obeys the same laws everywhere in space-time, whether here or there, now, in the past, or in the future, regardless of whether we can see it and whether we know these laws. Let's call this the first cosmological principle, in bold, because it is important. If we did not accept this, we would be completely stuck, unable to decipher what is happening in inaccessible or too distant places, or in a time too far in the past. If we did not make such an assumption, your friend could very well have gone back in time to hunt a delicacy dinosaur. In reality, there are many indications of the correctness of the first postulate, at least within the visible universe. Let's take the sun. We know what particles, what frequencies of radiation, and what types of energy emanate from its surface. We detect them as they shoot off its surface and land on Earth. And what about other distant stars? Do they shine due to the same nuclear reactions or completely different ones? Are they like logs thrown into a fire, or are they made of plasma like the sun? We do not have many tools to investigate such questions, and in fact, only one: the light received from those stars. It carries many secrets, and one of them that we have managed to decipher states that the laws of physics are the same everywhere. And since light is the key to understanding the cosmos, let's see what it is. Light, also known as electromagnetic radiation, can be viewed simultaneously as a particle, photon, and as a wave. As you will see later, both definitions not only work, but must be taken into account if we want to understand our world. For now, however, it suffices to consider it simply as a wave. To describe ocean waves, two things must be defined: their height and the distance between two successive crests. This height is obviously significant. Naturally, you would not react the same way to an approaching wave 5 meters high as to one 2 millimeters high. The same thought applies to light. The height of its wave is related to what we call the intensity of the radiation. Similarly, there is a difference between ocean waves that are hundreds of meters apart and those that are very close together. This distance is called the wavelength. The longer the wavelength, the fewer waves occur in a given period of time, meaning the number is related to the frequency of the wave. To intuitively grasp that the shorter the wavelength, or the higher the frequency, the greater the energy involved, imagine yourself in front of a dam. If a 5-meter wave hits it once a month, it would not be a cause for concern, unlike the same wave crashing against it 10 times a second. The same applies to meaning. The shorter the wavelength, or the higher the frequency, the more energy the wave carries. Now the statement. Contrary to what our ancestors thought, our eyes are receivers, not sources of light, and they are not designed to detect all existing types of radiation, neither by intensity nor by wavelength. A source of radiation that is too powerful easily and simply destroys the retina of the eyes, blinding you in a matter of seconds. This is what happens if you look at the sun, a laser, or another excessively intense light source. We can only see light waves that are neither too intense nor too weak. The limitation of wavelengths for our vision is elusive. Over thousands of years, during which our ancestors preserved the genes of those who existed long before they took on human form, their light detection organs evolved to see what was most necessary for survival. To pick a fruit or detect the presence of a saber-toothed tiger, it is far more useful to recognize green, red, or yellow colors than the X-rays emitted by falling stars near distant black holes. In short, our eyes are adapted to the light most necessary in daily life. Thus, if we could only detect X-rays, we would have gone extinct long ago. As a result, what our eyes can see today is quite limited compared to all existing types of radiation. But the universe does not care. It is filled with all of them. And again, we aptly named this visible light, the spectrum visible to us, and assigned its separate parts their own names, colors. The distinction between two colors may sometimes seem quite arbitrary, but there is a very precise mathematical definition based on distance, that is, wavelength. It is true that the eyes of some animals have evolved differently, and that some of them can see light beyond the perceivable spectrum. Summer snakes, for example, have infrared vision, and some birds can detect ultraviolet rays. All of this lies beyond our human visual capabilities, but no animal has ever built devices to detect them, except for us. And we have notably excelled at this. Yearly, according to the amount of energy carried by waves, surrounding light is divided into microwaves, radio waves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Radio waves are very long, ranging from 1 to 100,000 kilometers or more between each wave, while the wavelength of gamma rays is shorter than a billionth of a millimeter. But all of them are light, and all telescopes ever created have been designed to detect light waves, wherever they may come from, regardless of their intensity. To be able to look at the universe through all the possible windows our technologies provide, whether looking at the sky with the naked eye or through a telescope, you capture and process radiation from some distant source in space. Light waves, as I mentioned, your journey in the first part consisted of a three-dimensional reconstruction of all available photos and videos. But perhaps you did not notice that while the journey was cosmic, it was simultaneously a journey through the past, because light does not travel instantaneously. Now is the time for an interesting yet somewhat pessimistic question from friends on the tropical island. Haven't we all heard somewhere at a dinner party or elsewhere how someone boasts of their knowledge that the stars we see in the sky have actually long since died? Is it true? Have all the stars really died? Not quite, at least not all of them. Let's take a look. Suppose your distant cousin loves to give everyone ugly crystal vases for Christmas. She lives in Sydney, Australia, with a slightly old-fashioned future. She never sends anyone letters, except on her birthday in January, when she sends everyone postcards with her photo in front of a mailbox, where she is just about to drop that very postcard. On the back, it always says, "Today is my birthday. It would be lovely to hear your voice on the phone. Love, your grandmother." The Vase, Krypton, I hope you liked it. The problem is that even if you promise yourself every year to remember your grandmother, you still do not. And as always, by the time you receive the next postcard, for her, it has long since ceased to be today. January cannot last forever, and as usual, you hope she hasn't spent the entire month waiting by the phone for a call. In any case, what is important in this story is what your grandmother did a minute before sending the postcard. The photograph you now hold in your hands likely no longer matches her appearance. Your grandmother may very well be dead now, just like some stars up there in the sky. Don't worry, your grandmother is fine, and you will still receive a couple more vases from her, and even make several attempts to teach her to send emails instead of postcards. Surely, that will go faster. New correspondence is not instantaneous. Nothing is instantaneous. With email, you would still receive her photo a fraction of a second after it was sent. So, to reiterate, by the time it reaches you, your grandmother may already be dead. This idea is not meant to instill paranoid thoughts that everyone you know may be dead. Rather, it illustrates what happens in space, where the fastest postal service may use light as a communication device. And however fast it may be, light is far from instantaneously moving through space. Its unrivaled speed reaches a staggering 299,179,282.458 kilometers per second. While you read this sentence, light could circle the Earth 26 times. It is the fastest thing in our world, but surprisingly slow for the cosmos, given the local intergalactic distances. Furthermore, the light from a star always carries a timestamp. It shoots through space at the speed of light, and it can take quite a long time to reach us. This means that the farthest visible stars have likely died, but not all of them. The Sun, for example, is not dead. To be more precise, it is certainly not dead right now. No one knows, but the Sun did not die 8 minutes and 20 seconds ago. As you saw in the first part, sunlight takes about 8 minutes and 20 seconds to travel the distance of 150 million kilometers that separates us. This means that if the sun were to stop shining right now, we would learn of such a significant problem in 8 minutes and 20 seconds. It also means that from Earth, you will always see the sun 8 minutes and 20 seconds in the past. Never. Thus, as the sun is in the sky on a sunny day, it is never as you see it. It is not even in that place for 8 minutes and 20 seconds, the time it takes for its light to reach your skin. The sun will have traveled about 117,300 kilometers along its orbit around the center of the galaxy. Furthermore, the farthest light that has been detected in our universe took a whopping 13.8 billion years to reach the telescope lens, just from the moment when the universe became transparent, with enormous stars beginning to shine a few 100 million years after that event, certainly no longer existing, even if their light still reaches Earth, making them visible to us. The same can be said for many other stars located between the Sun and the distant corners of the universe. On January 24th, 2014, for example, astronomers observed a star exploding in a distant galaxy in the night sky. They saw it live as soon as the light from the explosion reached their telescopes. As far as we know, that star is considered dead as of January 24th, 2014. But if someone lived nearby and witnessed the explosion, they would name a different date, 12 million years ago. To summarize, if we are going to explore the cosmos, modern technology leaves us with little choice. We must use light. No one can teleport to the other end of the universe instantly. As a result, just like with the visible universe, gazing at the night sky is akin to receiving postcards from all sides, stamped at different times and in various places, traversing the universe. Depending on where and from where they started their journey, only by piecing together all these postcards, starting from the edges of the universe, can we reconstruct fragments of history as seen from Earth. That is the fragment you flew over in the first part. Chapter 5. Expansion. I repeat, all information about the distant universe is obtained from the light that reaches us. To decipher and understand it, it is necessary to accurately determine what information light carries and how it interacts with matter and the building blocks, atoms, with which it encounters in space. In the next part of the book, you will delve into the heart of atoms, but for now, it is not necessary to know everything about them. Let's just clarify that atoms can be described as round nuclei surrounded by electrons rotating around them. These electrons are not random. They are organized into specific shells around the nucleus. You can imagine them as planets orbiting a central star. But this can lead to confusion. In fact, we call the trajectories of electrons around their atomic nuclei orbitals with the sole purpose of distinguishing them from planetary orbits. With the right speed, theoretically, a planet can orbit its star at any preferred distance. Well, yes, certainly not in the case of electrons. Unlike planetary orbits, orbitals are separated by forbidden zones for electrons, places where electrons simply cannot be. Furthermore, electrons can easily and effortlessly jump across these forbidden areas from one orbital to another. However, and this is a key point, they cannot just jump around. To move from one orbital to another, electrons must absorb or release some energy. Thus, the farther an electron is from the atomic nucleus, the more energy it possesses. To jump to the next orbital, which is further from the center, it must gain some energy, just as the flame of a burner causes a balloon to rise into the air. Conversely, to move closer to the nucleus, an electron must release some energy. Like a valve releasing hot air from a balloon helps it return to the ground. But where does this energy come from? From the same source as light. Electrons can jump from one orbital to another. We need another light source, but not just any light. Transitioning from one orbital to another causes electrons to jump over the forbidden zones separating them, and performing such an act involves absorbing or releasing a specific amount of energy corresponding to a specific beam of light. If the light falling on them was not sufficiently saturated with energy, the electrons would not be able to make the jump and would remain in their place. Conversely, when excessively energized light beams hit them, they can leap over several such zones and even escape from their atom. This was discovered by humanity in the early 20th century. Such a discovery may not seem groundbreaking, but it truly is. Einstein was indeed an omnipresent figure who received the Nobel Prize in Physics in 1921 for discovering this law using examples from the atomic structures of various metals. Several decades of experiments and reflections conducted since then on all known atoms in the universe have led scientists to understand that energy is necessary for any electron to transition from one orbital to another within each atom, and it depends on the structure of that specific atom. We are very fortunate because different types of energy correspond to various sources of radiation, and with the help of telescopes, we can collect it from almost anywhere. In practice, this means that scientists can determine what distant objects, such as stars, gas clouds, or the atmospheres of distant planets, are made of without even traveling there. Now, let's discuss how scientists manage to do this. Imagine an ideal light source emitting all possible wavelengths of light, from minimal energy microwaves to powerful gamma rays in all directions. Such an ideal source creates a glowing bright sphere. If an atom is at a distance from it, its electrons, dazzled by the amount of incoming light, can absorb all the energy needed to transition to a higher energy level under its influence. During this process, they become excited. This is the correct technical term. The excited electrons are somewhat like children receiving candy at a party. Just as after the party, it is not difficult to understand what candies the children prefer. You only need to check what is left on the table. One can determine which types of radiation an atom has absorbed by looking at which ones are absent in the photograph of its shadows. All unused light passes through the atom unhindered, and its imprints can be easily detected on photographic paper. The absorbed waves appear as small dark spots on a continuous rainbow of colors and light. This photograph is called a spectrum, and the dark spots are called absorption lines. By simply observing the absence of certain wavelengths of light in the spectrum, scientists can identify the elements encountered along the path of the light source. Thus, the use of light is a way to determine the type of extraterrestrial matter without venturing into space. All radiation-collecting telescopes used by humanity up to this point indicate that all stars in the universe are made of the same material as the Sun, Earth, and ourselves. All cosmic objects in the night sky consist of the same atoms as we do. If this were not the case, telescopes would have already informed us. Therefore, it can be assumed that the laws of nature are the same everywhere. This is why the first cosmological principle is universally recognized as correct. What a relief! In fact, this is such good news that while in space, you decide to take another look at distant galaxies to find out what they are made of. Aren't they beautiful? Just consider their wonderful spectra, filled with lines corresponding to hydrogen and helium. But wait, something is wrong. Looking at the obtained spectra, you realize that the missing lines in the emissions of distant stars are not where they should be. While the electrons of certain chemical elements here on Earth get excited by the blue part of the visible light spectrum, ultraviolet light, the same electrons of those same chemical elements in distant galaxies seem to prefer slightly greenish shades for their transitions from one orbital to another. And atoms that thrive here on Earth in the yellow part of the spectrum seem to prefer orange light in space, while those that love orange choose red in space. Why could this be? Are all colors in space shifting, or have we made a mistake in observing the various distant light sources? But there is no doubt. All colors are shifted towards the red part of the spectrum. And what is even more interesting, the farther away the light source is, the more pronounced the shift. Does this mean that ultimately the laws of nature differ in different parts of the universe? If one could stroll on a planet similar to Earth, orbiting a star like the Sun billions of light years away, would you not find yourself in a sky filled with oceans and sapphire green plants, emerald yellow and red? Certainly not. If you were to go there, you would see an alien world just like here, a world where lemons are yellow and the sky is blue. The reason for the observed color shifts is not that the laws of nature differ significantly from ours. It lies much deeper. It has even changed what humanity has believed for over 2,000 years. Have you ever tuned a guitar or any other string instrument? You may have noticed that the pitch produced when plucking a string changes as you turn the tuning pegs. The more you stretch the string, the higher the pitch, right? The significant degree of what you just saw in the sky corresponds to the same phenomenon, except that sound is replaced by light, and the string is not a string. In space, light moves or propagates not through strings, but through the fabric of the universe. And to explain the newly discovered spectral shift, this fabric must be included in the process. Why? Because in this shift, which affects all possible colors in the same way, one must blame not the light, but what it passes through. When you pluck a string, tightening it with the tuning pegs, the sound it produces shifts to higher frequencies, not because something happened to the sound, but because the string was stretched. Guitar strings are stretched in exactly the same way to tune all notes. Now imagine that it is possible to stretch the fabric of the universe like a guitar string. And if one were to do this once, all wavelengths of light propagating through it would immediately become high frequency. Why? Because light can be viewed as a wave, and stretching it would increase the distance between two consecutive wave crests. Blue would become green, green would become yellow, yellow would become red, and so on. In terms of the spectrum, this means that the colors in the universe are indeed shifting towards the red side. This is redshift. Now, instead of a one-time stretching of the fabric of the universe, try to imagine that it is continuously and uniformly stretching. The greater the distance light has to travel, the more pronounced the redshift will be. By the time it reaches Earth, according to this scenario, blue rays sent from distant galaxies will gradually become green, then yellow, then red, then invisible to our eyes as infrared, and finally as microwave radiation. Knowing how much the original color of the radiation emitted by a distant star differs from the final blue color observed on Earth, one can determine how far away that star is. But is this really the case? Does the fabric of the universe behave this way? Yes, it does, exactly as you observe in the sky. But what does this mean in practice? In practice, the actual distance between distant galaxies and us is constantly increasing, which means that the space between galaxies is stretching, and thus, the universe itself is expanding. This means that the universe is changing over time. Countless experiments have now confirmed this theory, and scientists have learned to accept it. We truly live in a changing, expanding universe, although Einstein would not have liked it. 100 years ago, such a theory was not well received. For our ancestors, whether they were scientists or not, the universe always remained unchanged. But they were wrong. For clarity, it is not the galaxies that are moving apart. It is the distance separating us from those distant galaxies that is increasing. The void itself, space, is stretching. Scientists have named this phenomenon the expansion of the universe. And contrary to what one might think, it does not mean that the universe is expanding into nothing. It means that it is expanding and growing from within. Now, before jumping to hasty conclusions, wondering what could cause such expansion, you can verify everything for yourself. So, imagine that you are fantastically wealthy, and, for instance, you have 100 billion pounds in your bank account and 100 friends. As an astronomy enthusiast, You give each of them $1 billion to purchase powerful modern telescopes and travel to different corners of the Earth to collect as much radiation from numerous distant galaxies as possible. After several months, you invite them all to your mansion for a presentation of their discoveries. About half of those gathered turn out to be true friends and showcase their findings. At this point, you can consider yourself quite a lucky person. The other half preferred not to spend their money, but that does not matter because all presentations were identical. No matter where the telescopes were, be it in China, Australia, Europe, the middle of the Pacific Ocean, or Antarctica, everyone who returned to you observed the same phenomenon in the sky. Right above their heads, distant galaxies exhibited strange spectral shifts. All galaxies were receding, and the farther away they were, the faster they were moving apart. All friends witnessed the expansion of the universe. What conclusion should be drawn? While you ponder, a strange thought that had already crossed your mind at the end of the previous section resurfaces. To begin with, the strange visible universe has become a sphere with you at its center. And now, there is also expansion. Does it really exist? If everything and everyone is moving away from Earth, does that not mean that all mothers on Earth are right in believing that their child is the center of the universe? As astonishing as it may sound, it seems that it truly is the case. What wonderful news! What a joyful day! And if any of your friends happen to be nearby while you listen, you can confidently pop open the champagne. After all, we have turned out to be special. Especially in the end, it has been proven. Copernicus was wrong. He should have listened to his mother. Mothers are always right. Everyone living on Earth is at the center of our universe. But wait. What about mothers on distant planets and other galaxies? If they existed and thought like our mothers, does that mean they would be wrong about their children? Or is this evidence that there are no mothers anywhere else? Certainly not. Despite what you have seen, we are not at the center of the solar system, as Copernicus informed us 400 years ago. Most, if not all, scientists today believe that our position in the universe is no more privileged than any other. Strangely enough, this does not mean that we are not at the center of our visible universe. We are at the center, just like any other place. Any location is at the center of the visible universe from there. This highly authoritative opinion has even led scientists to formulate the following additional cosmological principles to unravel what is happening somewhere out there, very, very far from our planet. Scientists propose that there is no privileged position anywhere in the universe. This is the second cosmological principle, and that if a chosen observer were to travel through it, all directions would always appear the same to them. Distant galaxies will always be receding from wherever they are, just as they are receding from us here on Earth. This is the third cosmological principle. If you take a moment to reflect on this before your friends abandon the champagne, the third cosmological principle may seem inherently incorrect. The world clearly does not look the same from where you are now listening to this book and from the shower stall, unless you are listening to the book while showering. Once again, in order, the third cosmological principle does not concern those nearby. It only pertains to the overall picture of the universe on scales far exceeding galaxies. It states that the universe, on super large scales, looks roughly the same in any direction you choose. Nevertheless, It sounds unconvincing, does it not? Did you not travel through the entire universe in the first part? Did you not see places in the distant cosmos where the universe looked different than from Earth? You even traversed a distance of 1,000 light years, where stars did not shine, visiting the so-called cosmic dark ages. How can the universe look the same from Earth as from a place where there are no stars at all? Well, it is time to understand what I truly mean. When I say that, in the first part, you traveled not through the universe as it is, but through the universe as it is visible from Earth. This is not quite the same thing. Remember, the universe that appears at night does not correspond to what the universe is now. It corresponds to a piece of its past history, a history centered on Earth. Because we are on Earth, we receive colorful images every day from any point on the planet. According to the third cosmological principle, those living on a distant planet should hypothetically see the universe exactly as we do. Not in detail, of course, but on a grand scale. They too are surrounded by all the information reaching them from the past. They too are soaring in their night sky through a piece of our shared universe's history. They have all of this, even if their paths never cross with ours. Ultimately, to understand our universe and to get its complete picture, I need to add all the past histories from all points in the universe. Naturally, nearby places have histories that intersect at many points, while places separated by vast distances may not share any common points at all. Nevertheless, all of them must be considered equivalent. This is what the third cosmological principle means in practice. You will hear about it later. By the way, this also means that even if you do not occupy a special position in the universe, you are still, as your mother certainly believed, at the center of your visible universe. And if you feel that you have always thought so, then please fill your body and mind with a stream of joy. This is wonderful news. I repeat, you are at the center of your universe. Now, about what might make you feel less good, and that is your neighbor. He or she is at the center of their visible universe, and so is everyone else. We all and everything around us are at the center of our own universe, which we can explore through the light that reaches us. Only in rare, very special cases can the visible universes of two people completely coincide. Figuring out when and how this can happen, and arranging the waves. So, as they say, it is time to take a closer look at the expanding universe. Expansion is indeed happening. Yes. The distance between distant galaxies is indeed constantly stretching, although this does not apply to nearby objects because gravity is stronger on smaller scales. Galaxies create gravitational attraction, which counteracts such expansion. Just as the distance between the Sun and nearby stars does not expand, neither does the space around them. At this moment, neighboring galaxies are continuously getting closer and closer. However, for larger distances, expansion is indeed taking place. The discovery of the expansion of the universe in 1929 belongs to the American astronomer Edwin Hubble, and the law that connects the distance of receding galaxies to their distance from us is called Hubble's law. Due to this discovery, Hubble rightfully can be considered one of the fathers of modern observational cosmology. He is also the person who, along with Ernst and Pecker, proved that the Milky Way is not the entire universe and that there are other galaxies within it. These two discoveries are undoubtedly worthy of a Nobel Prize if they were made today. However, at that time, observations of stars and attempts to understand them were not regarded as part of physics by either the scientific community or the Nobel Committee. As a result, Hubble never received the Nobel Prize. But after his death, the rules changed, and many prizes have since been awarded to representatives of observational cosmology, some of whom you will encounter in this book. Now, as you prepare to understand the extraordinary implications of Hubble's law of expansion, you are likely to be shocked by how brightly scientists can sometimes appear on the scientific horizon through their reflections, roughly twice the average amount of coffee consumed. They have determined that if everything far away in our universe is currently receding from us, then everything that is now distant was likely closer in the past. You might try to carry this thread of reasoning yourself someday. That will be quite enough for realization. In fact, although this thought may not seem significant, it has become a true revelation. As I mentioned earlier, even Einstein refused to believe it. Why? Why does it matter that distant galaxies are receding or were closer in the past? Remember, the observation-based Hubble's law states that the distances between galaxies are expanding. They are simply moving away from one another. In other words, it is the fabric of the universe that is expanding. Following this idea to its conclusion, it should turn out that the universe as a whole was smaller in the past. But how could this happen? And can it be proven? One can look again into the depths of space. There lies the past, existing so that we can receive its message. The truth you saw at the end and in the visible universe brilliantly confirms this. And why? You will see in the next chapter. But first, we must once again venture into open space to get better acquainted with gravity. Chapter 6. The Sensation of Gravity. Of the four types of fundamental interactions governing the universe, gravity is perhaps the most well-known. Every time you use your leg muscles to lift yourself or pick something up, your body reminds you of its existence. Everything depends on gravity. Everything creates gravity, including you and the crystal vases your great aunt continues to send you for Christmas. Speaking of vases, imagine that you took one with you to an island. Look at it. Now drop it on a hard surface. It will fall and shatter into pieces. Then you can imagine how your entire collection falls onto the hard floor in any places on Earth you can think of. Amazingly, vases will always fall and break, no matter where you are. Not only will such experiments rid you of them, but they will also prove the following. Any object denser than air that you drop on Earth will fall to its surface, as Newton believed, and any reasonable person would agree. But what about objects lighter than air? Why do helium balloons rise into the sky and not fall? Do they not feel gravity? They do, but there is a hierarchy. Every time objects are attracted by the Earth, the densest among them tend to settle lower than the others. If we perceive lighter-than-air objects as rising, it is because the air below is denser and takes its place. If air were visible, you would notice it, but it is invisible, and you only observe the result. Lighter-than-air objects are pushed upward by the invisible air beneath them. It is an extremely interesting phenomenon, and it always causes things to fall. But the hierarchy creates layers, and some objects must move upward to make room for denser ones. You can think of the Earth as a massive ball with a mass of things stuck to its surface due to the steep parabola created by the planet in the fabric of the universe. All objects you have ever seen, including yourself, slide down its slope until the floor, or something denser, prevents you from sliding further. Rocks in the Earth's crust are denser than water, which is why the ocean lies in depressions on the Earth's surface. Rocks and water are denser than air, which is why the atmosphere covers the surface of our planet, whether in solid or liquid form. We, humans, live under hundreds of kilometers of air stuck to the surface of our planet. We are denser than it, so we do not fly, but we are lighter than the soil, so we exist on it. True, sometimes certain objects or animals manage to leave the Earth and find themselves in the sky, but this requires energy expenditure, and it usually does not take long before they begin to fall back, unless, of course, they are lighter than air, which is unheard of and would be quite unfortunate for any animal. Now, about how everything would fall if the Earth were not nearby. Your tropical island, a Sunday morning. Friends bring you breakfast every morning since your mind's strange journey, and they are clearly becoming more and more curious about your story. Some of them even wonder if you really saw what you were talking about. Others have stopped sleeping at night, fearing the death of the sun. Unfortunately, they are likely the ones actively seeking a way to make you stop talking about it all the time, and it seems they have found it. You open your eyes. Tiny dust particles continue to sparkle and swirl in the morning sunlight, even though they too feel gravity, you think. And then someone knocks on the door. "It's open," you shout, sitting up in bed and expecting to see another smiling face, perhaps with a tray of fruits and coffee. The door opens, and there she is, your great aunt, with 3 bags visibly filled to the brim with crystal vases beside her. It seems incredible, but they even declare that you were about to break one for a gravitational experiment. Not at all surprised to find you in bed, she enters the room, approaches the bed, pats you on the cheek, and silently smiles as she hands you one of the vases. Her face expresses an understanding that simple words could hardly convey your joy at her unexpected visit. With the vase in hand, you close your eyes to calm yourself, suddenly desperately wishing for a little sound somewhere else. And when you open your eyes again, you are exactly there, somewhere else, in outer space. Around you, dawn, the bed, and your great aunt all have vanished. You have returned to the stars, just as in the first part of the book, but now everything feels much safer than it did then. Looking around, you cannot help but smile broadly. No signs of an imminent explosion, no molten ground. All the stars are far away. Everything is calm. You float in the middle of what seems to be endless darkness, dotted with tiny lights. When you found yourself in space in the first part, you were merely a mind, except for that moment when you were ejected from a black hole. You felt nothing at all. However, this time you are about to experience something different. You are still on a mental journey, but you have not left your body. You are safely protected by a spacesuit, existing in a state of weightlessness. Everything feels so real that you start to feel genuinely nauseous, but soon you adapt and notice that, although your great aunt is no longer nearby, you still hold the vase she gifted you. Grinning, you look around again, but there is nothing here to break it against. No ground, no stars. Not flustered, you decide to conduct another gravitational experiment. Extending your hand forward, fingers spread in a T shape, you let go of the vase. But as far as you can see, it remains right where it was. A minute passes, then 2. Still nothing changes, but only the vase does not float a bit closer, but not much. Nothing particularly noteworthy. Finally, tired of watching this nonsense, you push the vase with the tip of your finger and watch as it slowly drifts away in what seems to be a straight line, like a road. If you had not pushed it, the vase would have remained nearby. It would not have fallen. And in what direction could it fall in the absence of planets and stars, as well as the concepts of up-down or right-left? In the center of nothing, all directions are absolutely identical. There is no surface of any kind to attract the vase, unless, of course, you consider yourself that surface. But that would mean insulting your own self, would it not? Well, when it comes to nature, one should not take anything too personally. For after some time spent idly, to your great disappointment, you see the return of the vase. Gravity works. Gravity created by you. Although a strange question arises, will it float to the quantum, or are you quasi to everyone else? You might say that the vase could very well be the surface onto which you are falling. Unfortunately, you cannot think the idea all the way through, because an asteroid suddenly zips by, separating you from the approaching vase with invisible gravitational fingers. If you were asked, you would probably answer that being heavier, you would reach the asteroid first. But nothing of the sort happens. You touch it, the dust on its rocky surface simultaneously. And as soon as your feet feel the soft ground, you immediately grab the failed work of art to smash it into pieces. Unfortunately, the surface of the asteroid is not as solid as Earth's, and you do not break it. Instead, you are immediately surrounded by a huge cloud of cosmic dust. Frustrated, you pick up the vase with all your might by its seams, love it, and in the cosmos, you go to get rid of it once and for all. This time, there are no chances of the vase returning, and you breathe a sigh of relief as you watch through the dust clouds how it dissolves into the distance, doomed to forever spin around itself. Finally, you are alone, and now you can relax. Enjoy the untouched cosmic landscape, and find out how to get to know gravity better than anyone before. While you ponder, the asteroid you are standing on stops moving forward. Its trajectory has just changed toward a dark, frozen world, a planet without a star, wandering amidst nothing in a futile search for a shining new home. In other words, danger would indeed be imminent. You notice at that moment, as the asteroid dives down toward the planet, feeling everything inside you tighten into a knot, and you are almost certain that it has chosen the perfect course for collision to flatten you against the surface of the cold. Dead world, you have heard that when faced with imminent death, people typically recall long-forgotten memories or see their lives flash before their eyes. But nothing like that happens to you. You cannot think of anything except your great-aunt's face, blaming her for your impending death awaiting your body. In a heroic effort to save your life, you push off hard, leap from the asteroid, and try to swim away from the planet. Immediately after such an act, you realize two things. First, contrary to what you thought, you are not on a trajectory leading to a collision. And second, while it is possible to jump off an asteroid, you cannot swim in the vacuum of space. Like on interstellar roller coasters, you accelerate faster and faster, sliding down the slope created by the fabric of the universe. As expected, you ultimately do not reach its surface, which lies several thousand miles away, and, turning right on that dark, cold surface, like a slingshot, you are propelled back into space along with your asteroid, traveling at a much greater speed than before the fall. You and the asteroid have just effectively stolen some amount of kinetic energy from this world, akin to a golf ball that, having missed a treacherous hole, spins around its edge before unexpectedly rolling away faster than when you putted it from a stationary position. Such a thing cannot happen with a stationary world, but it is quite possible with a moving one. A few minutes later, the dead planet disappears in the distance, and you land back on the surface of your asteroid. Strangely, you realize that it never stopped attracting you, and, even more oddly, you notice that you both followed a very similar path around the now vanished world. That a vase weighing 1/40th of your weight should fall onto the asteroid may be surprising, but that an asteroid the size of a small mountain should fall along with you to that same planet is frustrating. Nevertheless, that is exactly what happened. It seems that all objects fall onto a planet or each other in an identical manner, regardless of mass. Curiously enough, light and a feather will fall in exactly the same way concerning the asteroid, planet, or anything else. This occurs because susceptibility to gravity means traveling down the slopes created by the matter and energy of the fabric of the universe. It is quite clear that you sit on the surface of the asteroid to let this thought take shape. You look into space, but no meaningful ideas come to mind. Nevertheless, you continue to try, and ultimately, your persistence is richly rewarded. Suddenly, an extraordinarily beautiful picture arises in your mind. You begin to see curved slopes and parabolas everywhere around the asteroid, in distant planets, stars, and galaxies. Rays of light coming from far-off bright sources seem to glide along these slopes, leaving behind fading fluorescent lines so that, upon seeing them, you can imagine the real image of the canvas of the universe. You notice that neither matter, nor you, nor light and space move in straight lines, as one might think near galaxies, stars, planets, or even a small asteroid. Light bends. The greater the density of an object, the closer a ray passes by it, the more pronounced the curve. As they move, planets and stars, galaxies also create curved slopes, following which they dance around each other. Everything merges everywhere in our universe. Even its fabric seems alive. Observing this picture while sitting on the asteroid, you slide down the curve just as you are now, listening to this book. On the asteroid, the curve is created by its weight. In your case, listening to this book, it is the Earth. The curve of the asteroid is gentle, and it does not require much energy to leave it. The curve of the Earth is much steeper. If you do not have the impression of falling while listening, it is only because the earth beneath your feet or the chair you are sitting on prevents you from feeling it. But you probably feel that something is pressing down on your shoulders, indeed, on your entire body, all the time. Although if you were listening to these lines while jumping out of a plane without a parachute, you would indeed be falling down the curve created by the earth, even though the presence of air would slow your fall. Such a fall, the folds of the fabric of the universe, is the most natural motion for all objects within it. When you first pushed away the ugly vase, it slowly climbed up the invisible slope created by your presence, and then rolled back down. Just like any object thrown upward on the surface of the earth, it gradually slows down and then accelerates as it falls down. To push it into space, an object must be shot from the surface of the earth straight up at a speed greater than 40,320 kilometers per hour. If the speed is less, it will fall back down. Thus, To escape your gravitational pull, one should not confuse it with your attractiveness. A minimum speed is also required, the same as if you tried to toss a child's ball into a hole in the ground. You did not push the vase hard enough, and it returned because you also shot into the fabric of the universe. Then, when you raced toward the dead planet and pushed hard, using its own motion, you were unwittingly employing the technology that rocket scientists use to send fuel-less satellites far into the solar system. By positioning a craft near planets at the right angle and at the correctly chosen distance, they can make them jump with increased speed toward the distant regions of our cosmic neighborhood. But if your mind is flooded, you now create the understanding that even on Earth, everything and everyone is indeed falling down the slope created by the matter of our planet, and that this happens because it consists of layers, starting from the upper layers of the atmosphere and ending with the inner core, with the least dense particles on top and the densest buried deep inside. It took billions of years to achieve such equilibrium. Now, whether you create this or not, you have completely rid yourself of the notion that attraction is a force. Rather, you perceive it as a landscape of curves, parabolas, and slopes. And it seems you had a lesson for which you had to go into space, because as soon as you think about it, you find yourself back at your villa, lying in bed and looking at a somewhat cottage-like distant cousin. Didn't she just hand you the vase? She wonders, not seeing the trinket in your hands. Dear, I didn't pay attention, but what are you doing here? You ask. I was called. Your friend said you were having hallucinations about gravity. When you reach my age, you will understand that its force is a heavy burden. But you are young and shouldn't worry too much. And now, look at aren't they beautiful? Gravitational forces do not exist. There are only slopes. You respond rather gloomily, silently cursing your traitorous friends. Ah, slopes. Yes, I know, she suddenly says, unpacking you. And to your great surprise, she even floats. For from the perspective of gravity, the concept of force, slope, or anything else never made any difference to her. Don't we usually hear cries of, "Help, I'm falling," instead of, "Help, I'm being attracted"? It's foolish to make a fuss over such a ridiculous matter. And then she begins to decorate your villa, which has since been tastefully arranged, brought down south by you, while you silently observe her, thinking to yourself that life is indeed a cruel thing. That same night, when you finally manage to escape for some time alone, you abandon the relative civility of the villa in favor of taking a walk on the beach and looking at the stars. Your cousin's comment about gravity does not leave you in peace, and you try to sum up everything you have just learned. In the fabric of the universe, there are inclined folds. Everything creates a slope in any direction, an invisible slope that we call gravity, and the denser the object creating it, the steeper the slope. But if all large objects warp the fabric of the universe, then light must do the same, you think, because energy equals mass times the speed of light squared, according to the formula E equals mc squared. But is that really the case? Does everything indeed warp this fabric, including light? And what the heck is it made of? Have you ever felt it at your villa or anywhere else? Have you ever felt the invisible slope created by a wall, a couch, a ceiling, or the sky, or the light emanating from a lamp? No, you have not felt it. You have only experienced what was created by our planet entirely. Muscles and bones struggle with the necessity of getting up in the morning. If you were made of nothing but water, you would spill out, spreading across the floor or the wall. In reality, regardless of the gravity you feel right now, it is actually the sum of all the slopes created by everything around you, including the walls, ceiling, and even birds or planes flying high above your head. But everything beneath you right now is far more significant than what lies above you. The earth beneath your feet contains more matter, hidden energy, than the sky above, thus creating a steeper slope. Therefore, you slide down faster, feeling the gravity of the earth more strongly. And what about the fabric of the universe? What is this fabric and what bends it? In fact, it is so simple that Einstein discovered it through E equals mc squared. He proved that the distinction between mass and energy is superfluous, that mass and energy are merely two aspects of the same thing. This happened in 1905. In 1915, Einstein showed that the contours of the universe at any point are defined by the mass and energy present within it. Along the way, he rid himself of the idea that gravity is a force. Gravity is merely geometry, curved slopes created by matter and energy. But geometry of what? Clearly, there is no such thing as a cosmic stretching, soap-covered, rubberized fabric through which everything moves. But remember, just because we do not see something does not mean it does not exist. Before humanity understood that the invisible air around us consists of atoms and molecules, everyone thought there was nothing in it. Here lies the same kind of conceptual divergence in perspectives. Outer space, despite its apparent emptiness, is neither empty nor static. What makes it a moving and changing geometric object is precisely what I have been calling the fabric of the universe. Einstein discovered that this fabric is a mixture of space and time, two quantities that, as we have understood over the past century, cannot be separated. The fabric of the universe is now more commonly known as space-time, or the space-time continuum. Einstein's general theory of relativity describes how this space-time is warped, what it contains, whether energy and matter on one side and space-time geometry on the other are identical concepts concerning gravity. However, so far, you have only experienced the warping of space, but not time. At least you think so. In reality, the warping of time has always been occurring. It is happening right now as you listen to this. The effect is too weak to be perceived by the senses, but soon you will find yourself in places where the warping of time will be evident. This will happen in a rather convoluted way on a plane in the third part, and then when you eventually dive into a black hole in the sixth part. But for now, you are back on your beach, gazing at the stars. It is already late, but you do not mind. You look at the sky, and of course, surrender to the wonderful ideas that seem completely crazy, but for some miraculous reason, describe our cosmic reality quite well. Due to the warping of our planet's space-time, everything that comes close falls toward its surface, amplifying the warping. As a result, for many billions of years, since the Earth was born from a cloud of cosmic dust, equilibrium has been achieved. Our planet has gained an atmosphere that protects us from the airless void of space, allowing us to exist by breathing air and giving us the opportunity to look at the sky from time to time. Beyond the atmosphere, far from the Earth, lies the moon, orbiting our planet like a marble in a bowl, with the only difference being that the moon itself also creates a warp in the space-time continuum. The warping of space-time by the moon causes the water on the surface of the Earth to fall toward the moon. That is why the water follows the moon as it orbits our world, creating tides. Then there is the sun, with its steep space-time slope, down which everything slides and rotates at different speeds and at different heights. All the planets, comets, and asteroids of the solar system are like marbles rolling along the walls of the aforementioned bowl. And there is also competition with neighboring stars. Further out, the warping of space-time by other stars becomes more pronounced than that of the sun, and distant comets near the edges of their influence can sometimes reach the top of a parabola and transition from one star's realm to another, just as a marble thrown from one bowl can end up in another nearby. And in space, there is always something nearby, and all the warping of space-time by all the stars in the Milky Way galaxy combines, creating a gravitational field of the galaxy that competes with neighboring galaxies. And then the local group itself competes with the overall warping from other groups, and so on. Einstein devised a way to unify all this into a single formula. Good job, Einstein. You almost wish he would appear before you now so you could shake his hand. But you cannot shake the feeling that there is still something deeper to uncover. But didn't you read that Einstein opened the door to theories that our universe may have a history, to the idea that the universe was once smaller? You sit on the beach, focusing, closing your eyes, preparing to imagine what that might have been. Chapter 7. Cosmology. In life, there are some questions that can only be answered definitively. Unfortunately, despite what you have just seen, there is no unequivocal answer to what the universe looks like as a whole. Einstein's equation allows for many different global forms of the universe, and as you will see in the 6th part, we still do not know exactly what it is made of. That said, it is worth reminding that physics, no matter how powerful it has become now, never reflects reality with absolute precision. It does not even strive for such a goal, as that would imply that reality, whatever it may be, can be known absolutely. Observation and experimentation, despite their accuracy, always yield approximate answers. There is a probability of error, even the most negligible. Moreover, looking back, we know that throughout human history, the technologies through which we, humans, have mastered nature rarely match the level of possible predictions of physics at the time, sometimes leading to false beliefs. If a couple of centuries ago, your predecessor somehow managed to learn about the existence of certain bacteria, the size of which does not exceed 1,000th the thickness of a human hair, none of his contemporaries would have been able to verify it, so the scientist might have had to spend the rest of his days in a madhouse for his outrageous claims and scaring people. The same applies to distant galaxies. If your ancestor had insisted on their existence, he would not have been taken anywhere. He would simply have been burned alive like Giordano Bruno. The necessary technologies to look far enough into space and conceive of its theory did not exist even 100 years ago. Similarly, there are still no technologies available to verify and describe the theories I have outlined at the end of this book. As they say, science sometimes progresses by leaps and bounds, paving the way for revolutions in understanding. Nevertheless, it may be a sound position to view science as scaffolding for thoughts, attempting generation after generation to get as close to the reality in which we live, a reality whose mysteries are then unveiled through experimentation. And it is worth noting that even if something changes in the future, so far, human activity and science have never led to discoveries in nature that were not clearly visible. At the same time, it is necessary to humbly bow before the magnificence of the nature of science, for only science has given us the eyes to see how blind our bodies were. So, what has Einstein's vision given us that was absent before? If his equation is too complex to solve, what good is it if we do not even know what the universe is made of? How can we use it? Contrary to what most people believe, scientists do not like complexities. They prefer everything to be simple, and the essence usually lies in finding a simple pattern for what seems to be a complex system. And this is where ingenuity comes to the rescue. So, let us see what we can derive from Einstein's theory by simplifying everything observed to the largest possible scales. Let us forget the details and look at the big picture. There are no asteroids, no planets, no stars. They are too small for what matters here. Let us leave only galaxies, or even clusters of galaxies in place, and you can see everything with a cosmic long-distance eye in such proportions that the Earth, the Sun, and the hundreds of billions of stars that make up the Milky Way will be just a dot marking your location. The other galaxies are evenly distributed around, even if their filamentous structures are visible. Good, that's simple. This is the initial setup. Plug it into Einstein's equation and see if anything comes out in the end. And you wait, anxiously, not daring to expect too much. And then, oh miracle, it works wherever you look. The galaxies and clusters of galaxies move around each other in the expected manner. But that's not all. The surrounding universe, as seen from Earth, begins to expand. Space-time stretches between all galactic points, causing them to drift apart regardless of how they moved around each other. Whatever their motion on a small local scale, they now resemble poppy seeds in a pastry or dots on the surface of an inflating balloon. The farther they are from Earth, the faster they drift apart. This is precisely what your friends saw in their telescopes worth £1 billion. This expansion of the universe, substituting Einstein's controls, a simple model of the visible universe, gives you what was unthinkable before Einstein. At any moment in human history, something corresponding to what you see out there in the sky is what scientists see every day. The universe can evolve according to Einstein, and does evolve according to observations. From such a thought emerges cosmology, the science of uncovering the past and future history of the universe. Before Einstein, there was only cosmogony, the stories we told ourselves to avoid going mad from the mysterious origins of our reality. Now, we also have science, the means to decipher the history written by humans and nature. Watching all the surrounding points unfold, you suddenly realize that with Einstein's equations, you can indeed press the rewind button in your mind, making the expansion roll backward, and you press it. Instead of growing, the poppy pastry of the visible universe immediately begins to deflate. Your cosmic eye sees it shrink. The distant past now moves toward the present, toward you, absorbing images of the future. The entire sphere enclosing the visible universe of Earth compresses, shrinks even more, compresses, until. About 100 years ago, Belgian physicist and Jesuit priest Georges Lemaitre decided to implement 3 cosmological principles: a simple, functioning universe, like an imaginary clockwork mechanism, to observe its expansion and contraction. His conclusion was simple. It appears that our reality, that very reality perceived by humans as something self-evident since they learned to think, had a beginning. Einstein's equations quickly led Lemaitre, and subsequently many other scientists, to the very convoluted idea that the universe, although it always contained the same energy as it does now, once had no size at all, neither size in space nor in time. The idea certainly sounds absurd, and perhaps still does, but it was what Einstein's equations were talking about. Of everything we know today, it seems, however, to be the best idea humanity has come up with to understand what we see in the night sky. The theory asserts that everything contained in the visible universe once had zero or very close to zero dimensions at some stage of its past, which is called the Big Bang theory. The theory of the hot universe, a hot universe because only a very hot past can compress all the energy of the visible universe into tiny volumes. The heart of the sun is heated to the point where all the matter contained within it is crushed by its own gravity. Compressing the entire visible universe to the size of the sun gives you yet another level of a hot universe. Big, because the explosion involves the entire visible universe. And finally, explosion, because the subsequent expansions make it resemble an explosion in our past. Immediately after the birth of the universe, although later you will see that it was not an explosion at all. Incredibly stunning, mind-boggling, beyond scorching heat, hot, colossal, ubiquitous universal flashes. Such words would describe what happened then much better. But Big Bang is also a sufficiently dramatic name, and it should be modest, for even if your cosmic eye may perceive that everything related to the Big Bang is concentrated on our planet Earth, that is not the case. As you now see, the Big Bang did not occur at any specific point in space-time, but everywhere. Chapter 8. Beyond the Cosmic Horizon. When you lay on the beach at the very beginning of your journey, you wondered whether what was visible in the sky to the naked eye was the entire universe. Now you know that it is not. Our eyes allow us to detect only a few hundred stars, all of which belong to our Milky Way galaxy, as well as some faint traces for those who know where to look. Not many other nearby galaxies. Using telescopes and other powerful instruments, you now know that the entire observable universe is immeasurably larger than what is visible to the naked eye. But it also has a limit, the surface of last scattering. This surface lies in our past, about 13.8 billion years ago, but it also lies in space, 13.8 billion light years away from here. It limits what we can see today. Any light coming from a more distant source would have taken more than 13.8 billion years to reach us. But more than 13.8 billion years ago, light could not travel freely. It was trapped. The entire universe was then too dense. Light could only move freely through space and time about 13.8 billion years ago. And the surface of last scattering is the imprint that preserved that moment. Viewed from there, it marks the beginning of transparent space-time. Observed from Earth, it outlines the edges of the visible universe. In a sense, this surface is our cosmic horizon. We cannot see beyond it, at least not from Earth. At the very beginning of the book, you traveled through the universe from the perspective of Earth. You always limited yourself to the visible universe, the universe within our cosmic horizon, a horizon reduced to windows. But what about the universe, visible from somewhere else, from another place, but not from Earth? Would there still be a cosmic horizon centered on Earth? Imagine yourself on a raft in the middle of the ocean, far from land. the horizon is clearly visible. This line separates water from sky. Looking around, you can see it forms a circle with you at the center. Does this mean you are in the center of the ocean? Of course not. It means you are at the center of the part of the ocean you can see. Your visible ocean does not exist. There is no way to look beyond its edges, beyond your horizon. But that does not mean there is nothing beyond it. There is, of course, your friend on another raft some distance away, who will also see his surrounding horizon, his horizon limiting his visible ocean. If your friend is close enough, he might be within your visible reach. Consequently, your visible oceans will have some common waves, but he would be able to see in some directions beyond your horizon, just as you, in turn, could. But he might also have originally been beyond your horizon. In that case, you could also have a shared part of your visible oceans without being aware of each other's existence. The third possibility is that your friend is originally so far away that his and your visible oceans have nothing in common. If you look down on you from above, it would mean that the circles defining each field of vision do not intersect. Everything he could see would be completely hidden from you. He might notice a few volcanic islands and whales, but you would know nothing about it. The same happens in space. The universe visible from Earth is a sphere with a radius of 13.8 billion light-years, but that does not mean there is nothing beyond it. Someone else on another planet will be surrounded by their own cosmic horizon with the same radius of 13.8 billion light-years, because there is no reason for the universe to be younger or older there than here. The three cosmological principles you are already familiar with illustrate the following. The visible universe is so remote that it has no common visible part with our own, which seems similar, but not identical, universe, yet it obeys the same physical laws. Even if your friend's fruit is too far away for you to see, you do not expect to find flying mountains in his visible ocean. The same goes for cosmic space. The laws of nature should be the same everywhere, and no particular location should differ in this regard from any other. Hence, it follows that the visible universe, as seen by any, those living throughout our universe beyond visible existence, must also be expanding, obeying Einstein's equation. This means that if they were to rewind time, they would find the same Big Bang there. The Big Bang would be centered on them this time, not on us. With such a vision of our entire universe, the concept of a center of everything does not exist at all, and the Big Bang occurred everywhere. By sharing such a view, you enter into the taste of what is called the multiverse, consisting of many isolated universes that cannot communicate with each other, although all belong to a single whole. By the end of the book, you will explore 4 different versions of such multiverses. This is the first scenario I will present first, because most scientists consider it to be true. Now, if we accept it, isn't it true that the entire universe is the result of all the visible universes being combined together? Infinitely? No. For example, the entire ocean is derived from an ocean made up of all visible oceans, from any number of oceanic fruits you like. Of course, it turns out that the entire universe, well, no. It may very well be infinite. We don't know how. As I mentioned at the beginning of the previous chapter, Einstein's equations, unfortunately, do not provide us with answers to this question. Great. So what then? Is it proven? Do you think it's not much, or even nothing? Perhaps even the Big Bang Theory may seem unfounded to you, just an abstract thought. Well, it is indeed true that what your friends see in the sky, distant galaxies moving away from us faster and faster, simply indicates that the universe is currently expanding. Many possible past scenarios could have led to such expansion. There is no need to invent some Big Bang. Yes, one could argue that it is indeed the case, but not for long. Science is not politics. Nature does not care much about opinions, even if your opinion is the opinion of the majority. Rigid, experiment-based evidence is always necessary. And as we will now see, there is indeed some evidence of the existence of the Big Bang lying in our past, hints that are so convincing that some people go so far as to consider them proof. Chapter 9. Irrefutable Evidence of the Big Bang. If our universe, let's not get distracted by the word visible. If it were smaller in the past, how could you prove that? Time travel is one option, but you can look into the past. By now, you should be accustomed to the idea that by collecting light from stars shining billions of light years away from us, you see them as they were billions of years ago. You are looking into the past. Thus, one can check whether the universe was smaller then, or look for a movie of us. This effect is due to the light traveling to us. However, it is not always easy to understand exactly what is visible in the distant corners of the universe. So far, the best way has been to obtain an accurate picture of what is expected and then check whether it corresponds to reality. This is precisely what theoretical physicists do, at least what they should sometimes do. But now, let's see what conclusion can be drawn. Before examining anything through a telescope, you are back on the beach of a tropical island. It is deep night, but instead of gazing at the stars, you have twice made sure that no one is around and begin to speak aloud to yourself to construct a picture of the history of the universe in your mind. If the universe is expanding, then in the past it must have been smaller. Okay, but if that is so, then gravity, or the curvature of space-time, would have been much more pronounced, as all the matter and energy of the universe were contained in a smaller volume. And this is exactly what Einstein's equations talk about one way or another. Excellent. Then space-time began to grow, because for some reasons, expansion occurred. It started with a small, very densely packed volume of matter and energy, transforming over 13.5 billion years of expansion into what exists now, with Earth-like planets and stars similar to those we can see above the island. If the picture depicting the universe is small, is it true that the universe was densely packed with mass or energy? In fact, it does not matter, as mass and energy equally affect the geometry of space-time. This was also claimed by Einstein. If all the energy was contained in a tiny volume, then of course, there was strong friction. A lot of other things were happening, so the young universe was apparently very hot. Sounds convincing, yes, and for the first time, you come to such a conclusion. But then, perhaps, you can draw other conclusions. How about this? The universe could have been so dense that no beam of light from the outside could pass through it at that time. No beam of light could pass through it. It sounds like a wall. Exactly. You are right. Great job. Such a place must have existed at some point in the past of the universe. If the expansion model is correct from beginning to end, and it indeed exists, you have seen its surface. This surface of the last stretch is the surface that limits what can be seen in our universe. What you have just done is quite unusual. You have just been, in a physicist's dream. Based on pure logic, using Einstein's equations, having seen the universe after leaving your beach, you have figured out that somewhere in our past there must exist an impenetrable wall for light. This surface should still be visible, and in fact, this surface has been discovered as a result of experiments and mapping. As you will now see, I understand that while listening to these lines, you cannot help but feel that you have just revolutionized our vision of the universe. But that is because you were shown the wall before you thought of it. You did not spend over 20 years of your life trying to prove its existence long before it was discovered. Nevertheless, the scientists who discovered the wall were incredibly astonished by its existence and how they found it. Wandering thoughtfully along the beach, you realize that there is a problem. The surface you saw at the edge of today's visible universe is not quite the one you just thought of, is it? The reality is that what we can observe through telescopes is very cold, while this wall that has surfaced in your mind was very hot. How hot? Using Einstein's equations, some scientists have already calculated the expected temperature. In the end, a rather impressive figure emerged, around 3,000 degrees Celsius. They found that as the universe became transparent, it had the same temperature as the wall you saw in the sky. And that is a problem. But did you forget something? By concluding the very existence of a hot past, are you not allowing for the expansion of space-time? That the visible volume of the universe has grown over time and has grown to the sizes observed by your friends in the sky? And could this expansion not have affected the temperature of the universe? Well, yes, it not only could, but must have. That actually changes everything. Take the oven in your kitchen, heat it up so that the air inside becomes pleasantly warm, then turn it off. Imagine that the oven begins to grow rapidly, reaching the size of a house. The temperature inside it will instantly become significantly lower than at normal sizes. Calculations were made back in 1948 by American scientists George Gamow, Ralph Alpher, and Robert Herman. They showed that after the expansion of the universe from the mentioned 3,000 degrees Celsius, only a faint trace should remain and fill the entire visible universe with thermal radiation, as if emanating from the surface of your wall. What temperature did the scientists expect to find? Somewhere around minus 260 or minus 270 degrees Celsius, or somewhere between 3 and 13 degrees Kelvin above absolute zero. And it so happened that in 1965, 17 years after Gamow's calculations, his colleagues, two American physicists, Arno Penzias and Robert Wilson, were conducting unusual work for American companies in a laboratory. They needed to adjust an antenna to receive radio waves reflected from a satellite balloon. A pleasant light task, if it weren't for a rather strange obstacle: the annoying noise heard at all frequencies. To get rid of it and earn their fee, they conducted several brilliant checks and searches for potential engineering faults, but nothing helped. No matter what they did, the noise did not disappear. Eventually, finding no other causes for the problem, they blamed the pigeons or other passing birds that had nested on their state-of-the-art antenna. Despite the impressive scientific achievement, they went even further, spending a long time cleaning their device and cursing the existence of birds. But the noise did not go away, and it ended up with them calling their physicist friends. Shortly after their visit, they realized that they could try to get rid of this noise forever without the slightest chance of success. What they heard was not due to the presence of birds. The noise did not even come from Earth. It was a signal, a temperature signal, a signal of minus 270.42 degrees Celsius, and it came from space, from everywhere. Gamow, Alpher, and Hermann predicted it. It was a remnant of Einstein's equation. It was the residual temperature from the last impenetrable moment of our universe, a still frame taken 13.5 billion years ago, when the much smaller universe was so densely packed with matter and energy that light could not yet pass through it. Penzias and Wilson experimentally confirmed the calculations of a theory that seemed so absurd to some scientists that even its name, the Big Bang Theory, was coined by one of the most famous professors of that time, the British Fred Hoyle from Cambridge University, just to make you laugh. In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics. They discovered the residual heat. Melted long ago in the furnace of our universe, heat radiated from the surface of the last stretch, the surface that limits the end of the visible universe. This radiation is one of the irrefutable evidences of the hot Big Bang, known as relic radiation, or cosmic microwave background radiation. Penzias and Wilson proved that the Big Bang Theory was on the right track. However, why is this radiation called microwave? This is again related to the expansion of the universe. The light emitted during the last stretch, when the universe became transparent, was actually very noticeable, including various colors of energy and purity. But it is no longer perceived as such by our eyes. The light stretched. Remember that the color and energy of light waves depend on the distance between two consecutive peaks. Over 13.5 billion years, light, having begun to stretch due to the expansion of space-time, gradually transformed from indigo to blue, green, yellow, orange, red, and then became invisible to the eye, turning into infrared radiation, then microwaves, and finally radio waves. Today, we are at the stage of microwaves. What was once perceived as hot visible light has now, after 13.5 billion years of expansion, become cold microwave radiation at a temperature of minus 270.42 degrees Celsius. When you realize this, the Big Bang Theory stops being amusing. But what did the data of this theory imply? Perhaps they suggest that the universe was created at the surface of the last stretch? No. In the last chapter, you were convinced that the surface observed from Earth at the end of the visible universe means nothing to observers within it, Earth. They have their own surface. And now, what about us? If the universe was not created there, then something must be found beyond the wall that we could discover there. This is known as the Big Bang. Well, in a sense, yes, the Big Bang is beyond the surface, but not directly behind it. It happened 380,000 years before the universe became transparent. What lies behind or beyond the surface of the last stretch and later became our visible universe can be described as a soup of matter, light, and energy, and curvatures that become denser and hotter. And soon, you will be ready to go there and see everything with your own eyes. But for now, let's just say that the further you move away from the wall and the deep past of the universe, the more extreme everything becomes. Going too far beyond its limits, you will ultimately find yourself surrounded by the lost. This meaning of nothing, even space and time, eventually curve so much that the equations of the wall collapse, ceasing to track what is happening. When this happens, theoretical physicists reach a point where nothing more can be told, nothing at all. This moment can be considered the birth of the space and time we know. By definition, which we will use throughout the book, it lies beyond the Big Bang. Reaching this place and figuring out what the Big Bang is will be your mission in the fifth part. During the last journey, you will go even further back to the very origin of space and time. Why not go there right now? Because you will need a few seconds to catch your breath and congratulate yourself. You have come a long way since you first landed on the moon. You have learned many facts about the universe that your ancestors could not even imagine. You have learned that the fabric of the universe is a mixture of space and time called space-time, and that it not only takes the shape of what is within it, but also evolves according to its geometry and content. You have learned that the universe is vast by any measure, much larger than we can see, and that we do not know its shape or size. Moreover, our visible reality is also quite spacious, but it has not always been so. You have learned that the universe has a history, that it likely began around 13.5 billion years ago, hidden behind an impenetrable surface. And you have learned that it is still expanding, growing larger with each passing minute. And you should be proud that you have understood all this. So why not head straight to the beginning of the universe? A good reason for the journey might be that, first and foremost, it is necessary to try to figure out what the universe contains. Without such knowledge, there is no chance of ever unraveling its most hidden secrets, neither about its possible origin nor its possible fate. Well, let's exclaim. You open your eyes. A gentle night breeze over the ocean. A full moon. The round surface of the moon reflects the sunlight, bathing your island in silver light and shadow. A few turtles timidly emerge from the water to spend the night on the sand and perhaps lay eggs. If the day goes well, you feel amazing. I will soon return to treating the stars, but you are no longer alone. You heard a whisper behind you. You turn around only to see friends discussing the situation with your cousin. Hearing your conversation with yourself on the beach all night, they decided to move your departure date and find the earliest flight home. The plane departs in a couple of hours, and you need to hurry to pack. Get some rest, they say. All your cries, complaints, philosophical musings, and speeches about freedom have no effect on them. You are being sent home, and now, as sad as it is to leave the sea, the birds, the sweet scent of the wind, let me say this: the journey through modern scientific knowledge is just beginning. Part 3. In the World of Superspeeds. Chapter 1. Packing for the Journey. Our senses are adapted not to our scales, the size of our bodies, for survival here on Earth. Eyes are meant to judge whether a fruit is ripe enough to eat, ears to hear dangers, and skin to feel cold and ice and the warmth of fire. The senses allow us to see, smell, touch objects, taste them, and hear the environment. This world is the reality of which we are a part. But this reality is not the whole picture. We are quite small compared to our planet, and the Earth itself is not so large compared to the cosmos as you have seen during your travels through the universe. Therefore, it would be quite strange if, instead of surviving on a modest little planet, our bodies evolved super capabilities of the senses, capable of registering all known and unknown signals throughout the cosmos. In the everyday life of Earthlings throughout human history, there has simply been no need for organisms to grasp the mysteries of the subatomic world, the speed of light, and the full spectrum of radiation from microwaves to X-rays. In fact, we cannot even distinguish between two extremely high or low temperatures. They would burn or freeze our fingers even before we start to judge the details. For survival, it is much more important to pull your hand out of the fire in time or protect it from the cold. We can taste the slight acidity of a lemon to determine if it is edible, but we cannot detect the difference in the alkaline reaction of sulfuric or hydrochloric acid. They would burn through our tongues. Similarly, our bodies do not feel the curvature of space-time beyond their own and through the gravitational effect. Everything we need to know for everyday life is to safely remain on the surface of our planet. Thus, the world perceived through the senses is limited by its very nature. Our senses are windows into it, but they are merely tiny portholes looking into an endless sea of darkness. And for millions of years, the intuition of what we confidently call our reality could rely on nothing but them. But that is no longer the case. Now we can go beyond the senses, and their reality changes. In the first two parts of this book, you travel deep into existence, crossing intergalactic voids, and even briefly familiarizing yourself with how vast the universe is. You discovered that Newton's opinion on the universality of gravity is actually incorrect. Gravity, as Einstein claimed, is a result of the curvature of space-time. It is not a force. Newton taught us how to use words and equations to describe and predict the behavior of the world discovered through the senses. Einstein, with his general theory of relativity, took you beyond their limits, and following him allowed you not animal instincts, but your brain. Using it, you uncovered a law that unites space-time, matter, and energy in a theory of gravity. This became your first step beyond. Now, you are about to visit two different realms beyond, as if you are an adventurer wandering through newly discovered territories where nothing is yet familiar and cannot be taken for granted, not even the laws of nature. The first of these two realms is the world of superspeeds, and the second is the most inhabited of them, the micro-world. At first glance, and all subsequent ones, they will undoubtedly seem quite unusual. I guarantee that your sense of common sense will scream that everything you encounter here is simply a mistake. But remember, all the matter of your body is made from what belongs to these exotic worlds. The fact is, you are made of realities for which the rules of nature differ greatly from those we are used to feeling while lying in a lounge chair on a tropical beach. Only through a very strange mechanism does the reality we perceive day by day seem as it is. Chapter 2. An Unusual Dream. Your seat is 13, and next to you on that plane are 73 passengers. Everyone looks normal, except for your neighbor. He seems quite strange. You try not to look at him and almost regret asking for a seat far from your cousin. You have been on board for just a few minutes, but you are the last passenger, and the plane is already ready for takeoff. Your vacation companions wave goodbye to you with obvious relief, and you inhale a sigh, no matter how creepy it feels. But traveling through the universe was fun. Thoughts of returning home right now do not bring excitement. Drifting, gaining the necessary power, the winged machine soars into the sky, up the slope of space-time created by our planet. Being there, you feel compressed in your seat and thus feel heavier than usual. Now you experience gravity just as if you were sitting not in a plane, but on the surface of another planet, where gravity is stronger than Earth's. The longing for another interstellar journey makes you close your eyes and let your imagination run wild. Your mind conjures a wonderfully unfamiliar landscape with unusual characters, lakes, and a sky with two suns. You remember that just in the last few years, humanity has discovered thousands of planets orbiting distant stars, a handful of which are potentially Earth-like. The hum of engines, the plane's incline, and the pull of sleep make you start to imagine a futuristic plane flying far away through an alien mind, illuminated by the light of double stars. In the sky, a distant voice reaches your ears. It says that the plane has reached cruising altitude and is now accelerating to an unprecedented speed of just 1/1000,000,000% less than the speed of light. After a while, the plane begins to descend. The voice of the stewardess, giving you a quick glance at the dial, says that 8 hours have passed. You stretch, dress, open the window shade, and look outside. There is only one sun. Its rays, reflecting off the morning clouds, give them a pink hue, similar to the color of an alien sky you dreamed of before falling asleep. The surface of the earth beneath the plane's wing looks nothing like you expected. An endless ocean stretches to the horizon. You should land at the airport in a minute, but all you see is a water surface. A chill runs down your spine from the bad premonition. Maybe the plane was hijacked, but the other passengers seem quite relaxed, including your cousin sitting a few rows ahead of you. Oh, strange neighbor, so the hijacking version is out. And the nets, something is not right. Maybe while you were sleeping, the entire earth was flooded? You read somewhere that about 10,000 years ago, the oceans worldwide were much deeper than today, covering most of the continents. Looking out the window, you wonder, could you have traveled back in time to wake up on a forsaken land inhabited by long-gone animals? The thought makes you smile, but you cannot shake the unpleasant feeling that something is not right. It seems you have slept for approximately 8 hours of flight. During that time, anything could have happened to you or the plane. Throughout your life, like everyone else, you have gotten used to waking up where you fell asleep in most cases. Now imagine that you have never gone to sleep before, and for the first time in your life dozed off, waking up in a place where you will undoubtedly be quite confused and first check where you are and what time it is, as in a panic some of us still do when waking up not at home. In fact, whether at home or not, most of us, upon opening our eyes in the morning, automatically check the time. And only in quite rare cases, after a particularly successful party, for example, do we also check the place. However, waking up where you fell asleep has never happened to anyone. While you sleep, the Earth does not stop moving. Every hour it travels just over 800,000 kilometers around the center of our galaxy, or you along with it. This corresponds to about 20 circumnavigations of our planet every hour. Nevertheless, no one cares, as long as the bed remains stationary under the weight of your body. But if the Earth, or you, were traveling through time, everything would be different. But that is impossible. Time travel does not exist. As you gaze out the window at a vast city amidst the ocean, you realize you are about to land. No one is carrying the Earth from which you flew on vacation. Your panic in trying to get up from your seat is quite understandable, but the seatbelt pulls you down, and the sound of roaring engines drowns out your screams. In despair, you can see the steward disapprovingly looking at you and urging you to calm down, until he reaches for the microphone to remind everyone that any violation of flight rules during takeoff and landing in 2014 is still punishable by law. You open your eyes wide. What year did he say? Seconds later, the plane lands, beginning to glide along the alleys of glass skyscrapers, the style of architecture of which is unfamiliar to you. Helplessly staring out the window, you again hear the stewardess's voice, in the even dictatorial tone commonly used by passenger airplane crews, congratulating you on your return home. June 4th, 2014. 4 centuries after your departure, 3 days before the scheduled arrival. Local time is 10:25, with morning fog expected to clear soon. During the day, it will be sunny at times. The temperature outside is 10 degrees above the average temperature of the early 21st century. Thank you for choosing McFly Airlines, a member of the Heavenly Alliance of the Future. 2014. You look at your smartphone screen. No network, as usual. I communicate if they still work. And it seems you flew for only 8 hours, not 400 years. Something is definitely wrong. Maybe it's some kind of prank? Maybe your friends planned all this. You check your plane ticket. It's a regular return ticket. Maybe they slipped you drugs. Or worse, is all this happening for real? I wonder if a collector is waiting for you at the airport to collect a debt for 400 years of unpaid rent? And what about the girl you recently agreed to go on a date with? And what about the milk left in the fridge? Important practical questions flash through your mind at an unimaginable speed, making you dizzy. 400 years into the future. And in whose future exactly? Certainly not yours. Your joints, as your body seems not to have aged at all over the 8 hours since takeoff. And what about your friend's future? The city you just landed in definitely does not look like a metropolis or a city from your century. Time outside seems to have truly moved forward while you were sleeping on the plane. But wait, how can time outside the plane race forward in fast-forward mode and not change inside? It sounds absurd, but it seems to be true. In fact, it is true, and the blame lies with the exceptional speed of your plane. Chapter 3. Individual time. Speed changes everything, even space and time, including those moving through space at very high speeds, flowing not at the same rate as the neatly fastened watch on your wrist. During a stroll on a tropical beach, the idea of universal time, of some divine clocks beyond our universe that measure the movements of everything in it, the evolution of development, the age of the universe, and everything else, does not exist. What just happened to you on the plane vividly illustrates this. The time we perceive, as humans, seems the same for everyone, universal, but we perceive it as such only in comparison to light. None of us, not even military fighter pilots, move significantly faster or slower than the others. This is an extremely fortunate coincidence for watchmakers, but despite our senses being unable to perceive it, the fact remains. If every person, animal, and object on the surface of our planet had their own clocks, the time displayed on each clock would differ. We all have our own time, uniquely tied to us. Einstein figured this out 10 years before publishing his theory of gravity. In the general theory of relativity, which you were introduced to in the previous section, he was unable to secure a position at any university because no one wanted to hire him. The 20-year-old Einstein had to make a living as a patent office clerk, or rather, as an assistant, in the Swiss city of Bern. But this did not stop him from thinking during breaks between evaluating patents. He tried to imagine the workings of a world of moving objects depending on their speed. He hoped to derive a theory of moving bodies. He was not yet obsessed with gravity, nor the universe as a whole, but rather with how objects manage to move. At the age of just 26, in 1905, he published his work, and soon the entire scientific community realized that an unknown individual had made an extraordinary claim. Due to the complexities of this, it became evident somewhere within the offices of Swiss intellectual property that clocks do not always tick synchronously. More precisely, the passage of time on a clock depends on how it has moved relative to others. Or, even better, as proposed by this unknown young man, the theory could calculate the expected actual difference in time for two travelers based on their relative speed. This theory is known as the special theory of relativity. Let's imagine twins, as usually occurs in a pair. A couple of years after Einstein's publication, French physicist Paul Langevin, using the special theory of relativity, calculated that if one of the twins were sent on a rocket for a 6-month space journey at 99.995% of the speed of light, the brother remaining on Earth would have to wait 50 years for his return. Thus, according to Einstein's theory, 6 months spent by the traveler in the rocket must be equated to 50 years lived by the stay-at-home twin. During the journey, the twin on our planet would orbit the sun 50 times. Despite being twins, they would ultimately no longer be the same age. One would be 49 years and 6 months older than the other. Quite an astonishing statement. If you heat a metal rod, it expands and becomes longer. That is, it stretches. If the goal is to direct heat, you can only stretch the rod, not, say, the anvil on which it rests, meaning its surroundings do not change. According to Einstein's special theory of relativity, a similar phenomenon occurs with time. In a rocket traveling at 99.995% of the speed of light, or in a plane moving at 99.999 millionths of the same speed, the rocket and planes, everything inside them, moves at super speeds, but not their surrounding environment. Thus, only their own individual time is affected by the extreme speed relative to the surrounding world. What the twins experienced, what you experienced while flying in a supersonic plane, scientists call time dilation. The faster someone or something moves, the more pronounced the time dilation becomes. A rather peculiar phenomenon, but Einstein's special theory of relativity also proposes something even more complex to grasp. It states that time stretches while the length of objects, conversely, contracts. Now, since you were sound asleep on the plane while all this was happening, let me take you on another journey into the realm of superspeeds. Prepare to see what our reality becomes when moving at incomprehensible speeds. So, let's forget about the plane for a moment, and even gravity. Imagine yourself on the ground in a spacesuit with a couple of rockets attached to your back, so remarkable that they never run out of fuel. You say goodbye to your current life and are ready to launch into space. Now it's time to go. And let's hope that stray meteors do not cross your path. You are not just a mind traveling through the history of the universe, but a mind and body, just as you were the last time you ventured into the empty cosmos for sheer enjoyment. We are already in space. You check your watch. It ticks, just as it always has. Seconds seem to change one after another. Whatever that means, the Earth is receding from you, but you imagine that there are enormous clocks hanging at the bottom, which you can always check, no matter where you are, counting time, say, in your great-aunt's house, telling you what year it is there. Your rockets gain power. You reach 87% of the speed of light. Seconds still calmly follow one another on the watch on your wrist, but everything around begins to feel strange. You turn to look at the clock above the Earth. While 1 second ticks on your watch, 2 seconds pass on your home planet. Remarkably, your personal aging is slowing down to half compared to all the other inhabitants of Earth. But while your perception is troubled by this, the second relentlessly continues its course. The clocks on Earth seem to be moving faster. You continue to fly. You reach 98% of the speed of light. Already 5 Earth hours pass for one of your hours. You look ahead at distant galaxies. Strangely, all those sparkling blobs of light, which seemed infinitely far away a moment ago, now appear not so unreachable, as if the galaxies have jumped towards you. More precisely, 5 jumps, which of course is impossible. You glance at the clock and speedometer, the device measuring speed, just like in a car. You are flying at 99.995% of the speed of light, the speed Langevin assigned to the rocket of one of his twins. It is not yet as high as that of the plane carrying you. Even at 99.995% of the speed of light, Earth's clocks tick 100 times faster than yours. A full day on the home planet takes you just 1 minute and 26 seconds. 1 year for you here equals 100 years there, in your great-aunt's house. And those distant galaxies ahead, galaxies that were supposed to be millions of light years away from us, how did they suddenly become so close? Of course, they cannot become that close in just a couple of hours of travel, and yet they can. 100 times closer. Their distance from you has just contracted in the same way your time has slowed down compared to Earth. Although it does not resemble the expansion of the universe at all, the expansion occurs uniformly in any chosen direction. Here, however, everything is different. It happens only in the direction of your motion and depends on you and only you. So forget about the universe. Just think about yourself and focus on what you see around you. To the right and left, it seems nothing has changed. The same happens above and below, where the distant galaxies are still in the same place they were before your acceleration began. But the galaxies ahead of you have definitely changed. If you look at them again, there is hardly any doubt that something suspicious is happening. It seems that not only time is subject to dilation, but also long distances have evidently shortened. It's a pity. It seems that this is how the entire universe looks, as if you are viewing it through a distorted magnifying glass, compressing distances ahead, but not to the sides. You check your watch. Seconds are still following one another, and you are still accelerating, and everything seems even more distorted. Your confusion and fear are quite understandable, so you make a complete turn to return to Earth, which is supposed to be extremely far away. But it turns out to be right in front of you. Looking back, you see that the galaxies you were approaching have literally returned to where they were, very far away. Regardless of the direction in which you travel at this astonishing speed, everything ahead of you, no matter how far away it is, seems very close, while the distance in other directions remains unchanged. After a few minutes, still in complete disarray, you fly past the International Space Station, orbiting the Earth at a completely insane speed. You check your watch. 1 second still passes exactly as a second. A couple of astronauts, whose movements are accelerated 100,000 times, have their watch hands spinning like crazy. You see the difference between their time and yours. Their life unfolds before you. In 10 hours on the astronaut's clock, only a tiny fraction of a second passes on yours, and he moves accordingly. The same happens with the space station, the Earth, and everything around, while your rockets continue to spew fire, carrying you past the Earth faster and faster on your way to infinity. Or, in half a second on your watch, the astronaut finds himself back on Earth. After a couple of seconds, he dies, his children grow up, and his grandchildren. Thousands of days, nights, and years fly by on Earth, and you are now too far away to see anything else. For you, just a few more seconds pass as you continue to accelerate. There is no longer any point in returning to Earth. You will land in a future so distant that you will likely feel like a fossil and will undoubtedly be considered one. The entire universe before you continues to become closer and flatter. To the sides, nothing changes. The distortion occurs only ahead, in the direction of your motion. You are still accelerating. We are getting closer and closer to the speed of light. But something is going wrong again. Although your rockets continue to rush you faster and faster through space and time, your speed has not significantly increased lately. Moreover, the energy of your rockets is turning into mass. You are sure of this. You are becoming heavier with every passing minute. Years of torturous diets are undone, and so are the rockets. Who would have thought? Stop! You shout, irritated by this more than anything else, and everything freezes. Now you are somewhere up there, far in space, likely millions of years in the future, but frozen in place, light and easy, just like the entire universe. Nothing is moving. You can relax for a moment. All right, let's contemplate 3 counterintuitive aspects of your superspeed journey together. First, time flowed differently for you and those living on Earth, including the astronaut. Why is the time so close to that of the enormous clock hanging in the sky above your great-aunt's house that they can be considered identical here? Ordinary mechanical clocks, which he and the astronaut are forcibly holding in their hands, tick at the same speed in all dreams, and the faster you flew, the more noticeable the difference became. This is the first change. Strange, I agree, but it is so. The second experience you had is that the distance to the objects ahead of you compressed. What once seemed very far away, while you were not moving quickly, became very close as soon as you started moving that way. What is also strange, I agree with you, but nevertheless, this is also a fact. It is called relativistic length contraction of a moving body or scale. And third, the fact that you are becoming heavier and heavier, which, to put it mildly, is annoying, although perhaps not as surprising as the other 2 aspects, considering that you now know energy equals mass times the speed of light squared. So let's not delay any longer and examine this special byproduct of rapid movement. Something with any mass cannot reach the speed of light, let alone exceed it. This is a law. Therefore, the faster something with mass moves, the harder it becomes to accelerate it. To understand what this means in practice, imagine yourself flying so fast that adding just 1 kilometer per hour to your speedometer would mean reaching the speed of light. Then you pull a tennis ball out of your pocket and throw it ahead of you. To be specific, let's say you throw it at 20 kilometers per hour. On Earth, this would be easy, but right now, it is impossible. Nothing can move faster than light. So, if you are flying at a speed just 1 kilometer per hour, shy of the speed of light, The ball physically could not fly 20 kilometers per hour faster. Nothing prevents you from throwing the ball. That is true. But if the ball cannot move faster than the speed of light, then it is clear that you will have to do something else to hurl it into the void ahead of you. And the answer is given by our old friend. Energy equals mass times the speed of light squared. The additional energy imparted to the ball when you throw it turns into mass, as it cannot turn into speed. You already know that mass can be converted into energy inside stars, for example. And here you have an example of the opposite phenomenon. Energy turns into mass. And here is the explanation. You have just learned, thanks to Einstein's special theory of relativity, why you were becoming heavier before your shout and the freezing of everything around. Now let's address the two problems of your high-speed journey: time dilation and length contraction. Most people, including myself, are simultaneously puzzled and fascinated by the fact that universal time does not exist. Common sense, honed over millions of years of evolution on the surface of our tiny planet, intuitively rises against such an idea. But even if we can see the effects of time on us and around us, it is a rather abstract concept, an immaterial flow of something completely invisible. Thus, despite the strangeness of the idea, we can certainly get used to the thought that time is not as smooth as it has seemed until now. Space is a completely different matter. We consider ourselves familiar with it, but that is a mistake. We do not know its meter. Yes, you are always in meters, but you think you are, and you are mistaken again. Depending on how you look at it, space and time are interconnected. If time changes, distance must also change. Why should this happen, you ask? Why must distances, lengths, contract when time slows down? The answer to this question lies in the existence of an absolute, unbreakable limit to the speed of nature, the speed of light. If distances did not contract, you would have already violated this limit. In space, light travels at a speed of about 300,000 kilometers per second. An observer on Earth, noticing you flying at 87% of the speed of light, would see you moving at 260,000 kilometers per second. Flying at such a speed, you must remember that the seconds you are experiencing now differ from the perception of time at 87% of the speed of light. 1 of your seconds equals 2 seconds on Earth, and in those 2 seconds, the observer sees that you have traveled 520,000 kilometers. This is apparently a distance twice that covered by you in 1 second. Nothing special, right? Wrong. Because even if you flew 520,000 kilometers in 2 seconds, only 1 of your seconds has passed. That is 520,000 kilometers per second. As you recall, since the speed of light is 300,000 kilometers per second, you would have broken the universal record. But this is not prohibited by the police, but by nature. Remember, nothing can move faster than light. Already in the early 20th century, numerous experiments confirmed this fact. In space, light always travels at this given speed, no more, no less. And he would never be able to explain this through his vision of the world, but Einstein managed to do so with his theory. In his theory of moving bodies, the special theory of relativity, time and distances must slow down and contract in such a way that despite the fact that no object can ever cross the speed of light, from any point of view, the time of the Earth observer passes twice as fast as yours. Thus, the distance you have traveled is, from your point of view, half of what the observer sees. Flying at 87% of the speed of light, you cover not 520,000 kilometers in a second, but 260,000. What appears to be kilometers from Earth is actually half kilometers for you. Your speed is always the same, no matter who measures it, whether you or someone else. Speed does not depend on the observer. Only time and distance depend on them. With the increase in speed, distant galaxies will appear much closer to you. This is because they have indeed become much closer. Objectively, this applies not only to you, but the objects themselves also contract along with the speed, as seen by someone who is not moving with the object. Any rocket and its passengers contract. Even you, flying like Superman at 87% of the speed of light, with your fists stretched forward, have contracted to half your height as measured by a tape measure on Earth, and the passenger flying with you would not notice it, since his height would also have decreased. And all of this is a consequence of establishing a fixed, ultimate, unsurpassed speed of light. All of this is contained in Einstein's discovery made in 1905 in the special theory of relativity, a theory that indicates the laws of nature for those who decide to travel at exceptionally high speeds. Strange, isn't it? It contradicts common sense, certainly, but that is how nature works. Now, what about gravity? We have intentionally completely forgotten about it for a while, but if we want to have a real understanding of the universe, we must bring it back. Therefore, at this moment, you continue to move rapidly through a universe whose fabric of space-time interacts with its energy content and curves it, creating gravity. Let's return to you. You are in space. Everything is still frozen in place. The Earth is somewhere far behind. The astronaut you introduced is long dead and lying in a grave. You are heading straight for the distant galaxies, which now appear much closer. Just remember that time and space are now integral parts of the fabric of space-time in our universe. That gravity is the effect of the curvature of this fabric under the influence of the energy contained within it, regardless of its form. And that mass is energy. You are just becoming heavier and heavier when you froze your journey. Let's unfreeze the picture. Ready? You are flying again. Your body is moving extremely fast, and the engine is powerfully pushing you forward, making you heavier. It's as if gravity has taken its place in the picture. Your increasing mass increasingly curves the space-time around you. Now, you possess mass, small enough to cause passing meteors to start sliding down the slope you create, even falling on you. It hurts when they collide with you, but as you become heavier, without increasing in volume and denser than before, you do not shatter into pieces. Accumulating more and more energy, you become more massive than the Earth. Within your influence are already large meteors, even small planets. Now they orbit around you. You are so heavy that the curves you create in space-time around your own body become so pronounced that the universe you see begins to distort in all directions, not just ahead. This is no longer due to speed, but due to gravity, due to the curvature of space-time. The energy gathered inside you, energy, space, and time intertwine in the fabric of the universe, distorting everywhere you look. The universe appears distorted, accelerated, as if your time has begun to flow more slowly than in any other parts of the universe. You have reached a mass equivalent to 5 Earths concentrated within your body. You are clearly struggling to lift your arms or anything of the sort, and now you can't move at all. Frankly, if I were you, I would stop right now. Why? Because sooner or later, by accumulating more and more energy in your own body, you would ultimately turn into a black hole. That is not a very good idea. Unfortunately, you are already too heavy to even move, so you cannot even check if there is some hidden switch for the rockets behind you. Your arms are now practically glued to your thighs, and you are actually starting to sink into yourself. And 100, you scream in panic and find yourself in a plane in a seat. Your strange neighbor on the tarot looks at you. His expression is as if you have woken him up. He is undoubtedly strange, but at this moment, you probably look even stranger. You mumble something that sounds like ringing and turn to the window to look outside. It is dawn. No signs of an imminent landing in your hometown. No signs of a future. No signs of distant galaxies that have become closer than they should be. No revolving planets. You are just flying. You look at your watch. It seems you have been in the air for 8 hours. May I ask why you were screaming? Asks the strange neighbor. Where are we? What year is it? He asks in confusion. You respond, Excuse me, what year is it? You insist, rather nervously. 2015, replies the neighbor, slightly surprised. When the flight attendant announces that the plane is ready to begin its descent, you realize that you are just sleeping, that you did not travel into the future. You are still here, on your way to a beautiful, ancient, normal hometown with its concrete roads and brick buildings. The outside temperature is 12 degrees. Continue your restorative nap, and the morning fog promises to clear by noon. 2015. What a relief. A lot of strange dreams. On a plane traveling at near light speed, it is evident that the fidelity of the experiments of Ophelia Keating from 1971 has been proven, confirming the result with an increased level of accuracy. So space and time truly mean what the combination of space and time means in the universe. Time measured by clocks depends on who is looking at it, and the hands depend on where you are and what is nearby, a bit of gravity, and your speed. In the early 20th century, this sounded very abstract, but today it is an experimentally proven fact. We all must accept that in the universe, time and distance are not universal concepts. They depend on the observer, on who experiences them, and who looks at them. This is the concept of relativity. Otherwise, the speed of light would not be fixed or limited. And what humanity has drawn from this knowledge, will it change our everyday life? Part of it is indeed related to speed. The fact is that our technologies frequently use rapidly moving particles to transmit information in every possible way. The special theory of relativity thus helps us understand how all the matter we are made of works. As you will soon see, the electrons within the atoms that make up your body, and almost everything else in the microworld, indeed move very quickly. However, as for gravity and space-time, however astonishing it may sound, only one thing. Popular devices still use the GPS connection. Each time it checks your location, GPS, whether in a smartphone or in a car, uses the fact that space-time is curved around the Earth. The closer you are to the surface, the steeper the curvature. And not only in the spatial aspect, but also in the temporal aspect. Satellites embedded in watches exchange information with GPS devices, creating localization. If the correction accounting for the time difference between Earth and the satellite does not occur, the location will immediately be thrown off. It will shift by 10 kilometers a day, and GPS will become useless. It is thanks to Einstein's special and general theories of relativity that GPS works well. This is the essence. There is no such thing as parts that move uniformly throughout the universe. So, the plane you imagined flying at 99.999 billionths of a percent of the speed of light has incredibly quickly moved through space. And compared to Earth, with all its inhabitants, you have landed in 2014. You can consider yourself lucky. If you had flown even faster, you would have landed even further into the future. How much further depends again on the speed, but there is a limit because nothing can move faster than light. Traveling as fast as light may one day become possible, but you will have to make a tremendous sacrifice. Get rid of weight. All weight, because light cannot carry any mass and therefore moves so quickly. Acceleration spreads light. And what happens to matter, you justly ask? You have experienced it yourself. By accelerating too much, everything with mass becomes even more massive. So, to reach the speed of light, you must first have no mass. Nevertheless, what could happen if you were able to transform yourself into some massless being? How would time flow then? As shocking as it may seem, the answer is not at all. The ticking of any clocks, even if you were to find yourself massless, would simply stop. At the speed of light, time freezes completely, and this is the reason why light, having traversed the entire universe before reaching us, remains the same as at the moment of its emission. Unlike postcards, torn and tattered, bearing no resemblance to the original, after 13.8 billion years, the images carried by light across the cosmos are not subject to the passage of time. By collecting radiation from the farthest corners of our visible universe, we obtain snapshots of that time. So, as a being of mass, you have no choice but to be subject to the effects of time. You cannot do anything about it. To become eternal, you would need to transform yourself into light, which is impossible. However, if you could, then your time would indeed restore itself, and you would become immortal without even realizing it. Nevertheless, despite the impossibility of achieving immortality, even with mass, it can be said that one can reach a future unattainable for your neighbors. To do this, you simply need to move as fast as your plane or relocate to a gravitationally much more powerful planet than Earth. In conclusion, I would like to say, I know that some of you, for one reason or another, dislike my age, and you would very much like to remain young for as long as possible, or at least much longer than your neighbors. To such readers, I address the following warning. There is no point in trying to become a sprinter, a Formula One driver, or a pilot of a British Air Force aircraft. There is no point in attempting to accelerate to 99.999 billion% of the speed of light. Why? Because your clocks, from your perspective, will never change. For your eyes, as well as the cells that make up your body, a second will always remain a second, day after day, year after year, and so on. Your personal time and aging will not slow down. You will not live longer. Cells will continue to grow and decay at the exact same rate as everything traveling with you. Traveling at cosmic speeds or living on a much denser distant planet will not allow you to live longer, because for you, 24 hours a day have always been and will always be 24 hours. However, other people may see you living longer than they do. The acceleration of the present for the rapid attainment of something in the future is theoretically possible and may even one day be practically realized, but living longer through space travel is not possible. With the help of Einstein's special and general theories of relativity, you have discovered a truly strange world around us, accessible to us through our senses. The world in which we live our daily lives is no stranger than what you will encounter upon your safe return home. After that, there is the world, and the world of superspeeds. It is time to visit the micro world, and I fear that even if you have not believed in magic before, it may be time to start. Part 4. Immersion in the Quantum World. Chapter: A bar of gold and a magnet. The cousin has left. You really asked her to stay for a couple more days, mainly so you would have someone to discuss the strange relativistic dream with. Well, rather unexpectedly for you, she declined the offer after weighing the pros and cons. She found you to be perfectly fine and felt that she had played her role in bringing you home. She flew on the first flight to Sydney, leaving you in charge of the entire collection of crystal vases she brought to lift your spirits. Now she is in Australia, and you have returned home to your couch, looking at the dreadful vases, twirling a small palm-shaped magnet you bought at a souvenir shop as a memento of the tropical island. You still have a whole week before work starts, 7 days to find as many ways as possible to get rid of all of this. The new oscillations are over, or the adventure of the hidden nature of reality, or a new level of understanding awaits you ahead. Not finding a direct answer, you get up to make yourself a hot cup of coffee. While fussing in the kitchen, you suddenly notice that one of the bricks is slightly protruding. You are puzzled, pull it out, and to your surprise, in the resulting hollow lies a bar of gold, probably hidden there by someone from the rather well-off former residence. It is the size of your palm, and therefore worth a pretty penny. How you could have missed the brick before remains a mystery, but there is probably nothing better than returning home to discover gold in your kitchen. So you do not ponder this for too long. Pour yourself some coffee and look at your treasure with a sly smile. You have traveled through space, the realm of everything very large, the mega world. You have moved in a world of super speeds as fast as possible, but you have no idea about the micro world that actually makes up matter. Perhaps gold is made of tiny bricks. Why are the materials around us so different? Why is gold different from cheese? Why do we not turn liquid like water at room temperature? With a smirk, deciding to prefer science over money, you cut the gold into 2 equal parts to look inside. Unlike some types of cheese, but not all, the inside of the bar has the same color, the same lack of smell, and everything else as the outside. Nevertheless, you cut one of the halves into 2 more pieces, then into 2 more, and then into 2 more, feverishly watching for any changes in the ever-shrinking pieces. It seems that gold does not change. One might think you could cut it forever, but there is nothing like that. After 26 or 70 attempts, you are left with the thinnest possible piece of gold. Cutting it again, you will still get something, but it will definitely not be gold. You cannot break it down further. We call the smallest piece that still remains gold an atom of gold. Note that while it may seem that cutting something in half 26 times in a row is not much, it is not so. It would be quite difficult for you to accomplish this under normal conditions. To give you a general idea, when you fold a page from this book in half 26 times, you would achieve a thickness of about 14 kilometers. A similar example. Let's say you take a mountain 50% higher than Everest and have it 26 times. In the end, you would be left with something as thin as the pages of a book. Only with the best modern technology can one examine an atom of gold. And what about lead, silver, or carbon. Any other pure element instead of gold would lead to the same outcome. Rolling two small pieces that easily fit in your palm 26 times, plus or minus 1 or 2 times, you would ultimately see an atom that cannot be broken down further without getting something different from the original material. However, cheese is not a pure material, but it too consists of particles stuck together. All known matter in the universe consists of atoms. So what are atoms themselves made of? You cannot say yet, but you already have a hunch that they are filled with smaller components. These tiny pieces are the same for all atoms in the universe. Very soon, you will enter their world. But I can already tell you that since the number of these tiniest components varies from one atom to another, pure materials have very different properties. Therefore, as everyone knows, any stockbroker will certainly question your mental health if you try to exchange a kilogram of mercury worth about 23 pounds for a kilogram of gold worth about 26,000 pounds, or plutonium worth about 2.6 million pounds, depending on the market, on the grounds that they are all made of equally structured atoms. So what are they? What is the theater that gives the materials made from them such different properties and forms? And why, if everything is made from the same oil, can you cut a diamond with a knife? No. With such questions buzzing in your head, you go out for milk and coffee. On your way to the fridge, you automatically grab the palm-shaped magnet to stick it with the others. But when it slips from your fingers, jumping straight onto the metal door, you freeze in place. Until now, such behavior of the magnet has been quite familiar to you, but no more than that. How did the magnet know about the fridge's approach? Did the magnet know about the fridge, or did they both? Or is it just magic? As far as you know, you have never seen any interactions between magnets and fridges, nor has any ghostly hand reached out from one to grab and pull the other to its surface. But maybe you just weren't paying enough attention. You distinguish the magnet from the fridge and examine the rough back of the palm. As far as one can claim, the dark surface is flat. Focusing and firmly gripping the magnet between your thumb and index finger, you press your cheek against the fridge door, intently studying the air as you bring the magnet closer to the door. It is already a few centimeters away from it. You feel something, a force. Is the force of attraction pulling the magnet to the fridge, or the fridge to the magnet, or both to each other? It is hard to say, but there is nothing in the air. You definitely do not see the slightest hint of anything that could explain how they know about each other's presence. Now, the magnet is half a centimeter from the fridge, and the force of attraction becomes much stronger. It is even hard for you to keep the magnet in place, and still, nothing is visible. You release your hand, and the magnet jumps from your fingers towards the door, sticking there, just as delighted with the new neighbor as you are. Captivated by curiosity, for centuries, many men and women have been puzzled by this strange attraction. Something otherworldly, isn't it? The magnet jumped from your hands. Until it touched the fridge, nothing happened, and there was still a force present. Our ancestors thought the same while observing magnets. So, although they did not have fridges, they began to speak of a frightening long-range force to describe the invisible something that makes magnets work. In fact, it is somewhat reminiscent of gravity. No one can see gravity when they walk. He invented his amazing formula to describe how objects in the universe attract each other. He had no idea what exactly was responsible for the gravitational force he discovered. However, Einstein revealed this about a century ago. Gravity is not a force, but a fall, he claimed, a fall down through curved spacetime. The same happens with magnets. That is, magnets also create steep curves in spacetime. No, it cannot be. Otherwise, everything would fall in relation to them. Trees, ourselves, beer, and any real things. They are only nails, iron filings, and other potential magnets. We never feel how our own fingers are attracted to a magnet. No, there must be something else. And that something was discovered about 80 years ago. It is what we call the quantum field. To express it more accurately. And now that you know about the existence of the atoms of magnets, you are on the verge of discovering the wonders of the quantum field. Chapter 2. Like a fish in water. Imagine for a moment that you are a fish, and for some reason, you decide to take a look at what is above your home, the ocean. Gathering as much speed as possible, you shoot up from the ocean depths like a torpedo. You are heading towards what people call the surface, which a fish would probably call the ceiling. You swim quickly, even faster. The water glides over your scales, and the surrounding light grows brighter as you approach the boundary of your liquid world. And then you burst through to the surface. There is no water around anymore. You rush through the void that we, humans, call the atmosphere. You flap your fin, but cannot rise higher, unlike birds. But, as befits a fish, your journey upwards suddenly ends, flying headfirst and sliding down the slope of space-time created by the presence of the Earth. You switch back into the ocean. After a while, returning to the salty depths of your liquid home, you discuss your experience with your fish friends, who share your aspirations for the unknown. You immediately agree that up there, but the ceiling of your vast liquid world, it is impossible to swim. Above the ocean, you conclude, there is only blue emptiness. We, humans, understand the subject better. We know that above the ocean there is air, and that it is far from empty. Deprived of air for more than a couple of minutes, we die. However, most of us are not much wiser than fish. Don't we all hold the opinion that in open space, outside the atmosphere, beyond our precious air, there is absolutely nothing? Are we not sure that space is a black void? As you will see over the remainder of this book, this is a misconception. Outer space is far from empty. When you, in the form of a fish, momentarily found yourself on the surface of the ocean, you entered another world, primarily composed of gas and dust, not liquid. The world you are about to enter now is much more spacious. It is called the quantum world, the world of fundamental matter. Unlike the sea, which consists of water and ends where air begins, the quantum world is everywhere. It makes up us, the matter in space, even in empty space. Nevertheless, the search for an entrance into this realm took humanity millennia. The doors to the quantum world are hidden deep within the micro world, and since air, gravity, and many other things can spoil the picture, let's forget about them for a moment. And the best way to do this is to send you back into outer space, tearing the magnet from the fridge door to check its surface again. You observe absolutely no visible changes on it. It is just as black and just as smooth. And yet you felt a force. There is no doubt, it is very strange. Pressing your cheek against the fridge again for a repeat experiment, you focus so much that everything around you, except for the magnet and the fridge, disappears. The floor, the air, the bar of gold, the kitchen walls, the apartment, your hometown, as well as the Earth moon and everything else. You float in outer space, in a world of thoughts, governed by the known laws of nature today. There is no air here, no gravity. There is nothing at all except for you, the magnet, the fridge, and whatever makes them interact. At this moment, you need to use this kind of situation, so don't worry too much and focus on the task. Your cheek feels the coolness of the fridge door. The magnet is still in your hands, and when you let it go, new adventures begin. You start to shrink in size throughout your journey through space-time, examining the universe on a grand scale to understand the mega world. And when it was necessary to look at the world from the perspective of super speeds and to move rapidly, now you are on your way to discovering the quantum world for yourself. So keep shrinking. You become a smaller copy of yourself, less than a few atoms tall. At some point, let's see. When you read these lines, the book or computer screen is probably at a distance of a few palm widths from your eyes. The smallest thing that vision can perceive at that distance is about 1/20th of a millimeter, a third of the width of a human hair. Right now, your copy has shrunk 100,000 times, just to the right size, to see if anything is actually happening between the magnet and the fridge. Carefully, though somewhat stunned by such a reduction, you look around for ghostly hands reaching out to each other. You turn your head, left and right, up and down, and see nothing. You know the magnet is somewhere to your right, and the fridge is somewhere behind, but not too far from your new location to see them. So you wait, and nothing happens. Nothing. After quite a long period of silent observation, you decide to try something else. Where sight is powerless, perhaps sensations can help. You remember that, as a child, to keep yourself occupied, you played at being a psychic. You take a few deep breaths to concentrate and then shut your eyes, becoming like a tiny yogi in space, smaller than a speck of dust. With your eyes closed, you slowly spread your arms out to the sides, as shown in movies. At first, you feel nothing, and then something happens. It feels like you are a fish, and everything around you is immersed in something, certainly not water. You open your tiny eyes, ready to see what this sea consists of, but the sensation immediately turns off your vision, and once again, there is nothing around. Indeed, a very strange feeling, even a bit frightening. You are not a coward, and quickly conclude that, like many other things in the universe, what you felt is real, but not visible. So you close your eyes again to enter the quantum world, like a yogi. The sea is here around you. There are even currents that are supposed to arise in the magnet and end at the fridge. You are surrounded by force loops passing right through you, and you realize that what you feel is what makes the magnets and the fridge interact. There is something called an electromagnetic force field. Through your closed eyes, it looks like a woven bright mist, spreading everywhere and thickening near the magnet and the fridge. Pulsating waves travel through it at the speed of light, informing you of the magnet's and fridge's approach, and thus, sooner or later, they will stick to each other. Therefore, you open your eyes with a mouth twisted in horror and look at the approaching huge black magnet just about to crush you. You step back, filled with fear. Now you are so close to the magnet that you can almost see the atoms moving on its surface and even the microcurrents flowing across it. What nature of the electric and magnetic is, or both, you have no idea, but it is clear that, wait, what was that? Something happened. You did not see any hands reaching from the magnet to the fridge. They did not appear, but there was light. Virtual or real? It is hard to say, but it was definitely light. It emerged from nowhere, right before your eyes, from the surface of the magnet or from inside it. You turn your head towards this absurd appearance and see the fridge door, a huge door, also moving in your direction. You hold your mini breath. In a moment known as a catastrophe, more strange pearls of light appear from the void that seem to separate the magnet and the fridge. Just a moment ago, the void definitely did not look empty anymore. Pearls of light flash around you, between the magnet and the fridge, as if numerous tiny angels were present. You easily guide the two objects towards each other, mesmerized by the spectacle, and convinced that your smaller body is living its last seconds. You wonder if these particles of light are products of your imagination or reality. They seem virtual, as they last only moments, appearing from nowhere, but they have a very specific effect on the magnet. Let's say bright little angels carry traces that pull the magnet towards the fridge. In your home, you close your mini eyes and wait for the moment when you will be crushed. You are back in the kitchen, in shock, looking at the fridge door where the magnet has stuck with a characteristic metallic sound. Wiping the drops of cold sweat streaming down your forehead, you, despite being completely alone, feel a bit embarrassed because you thought it was all again a product of your imagination, even though it felt quite real. You have just witnessed a long-range effect not due to magic, although I admit it is quite eerie. You have undoubtedly observed a mysterious force that causes two magnets to attract each other. Electromagnetic interactions, carried by virtual particles of light, are so strange that they exist solely to convey this electromagnetic interaction. They emerged between the magnet and the fridge, seemingly from nowhere, but that is not the case. You have just discovered that between any two objects in the entire universe, whether they are magnets or not, there exists something called an electromagnetic field, a sea of forces from which virtual particles of light can pop out at any moment. Right now, while you are looking at the fridge, countless tiny virtual pearls of light are moving between the magnet and the door. But you will never be able to see them again. That is why they are called virtual. They appear and disappear in the void, which is not a void, preventing anyone from seeing them. Such virtual carriers of interaction exist everywhere around, right now, even inside you. They all belong to the electromagnetic field, an invisible mist that fills not only the space between fridges and magnets, but the entire universe. And what about magnets that repel each other? You have certainly seen those, haven't you? As you will soon experience, these virtual pearls of light, with which you have just been introduced, can either attract, repel, or have no effect on the matter around us. It all depends on what matter is being referred to. In fact, it all depends on a single thing that scientists have called electromagnetic charge. And just as you can measure your weight with scales, you can also measure your charge with instruments. Although our charge averages out to zero, the human body is electrically neutral. Otherwise, magnets would stick to us, which would be quite annoying. But the individual particles that make up your body have different charges. Nature has only two types of electromagnetic charges. For convenience, they are called positive and negative. Like charges repel each other, that is, similarly charged, and attract oppositely charged ones. Plus and plus, as well as minus and minus, repel each other through the virtual light that arises between them. The closer they are, the more virtual pearls of light, the stronger the repulsive forces. On the other hand, pluses and minuses love to squeeze together in embraces, like the magnet and the fridge. And the closer they are, the stronger they attract each other. At the same time, neutral objects, finding no pearls of light, do not stir. They may be neutral, having an equal number of positive and negative charges, like your body, or have no electric charge at all. Some particles you will encounter later do not have it. Such are the laws of the electromagnetic field. Now you may think that since such an explanation of the interaction of magnets with the fridge cannot be seen with the naked eye, all of this may be a rather useful conclusion, but does not quite correspond to how nature works. In fact, then you might argue, the electromagnetic field is just an image that allows scientists to describe the reaction of charged objects to the presence of a magnet. The description, of course, is justified and figurative, but it is nothing more. One might think that all of this is obvious, but you would be wrong. The field you have just been introduced to, the invisible mist that permeates the entire universe, activating near and between charged objects, is much broader than this definition. First of all, it is very real. In fact, it not only encompasses electrical or magnetic charges, but is the essence that gives rise to all charged particles. Light everywhere in the universe, the electrons you will soon encounter are its expression. The light perceived by our eyes is of a completely different nature, and both are nothing more than the pulsation of the field. Many of the most outstanding scientists on Earth today consider the electromagnetic field, the fundamental fields of magnets and even fridges, to be even more important than light, and, as absurd as it may sound, by the end of this part, you will be introduced to the existence of two other quantum fields that also fill the entire universe, and understand that, as modern science asserts, all the matter we know, all the light that spills everywhere, is merely an expression of the pulsation of these fields. We, humans, are indeed like sea fish, in a sea made of fields, just like everything else. And although our ancestors once lived in the ocean, it took billions of years for them to evolve and discover the existence of quantum fields. Chapter 3. Entering Hell. You passively gaze at the magnet on the fridge for quite a while, then shake your head, open the door to finally get the milk you have been craving. Before the magnet drew your attention to the phenomenon from the world of ghosts, returning to the mug left on the table, you are about to pour the milk into it. Suddenly, the sight of the gold lying nearby makes you stop. What exactly are the atoms of gold you discovered earlier, or the atoms moving on the surface of the magnet? Perhaps they resemble small round balls or cubes. How exactly do charges prefer to receive virtual pearls of light from the electromagnetic field? And what the hell do I mean when I say that in this expression of certain fields? As expected, these questions send you back to the state of mind, and you find yourself floating in the middle of the kitchen, away from all familiar objects, curiously awaiting an answer to the question of what your discovered gold atom consists of. But this is not that salad. Rather, it is the smallest atom, the atom that makes up 74% of all known matter in the universe, hydrogen. This is the very hydrogen whose atomic nuclei in sun-like stars fuse, creating larger elements. The byproduct of this fusion is light. Frankly speaking, It is clear that there is too much of something new right before you. It is very difficult to determine where it is, let alone what it is. Your intense scrutiny does not help. What you decided to try to feel it again using the yogi method is astonishing, but it works. Your eyes are closed, but you can imagine a picture, something like a wave, oscillating, swirling in the electromagnetic field, a wave rocking around a sphere, a hollow sphere, or, rather, a full petal. And it is not quite a wave, but in a spherical shape of a petal, pulsating, moving rapidly at a speed very close to the speed of light, so that the world seems heavily distorted, not to mention the counting of its time compared to yours. But it is not concentrated in a specific place. All right, let's be honest. You have no idea what you are imagining. But all this spherical shape of a petal, and any other rapidly moving thing, indeed, carries an electric charge. One can feel its interaction with the electromagnetic field, just like when approaching a magnet. So is this hell? Still varieties? Exactly. I think you understand that here there is nothing other than something buried deep within the microscopic compared to the volume of the moving wave. But something must be strong, and even very strong, to keep the charge you feel moving from disappearing. You understand that a hydrogen atom has a nucleus surrounded by a moving charge. All atoms in the universe have such a structure. Nuclei of different sizes surrounded by one or more electrically charged waves. Scientists have named such a nucleus an atomic nucleus. They clearly charge the oscillating wave an electron. And this is a confusing discovery. An electron has nothing to do with the tiny point you have imagined. To confirm the correctness of your conclusions, you leave the yogi method alone and open your eyes. Quite unexpectedly, the oscillating wave disappears, becoming something else, much more resembling a particle. All right, electrons, absolutely identical to this, are present in various quantities in all atoms of the universe. They are the basis of all our electrical and magnetic devices, whether it is a computer, washing machine, cell phone, electric light bulb, or anything dependent on them. Therefore, you slowly, very slowly, extend your tiny hand forward to grab it and examine it more closely. Strangely enough, it is very difficult to catch an electron. Every time you manage to catch a glimpse of it with the corner of your mini eye, it starts moving chaotically, as if the very attempt to detect it causes the electron to change its course in unpredictable ways. This is not a trick of your imagination. It is a real phenomenon, one of many occurrences in the quantum world, but not in our everyday world of crystal vases and coffee cups. This is part of the fundamental uncertainty of nature, viewed from our perspective. You will learn in detail what this means in the 6th part of the book. Even now, you sense that something supernatural is happening. You think you need to catch this electron and make it comply. Sure, no matter how small it is, you are pure intellect and can do anything you want. And may you be damned if some tiny electron tries to refute that. As soon as your mini eye detects its presence right here, to your right, you pounce on it faster than lightning. And there it is, in your tightly clenched right hand. The electron wriggles inside like a butterfly, practically at the speed of light, flapping its wings against your palm. You begin to squeeze your fingers. Electrons are charged particles. They interact with others in your hand through virtual pearls of light emitted from the electromagnetic field. You continue to tighten your fist, wishing for the electron to enter its tiny prison. And suddenly, You no longer feel it. It has vanished. You clench your fist, and there are no electrons there. You are absolutely certain that you left no tiny gap between your fingers, yet it slipped away, and you felt nothing. It seeped through your palms, touching them, and returned to the invisible core of the hydrogen atom from which you took it. Outrageous, but how did it manage that? How could an electron slip from your grasp without touching you? Frankly, it passed through your hand, leaped out, a record jump, a quantum leap, something confined to the subatomic world, non-existent in the everyday life of kitchens, you, and airplanes, or something of the sort. You haven't figured out the electron yet, but you are already familiar with one of its strange properties. It can jump like no other. This phenomenon is called quantum leap, or tunneling effect. And it turns out that not only electrons, but also particles you will discover in the quantum world are capable of such quantum leaps or transitions. Now that we have clarified this, let's pause for a moment to think together about terminology. When scientists discover something new, it is necessary to give it a name. For something microscopic in the quantum world, they create associative words, where the adjective quantum is followed by a noun, usually taken from everyday speech. Thus, we get tunneling jumps, or world, and the terms are easily understood as they mean the same thing as in everyday life. However, the presence of the word quantum serves as a warning. Quantum automatically implies the existence of something suspicious. In the case of the hand, the suspicion of quantum tunneling lies in the following. Electrons indeed make tunneling moves, but there are no tunnels. Quantum leaps are hardly ever significant for humans, but imagine if they were. Perhaps you can imagine it, and you find yourself back in the past, in your childhood, in that very kitchen. Your father has just asked you to clear the dishes from the table. It is already late, and suddenly you feel as if all 100 kilometers of the Earth's atmosphere have fallen on your fragile shoulders. You mumble something barely resembling the growl of a bear cub, but nothing helps. The table with dirty dishes awaits you in despair. You sit on the floor, and then it begins. You suddenly find yourself in the dining room on the other side of the kitchen wall, next to the table, and all the cutlery is in order. A glass begins to tunnel, jumping and so on, through the wall straight into the kitchen. This may sound like a fairy tale or an excerpt from a Mary Poppins book, but honestly, with these quantum leaps, you can never guess where the cutlery, dishes, glass, and so on might jump. Ultimately, they are unlikely to end up in the dishwasher, and your father will have to buy all new dishes because you will never find them again. Sounds strange, doesn't it? That is what quantum tunneling is. If we were to translate quantum laws into our plane, then doors and walls of personal privacy would not exist. Fortunately, in a rather mysterious way, they do not apply to us. However, thanks to the tunneling effect, almost everything in the micro-world is capable of crossing any barrier. Thus, it is believed that particles can do this because they are allowed to draw energy from their quantum field, a sea in which they swim. A sea that indeed fills all places in space and time, with as much energy as one desires, a dream of all athletes. But this does not give you a clue as to what an electron looks like. I would prefer to be quite frank with you. Your copies may face a slight disappointment here. It is impossible to visualize an electron because of the very quantum field to which it belongs. The electromagnetic field exists everywhere, and each individual electron in the universe not only belongs to it, but is absolutely identical to any other electron, everywhere and always. Swapping them around the universe would go unnoticed. Because of this quantum field, whatever expression they are, electrons cannot be described as macroscopic objects. They relate to the field. They are part of it, just as a drop of water belongs to the boundless ocean, or a gust of wind belongs to the night air. Drops or gusts that you cannot isolate individually until an observer looks. Drops and gusts of wind are identical to the ocean itself, or the wind itself, mixed in essence, much broader than they are. They have no individuality of their own. In the quantum world, when observed, electrons become particles with defined properties, like drops taken from the ocean. But their properties are unlike anything you have seen before. They do not behave in a familiar manner, or, at least, as we might expect, based on everyday experience. Even if you know where the electron is, it is impossible to know how fast it is moving. Its speed becomes unpredictable. This is why it was so difficult to find the electron inside the hydrogen atom. The moment you saw it, it began to move chaotically. You were unable to keep track of it, and it vanished from sight. Similarly, if you know how much energy an electron has, you cannot calculate how long it will retain it. Energy, time, location, speed. These are truly independent concepts in the fields of quantization. You will hear more about this in the 6th part. For now, while your copies are judging their journey through the quantum world for the first time, you may consider my remark a warning about a potential bait for some listeners. Your diminished copies will simply have to perceive everything as you did when you were a small child discovering the world without prejudice. Location and speed cannot be known simultaneously. Fine, so be it. Quantum laws allow for supernatural jumps and tunnels. All right, let it be. The explanation will come with time, because, after all talk about the quantum tunneling effect sounds like complete nonsense to me. I have been told that once, after giving a lecture on quantum physics, Einstein told a student, "If you understood me, then I must not have been clear enough." So if this also sounds like nonsense to you, that's perfectly fine. Nature does not take offense. It is here for us to discover, that's all. But is it really real? Well, some have taken quantum tunneling quite seriously and have tried to find practical applications for it. Amazingly, they succeeded about 30 years ago. Working at a company in Zurich, German physicist Gerd Binnig and Swiss physicist Heinrich Rohrer were convinced that they could use quantum tunneling to visually inspect any surfaces on a phenomenal small scale. The scientists believed this would finally allow them to see atoms. Generally, an electron does not leave its atom. There is no better place, and usually an alternative appears that must be located quite nearby. Otherwise, the electron cannot get there unless it uses its quantum power, creating a tunnel through voids and jumping over obstacles with the help of an extremely thin, finely sharpened, and pointed needle connected to a current measurement recorder. Binnig and Rohrer scanned the surface of materials without touching them, remaining quite far from the surface. They should not have detected anything, as the distance between it and the needle was too great for the amplitude of the electron's movement. But they detected electric currents related to the jumps of the electron. The closer the needle was to the material's surface, the more jumps were detected, and the more noticeable the electric current grew. By plotting these currents on a graph, they obtained three-dimensional images of the material at the atomic level with extraordinary detail. They built a microscope, now called a scanning tunneling microscope, which could see the atoms themselves. Its accuracy is astonishing, within 1 to 10% of the diameter of a hydrogen atom. In other words, if a hydrogen atom had legs, the scanning tunneling microscope could count them, and perhaps even the number of toes. Gold atoms, like those you find in your kitchen, were scanned in the same way several decades ago. Today, the scanning tunneling microscope is used to gain insights into how different types of atoms intertwine in the matter around us, as well as in the most advanced artificially created materials. With such a microscope, engineers have gained the ability to manipulate individual atoms. Quantum tunneling has proven to be real, and it has practical applications. For creating such a tool, Binnig and Rohrer were awarded the Nobel Prize in Physics in 1986. Electrons, like the one you tried to catch, inhabit the outer boundaries of all atoms in the universe, and they are elusive. But despite the impossibility of describing their appearance using everyday terminology, scientists have learned to accept their strange behavior. As far as modern science knows, electrons cannot be split into any smaller particles. Unlike atoms, they cannot be divided, split, or even broken. They are created by the electromagnetic field. They are its expression. In contrast, quickly disappearing pearls of light appearing between a magnet and a refrigerator are called virtual particles. They are carriers of interactions, existing only to transmit electromagnetic force between electrically or magnetically charged particles. Atoms, being made up of smaller components of electrons and what constitutes their nucleus, are not fundamental particles. They consist of a large number of further components. Electrons interact with the rest of the world not only through virtual photons, they can also come into contact with real photons, with real light detectable by the human eye. This interplay of matter and light allows us to see the world as it is. Currently, real photons, like electrons, are also understood to be created from nothing, fundamentally, and as an expression of the electromagnetic field. They are real, a series of invisibly removed quantum pulsations, capable of behaving both like waves and like particles. Just such a wave of photons. Now we, white hydrogen atoms, to get here, had to make a long journey, about 1 million years. They tried to break free from the molten core of the sun to its surface, which they reached about 8.5 minutes ago. Finally free, unburdened by matter, they raced through space at the speed of light, all 150 million kilometers separating the surface of a divided star from our planet. Of all the places they could have gone, these photons ultimately chose Earth, reaching its atmosphere just a fraction of a second ago, only to charge up in it and fly, just like in your kitchen. From this moment on, they have little left to do. They pass through the window glass and approach the hydrogen atom. Your mini-copy watches their erratic movements across the kitchen, hoping to see the moment they touch it. Instead, they all fly through it and smash against the kitchen wall, except for one that has disappeared. Gone. Where did it go? In astonishment, looking around until you notice that the elusive electron of the hydrogen atom is now moving differently. It can be seen as a wave surrounding the nucleus. The peaks are coming closer together. How is this possible? The electron is excited. It has swallowed a photon. Remember how we first encountered this strange phenomenon some time ago in the second part, checking the cosmological principle? But now something even more interesting is happening. After a while, the electron unexpectedly spits out exactly the same swallowed photon that is now taken off in a randomly chosen direction. After thinking for a moment, you make the only possible choice, the most well-known of the fundamental particles of the electromagnetic field, namely the electron. Photons can interact and do interact with each other, and these electrons and photons can transform into one another. After thinking a bit more, you realize that you have always known this. Don't you feel warmth while basking in sunlight? When you sit by a lit fireplace in winter, doesn't your skin warm up? The skin, like all matter in our world, is made up of atoms, the outer layers of which are filled with electrons. When light from the sun collides with the atoms of your skin and their electrons, it captures photons, turning them into excited electrons that begin to move a little faster, creating heat. Whether you like it or not, your body is this incredible discovery. I will reiterate, matter and light can transform into one another and do so. Everything in our world is a play of matter and light, but not only that. Chapter 4. The Harsh World of Electrons. In the last 2 chapters, although you merely observed the interaction of a refrigerator and a magnet and glided over the surface of an atom, you have made great discoveries. You have unraveled the mystery of the long-range effects of electromagnetism and seen how matter and light can play with each other. Of course, this play is just one aspect of our world, but it is truly phenomenal that humble human senses are created to feel it. Light constantly hits our bodies, exciting the electrons in our flesh, eyes, and their retinas, heating us, creating us, matter, imparting some energy to it. Atoms can also spit back light swallowed by their electrons, causing surrounding objects to glow in one or several colors. The colors of the atom, or many atoms that have absorbed their photons. This is what gives color to our eyes, skin, hair, and clothing, to all plants and stones, as well as a special hue to distant stars. Rays of light fall on a tomato. All visible light is absorbed, heating it or being retained inside, except for the useless rays of the red part of the spectrum for the tomato's atoms, which try to bounce back for further travel, simultaneously telling the eyes that we are looking at an exquisite red vegetable. Without electrons and photons, we would not see tomatoes, would not know what the rest of the universe consists of, and whether the distant corners obey the same physical laws that exist around us. But even more astonishing is the fact that through our senses, incredible interactions are transformed into processed sensations in our brains. Humanity has derived science from these interactions and has also discovered the existence of fields filling the entire universe. And this is not just astonishing, it is a true miracle. Now, what about the atomic nucleus? Does it also consist of electrons? Is it another expression of the electromagnetic field? In a way, yes. As long as you can assert that the entire hydrogen atom you are considering is electrically neutral, then the nucleus must also have a charge opposite to that of the surrounding electrons. Thus, they balance each other out. Judge for yourself from a distance. But why then do you not see, while your tiny copies are intently gazing at the hydrogen atom floating in the middle of the kitchen? You suddenly notice that this hydrogen looks terribly like a heap of empty space compared to its contents. Regardless of what its nucleus may consist of, the fact that there is some amount of emptiness between the nucleus and the electrons is actually common to all known atoms in the universe. Strange. Then why doesn't the magnet simply pass through the surface of the refrigerator, allowing the vast empty spaces of the atoms of the magnet to penetrate the equally vast empty spaces of the atoms of the metal door. Why does the magnet stick to it instead? Shouldn't the colliding atoms simply collide and pass by each other like two clouds of steam without even noticing each other's presence? But no. Fortunately, otherwise, the world would not be solid, and the reason for that is electrons. To figure out why, your prepared gold atom will come in handy. The hydrogen atom you considered is the smallest atom on Earth. The gold atom is larger. You find yourself nearby and examine it. The first thing you notice is that it has not just one single wave-like electron circling around the hydrogen nucleus, but a whole 79 absolutely identical wave-like electrons swirling around the nucleus. The two things you notice are that, no matter how identical the electrons may seem, these wave-like entities do not share their territory at all. They simply avoid being in the same place at the same time. Nature forbids them to act otherwise. Regardless of the atom they belong to, their wave-like entities do not intersect anywhere, thus creating very strict conditions for potential cohabitation within any atom. They have no choice but to arrange themselves around the nucleus in layers, like an onion. That is exactly what they do. Only 2 electrons can fill the first inner shell. Only 8 can occupy the second, 18 in the third, 32 in the fourth, and so on. These numbers are known, and the same for all known atoms in the universe. What makes one atom different from another is related to the number of electrons it contains. By nature, they are always identical. The smallest hydrogen atom has 1 electron, whose orbital is within the first electron shell. Helium has 2 electrons. Their orbitals fill the first shell. Not randomly chosen by me. The third has 10 electrons. Its first 2 electron shells are completely filled with electrons. The chemical and mechanical properties of all atoms are related to how filled their outer atomic shells are. If you need to add an additional electron to this, you cannot simply shove it wherever you please, and certainly not into already filled layers. If electrons were like points, they would be hard to visualize. Although they can indeed resemble tiny balls under certain special circumstances, you will learn about them in detail in the 6th part. But to have wave properties, they cannot be merely that. Waves can easily fill space. That is why there is no space left for intruders in a filled electron layer. If an additional electron, whether by itself or belonging to another atom, truly decided to become part of an already created atom, it would have to settle aside, away from the natives, where there is still room, or take the place of one of them, pushing it out. Electrons simply cannot stand having their wave-like entities touched by anyone. This is a merciless world. Such a rule of non-overlapping has a name: the exclusion principle, or Pauli's principle. It was discovered in 1925 by Swiss theoretical physicist Wolfgang Pauli, who was awarded the Nobel Prize in Physics for it in 1945. The exclusion principle is the reason why magnets stick to refrigerator doors without penetrating inside. Or, what may be more important, why you cannot pass through walls, why you do not fall through the floor. It also explains why you can hold a book in your hands. The atoms of the cover have outer electrons that categorically refuse to give up their places to the electrons at the tips of your fingers. And your electrons also will not budge. So they are pages of each other, and there is no way your own force can compel any of them to act otherwise. The waves of electrons do not overlap. Never try to slip through a wall to prove that I or Pauli are wrong. You will break your nose, and the electrons will notice nothing. And yet, it is necessary to note that while electrons enjoy the sanctity of personal space, they do not mind exchanging. And this allows them, much to our delight, to create the matter that constitutes us, which you will now see. You are about to dive into the gold atom, but you will have to wait, because just then, an oxygen atom flies by. You look at it. Smaller than gold, oxygen with its 8 electrons is much larger than hydrogen on one side. Its first atomic shell is filled, but there is still room for 2 more electrons in the outermost shell, the second one, which has 6 electrons, but can accommodate 8. The lonely electrons of the hydrogen atom are about to miss this opportunity. Nearby are just 2 hydrogen atoms. So, as soon as the oxygen comes close, the lone electron of the first hydrogen atom jumps out, finds itself among the family of oxygen, never to be alone again. And at the same moment, another electron of the hydrogen atom fills the last spot. And since all electrons in the universe are absolutely identical, no one can say for sure who ended up there first and who moved in later. Perfect assimilation. The nucleus, bound to its electrons by virtual pearl-like lights, has no choice but to follow them. So now, 3 atoms are firmly stuck to each other. 2 hydrogen atoms and 1 oxygen atom are forced to cohabit. There is no more room for an additional electron. The entire structure is stable, sharing its electrons in the manner described above. Atoms become part of larger structures called molecules. The molecule just created before your eyes consists of 2 hydrogen atoms and 1 oxygen atom, 2 H and 1 O, H2O, which is water, the most valuable molecule for life, as far as is known, on a universal scale. Water typically does not gather in the kitchen. Rather, it occurs in space, within vast clouds of stardust scattered within galaxies, called nebulae by astronomers. Within these nebulae, oxygen produced by exploding stars mixes with hydrogen, which can be found everywhere as stars die, scattering. Around, their seeds pave the way for future water molecules, as well as many other substances. By exchanging 1 or more electrons, many atoms can be linked together in various ways. Molecules of varying degrees of complexity are formed. Thus, nature has created molecules of various sizes and properties. Tiny water molecules consist of just 3 atoms, while extremely long ones, like your own DNA, contain billions of attached atoms and carry all the information necessary to create someone like you. To shed light on the genesis of these molecules, with their help, life originated on Earth, and to unravel the mystery of the water that today covers 70% of the surface of our planet. Over the past decades, many satellites have been sent into space. Did water come from asteroids that collided with our planet about 4 billion years ago, or from comets that did the same? Did these cosmic rocks bring icy chunks or molecular seeds of life? We will soon find out, as many of these satellites are currently in place or on their way there. Meanwhile, we know one thing for sure. Only 6 chemical elements were necessary to create all the molecules needed for life on Earth: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, the so-called cetenops. By the way, since all your body is made up of molecules formed from these atoms gathered in various ways, you are ketenops. No offense. Now, while you contemplate your chnops, another question arises in your mind. Since you and the air consist of the same atoms exchanging their electrons, why can you happily pass through the air but cannot pass through a wall? In fact, That is an important question. As far as we know, air is filled with atoms that have as many electrons as you want, so they should not let you through. Not according to Pauli's principle. The answer is that not all atoms in the air share their electrons, and therefore are not as tightly bound to each other as the atoms that make up solid bodies. Your body, in particular, instead of hindering any of your movements, allows the electrons swirling in the air to spread apart as you force your way through them, bumping into each other along the way, creating some wind. This, by the way, is again the difference between gas and solid. In liquids, the nearby atoms are somewhat more tightly bound to each other, but not enough to stop you unless you try to penetrate it too quickly, like when jumping off a cliff. In solids, atoms do not move aside at all unless forced to do so, for example, by cutting paper with sharp scissors. And then, instead of fighting for their place, an electron will be forced to leave, leaving a vacancy for another electron. When an atom loses an electron, for example, after being hit by a powerful photon of sunlight, the combined charge of the nucleus does not reach the electrons. Deprived of one or more electrons, atoms become what scientists call ions, and they generally strive to stick to something to form molecules. In fact, they desperately try to find electrons. In the terminology of physics, they react vigorously, and conversely, the bonds created by electrons within the molecule can be disrupted during such processes. Energy is usually released. This is precisely what food is needed for. The chemical reactions within the body break down the molecules contained in food, releasing energy that is then multifunctionally used by the organism to sustain your vitality. Remarkable. This concludes our overview of the tiny world of electrons. You have only skimmed the surface of 3 atoms and already discovered how deeply modern science understands the processes occurring daily in our bodies. So before saying goodbye to the still mysterious atomic nucleus, I will summarize what you have learned over the past few chapters. The outer part of all atoms in the universe is diffuse, wave-like, massive. Electric charges are called electrons. They are fundamental particles of the electromagnetic field and actively protect their personal space. Pauli's exclusion principle prevents any 2 electrons from being in the same place in space and time. Despite the fact that there is more emptiness in all atoms of the universe than anything else, this is the reason why you will not be able to pass through a wall, fall into a chair, into a bed, or anything else solid, and our existence would turn into an art of survival. Thus, the Pauli principle leads to structural and chemical differences between atoms. Since electrons cannot all be close to the nucleus at the same time, they are arranged in layers around the atomic nucleus, filling only available spaces. This causes atoms to grow as the number of electrons they contain increases. It is important to note that electrons are not the only particles that obey the Pauli exclusion principle. Other particles do as well, but not all. Light, for example, does not. You can pack as many photons as you want into any chosen space, and they won't mind. In fact, they even enjoy it. And the more similar 2 photons are, the more they love to hug each other, like penguins in the north. Lasers are a consequence of this affinity. They represent a highly concentrated, high-energy beam of identical photons. Now that you've grasped this, you might get the impression that electrons and light are the only particles worth considering in our universe, but that is not the case. You will soon see other things within atomic nuclei. I just want to emphasize that there are even particles around us that do not care about the reluctance of electrons to ensure their privacy, non-existence, or anything else. They are known in this regard. They are particles that do not belong to atoms. In fact, some of them are so arrogant that most of the time they shoot at everything and anything, leaving almost no trace. For these tiny particles, the universe must seem quite dull. Even Earth, even you. You will encounter them quite soon. However, for now, you have yet another reason to celebrate. With such newly acquired knowledge about electrons and light, you are aware of what was known only to a limited number of people half a century ago, most of whom were outstanding scientists who received Nobel Prizes for these discoveries. And that's not all. Thanks to them, you can now explain almost everything that happens around you. From the color of a tomato to the hardness of a wall, the ground, or the reason why magnets leap from your fingers to stick to refrigerator doors. Everything that you, I, and all our friends experience daily is defined by the interplay of matter, light, and electrons, which categorically refuse to share their small amount of space-time with an exact copy of themselves. The next time you hug someone, feel free to imagine the virtual pearls of light being created, becoming reckless as your bodies draw closer, before the electrons obey the Pauli principle and decide that you cannot get any closer. I'm not sure you will mention this amazing fact on a first date, but I leave that decision to you. Before continuing your journey through the matter, we know there is one more piece of good news. In 2014, experiments conducted in the impressive underground laboratories of the European Organization for Nuclear Research, CERN, located on the border of Switzerland and France, confirmed that humanity has theoretically discovered everything that needs to be known about the matter that makes us up. This does not mean that there are no more mysteries left. A sixth of them will be more than enough. But it means that starting from 2014, we have a picture of the known contents of the universe that largely corresponds to everything that can be explored or discovered within the capabilities of modern technology. A picture that includes atomic nuclei, which you are now ready to consider. And if a sense of foreboding has crept into your soul about what strange things will be discovered there, you are absolutely right. Chapter 5. An unusual prison. Your coffee is getting colder, and the hand holding the milk is aching, but you don't care. Your mini-copy has just decided to dive into the depths of a hydrogen atom, creating a water molecule right before your eyes. Its nucleus is a multitude of tiny pearls of light, virtual photons, united with you. Between the magnet and the refrigerator, they appear and disappear, confirming that the nucleus you are striving for is electrically charged, shattering the notion that nothing exists between the electrons of the atom and its nucleus. Nevertheless, compared to the size you mentioned, you have to cross a vast distance before reaching the hydrogen nucleus, but you eventually find it. Just like the electron rotating around it, the nucleus of the hydrogen atom seems to lack a definite shape, but possesses a mass that is much heavier than that of the electron, 1,836 times more, and has a charge completely opposite to that of the electron. The hydrogen nucleus is called a proton. It is larger than the electron, but compared to the size of the atom itself, the volume along with the electrons is extremely small. The British physicist of New Zealand descent, Ernest Rutherford, discovered its existence in 1911, 3 years after being awarded the Nobel Prize in Chemistry for his work on a completely new phenomenon called radioactivity. However, he did not know what he could have known, namely, that unlike electrons, the proton is not a fundamental particle. Inside, it exists its own world. Not wasting time trying to comprehend the impossible, you close your eyes and spread your arms out to feel, like a yogi, what the inner world of the proton represents. You are immediately seized by such powerful forces that everything experienced so far seems like child's play. You open your eyes again, looking straight ahead. Electromagnetism can easily transport you. Some magnets stick together so firmly that you will never manage to separate them. Gravity can also overpower you, and in fact, it is doing just that. We will never be able to escape Earth's gravity, but overall, it is a different level of forces. Inside the proton, which looks like a somewhat cloudy sphere, you catch glimpses of appearing and disappearing virtual particles, as well as electromagnetic pearls of light that you introduce between the magnet and the refrigerator, or between electrons and protons. But they are not virtual photons. They are carriers of a new interaction, and the new force, along with the quantum field it belongs to, provides stability to universal matter. Without it, everything we know would vanish in the blink of an eye. Everything, including your body. Virtual particles carry that astonishing force, the force that keeps matter unchanged, hundreds of times more powerful than photons, the carriers of electromagnetic interaction. They are the carriers of what are called strong interactions. But if they were merely carriers, then why are fundamental particles of the new field not visible? Virtual photons make charged particles interact. And where is this interaction? Without waiting for the next thought, you jump inside the proton, close your mini eyes again, raise your mini hands, and try to feel, to find the target of the powerful interaction carriers. Being surrounded by such a quantity of energy, it takes tremendous effort to concentrate, but eventually you succeed. You manage to distinguish three things. Three blurry wave-like heavy little particles that scientists call quarks. The name may seem strange, but isn't that how all new names feel before we get used to them? No one but you has ever seen quarks right now, and they do not even exist independently. They're strong, virtual little siblings, constantly appearing and disappearing around, simply won't allow that to happen. The farther they move away from each other, the more powerful the carriers of strong interactions become, effectively bringing the quarks back much more efficiently than any other known force in nature. Therefore, life for the three prisoners inside the proton, the quarks, is quite limited, practically being a prison, with their virtual jailers being the carriers of strong interactions. What are they? They are definitely not photons. They are not part of the electromagnetic field. Remember, they are expressions of an entirely different field, the quantum field of strong interactions. And they are so effective at gluing quarks together that they are nicknamed gluons. Quarks and gluons make up all the protons in our universe. Now, something strange about this tiniest of prisons that your mini-copy has visited. Most of us believe that if one finds themselves behind bars as a human, freedom means getting as far away from the cell and the guards as possible. But for the quarks imprisoned in protons, whether they are criminals or not, it is the opposite. For them, freedom lies in close proximity. The closer they get to each other, the freer they can do whatever they please. The freedom of quarks is indeed a very strange concept. A world of possibilities opens up as soon as they come closer to one another. For the discovery of this peculiar type of freedom, 3 American scientists, David Gross, Frank Wilczek, and David Politzer, were awarded the Nobel Prize in Physics in 2004. It is indeed a difficult concept to grasp, so much so that when I met David Gross and Frank Wilczek in Cambridge a couple of years before they received the prize, I remember asking if I should ask them to refund the money I spent on headache pills earned in my attempts to understand their work. Quarks and gluons are elementary particles. Quarks are made from themselves, while gluons are the carriers of the strongest forces known to us, the strong nuclear interaction that holds quarks together, allowing them to be free only when they are close to each other, thus ensuring that the matter that makes us up does not tear apart. Quarks and gluons have truly strange names used to describe the essence of reality, so far removed from our everyday lives that it may seem quite insignificant. However, the strong interaction with its quarks and gluons involves about 99.97% of the mass that makes up our bodies. If a person weighing 60 kilograms were to instantly lose all their quarks and the binding gluons, they would immediately weigh just 18 grams and, obviously, die. To understand what humanity has learned so far about our reality, or even to figure out what it consists of, quarks and gluons are quite necessary. And this seems to me a rather compelling reason to study them, even though they will soon allow us to go back to the past, approximately 1 second after the birth of space and time. So, as we have already mentioned, the particles to which these new particles belong are called the strong interaction field, or strong field. This is, of course, a quantum field, as much of the strange quantum behavior was previously discovered involving electrons and light disappearing and reappearing somewhere else, such as in tunneling. It does not apply here. But what is important to emphasize is that although the strong interaction field is not the same as the electromagnetic field, it nevertheless fills the entire universe. This is another one of my, if you will, chi. Drops of quarks and gluons. They are electrons and photons, and nothing prevents particles from belonging to both fields. Electrically charged quarks belong to the electromagnetic field, just as they do to the strong interaction field. They can interact with the carriers of the interactions of each field using light and gluons. But at short distances, gluons are much more powerful than light. So, what about the new C? What are its fundamental particles? The strong interaction field has 6 types named after the 6 different varieties of quarks that can pop out of it at any time and anywhere if enough energy is available. Although only 2 types of them are found in the nucleus of an atom, these are the so-called up and down quarks. In every proton in the universe, there are 2 up quarks and 1 down quark. So it would be fair to say that protons have more ups than downs, which perhaps explains why they are happy in their subatomic prison. But protons are not the only existing quark prisons. As you now see, inside your gold atoms, tired of hydrogens, the mini copy jumps out onto the kitchen table, and you have sliced your treasure into pieces. The gold atom is still there. You dive into it, hidden deep beneath 79 rotating electrons. The nucleus is much larger than the hydrogen atom. To balance the charge with 9 electrons, there are 79 protons. But there are also other fuzzy spheres surrounding, separating these protons, neutral spheres. You can count 118 of them, being electrically neutral. They are called neutrons. They are also quark prisons, discovered by the English physicist Sir James Chadwick, who happened to be an assistant to the outstanding scientist Rutherford. In 1935, Chadwick received the Nobel Prize in Physics for his discovery. Inside each proton, gluons hold 2 up quarks and 1 down quark, while in most neutrons, it is the opposite. Down quarks lead 2 to 1. So, how do all these prisons come together to form the atomic nucleus? Why do they not either move away from each other or collide? After all protons are positively charged. They should repel each other. But that doesn't happen. Why? Because the strong field and its carriers do not allow them to do so. In a very strange way, through a residual effect. To find out what this means, the mini-copy makes a bold decision to closely observe the elusive gluons, the guardians of quarks inside protons. There they are. You cannot see them, but you can feel them using yogic methods. They appear and disappear to keep the quarks from wandering off on their own. But suddenly, something very strange happens. Something flies out, bursts out of the proton. But what? A gluon? Why not? After all, they are the guards. They are prisoners. But no, it is not a gluon. Nothing resembles it. In any case, you sharpen your yogic perception. Here, it turns out that gluons do not walk alone at all. They must find another gluon, a partner. By teaming up with the right companion, they transform into something else. You look around, right there to the left, between the quarks. You know, the same thing is happening. A gluon flies out of the field just like its partner. They stick to each other, and bam. Just as light can transform into an electron, 2 gluons turn into 2 quarks, a quark duet that is no longer bound to the other quarks guarded by gluons. They emerge into freedom as a new object, leaving the quark prison of which they were a part. You see the newly minted quarks moving away and heading straight for the nearest quark prison. Essentially, they have become carriers of another force that acts not on the quarks, but on the quark prisons themselves. Upon reaching it, they transform back into gluons and begin guarding the quarks there. It is through such transformations that neutrons and protons coexist within atomic nuclei, traveling from one prison to another. The 2 shapeshifters, quarks and gluons, provide stability to atomic nuclei. These exchanging particles, the quark duet, and the wandering ones in prisons are called mesons, and the force they carry is the strong nuclear interaction. This attractive force is quite powerful. The hypothesis of the existence of mesons was proposed long before they were experimentally discovered. The Japanese theoretical physicist Hideki Yukawa was awarded the Nobel Prize in Physics in 1949. The strange 300 boiling soups of quarks and gluons that can be found inside all protons and neutrons are also responsible for the missing mass we have already mentioned. Long ago, the missing mass caused stars to shine. Inside stars, as you now know perfectly well, tiny atoms fuse together to form new, larger ones. This means that stars combine protons and neutrons together, and it happens that the combined neutrons and protons no longer need as many virtual gluons to guard their quarks or mesons for protective prisons as were necessary when they existed separately. It is somewhat like merging 2 companies. Some employees become just that, and they are laid off. In the cores of stars, the excess gluons, quarks, and mesons are also expelled as they carry energy, and energy is mass. That is, the selection reduces the mass of the newly merged core. This is why everything formed through fusion is not as heavy as when taken separately. However, unlike the laid-off people, this missing mass turns into energy. The exchange rate, which equals E equals mc squared, makes stars shine. Thus, the gravitational energy in the depths of stars is used to form atoms, a process that involves mass turning into heat, light, and many other particles present around but invisible to the eye. Although much of reality is hidden from our senses, everything in the universe is interconnected. Chapter 6. The Last Force. You have already learned about the existence of two quantum fields, namely one responsible for all electromagnetic interactions, and one leading to the emergence of the most powerful force known to humanity, aptly named the strong nuclear interaction. Including the residual interaction, partly these interactions and their fields are the engines of matter creation. Although magnets can attract or repel, electromagnetic interactions ensure the preservation of electrons around atomic nuclei. Electrons could separate or collide with a bucket, but that doesn't happen. Virtual pearls of light prevent them from doing so. The electromagnetic field provides atoms with the stability of electron shells and ways to exchange charged electrons to create molecules and form the matter that makes us up. On the other hand, strong nuclear interactions take care of the atomic nuclei themselves. They hold protons and neutrons together, forming atomic nuclei. And without them, all nuclei would disintegrate, and we would instantly turn into a mist of protons and neutrons. The same goes for Earth and everything else. Finally, strong interactions keep quarks imprisoned within these protons and neutrons, binding them with the gluons flying out of the field. Thus, you have taken a journey through two fields, seen interacting particles, and the carriers of the forces that give the world a solid, albeit elusive, tangibility. You have observed photons and electrons playing, transforming into each other. You have peeked at gluons and quarks moving within the atomic nuclei of precious gold and ordinary hydrogen, the smallest and most common building block of universal matter. The very hydrogen that stars melt in their hearts to create the substance that you and I are made of. Hydrogen, the lack of which will eventually lead to the death of all stars in the universe. Reflecting on the last sentence, you suddenly remember what will happen to the sun in 5 billion years, and you immediately return to your normal size, leaving your mini copy floating in a ghetto too small for human perception. Your perception of the universe has changed dramatically since you lazily gazed at the stars from the beach of a tropical island. Now you know that there is no such thing as emptiness, that everything interacts with everything, down to the most hidden parts of atoms, created and remaining whole thanks to extraordinarily strong interactions. The sky outside the kitchen window takes on a reddish hue. The sun is setting somewhere in the west, painting the flat clouds in fiery colors. Your hand aches from holding the milk bag for too long, but now you sip a cup of cold diluted coffee. You approach the window with a distant look, gaze at the sky, and suddenly realize what it means to be part of a family of stars. All the stars in the universe emit and flood their cosmic surroundings with light and particles, all direct or indirect byproducts of the thermonuclear reactors in their hearts. And while the gravity they create in space-time bends, causing every single object, adjacent or passing by, to fall towards them, winds of light particles are blown out into space, creating a pulsation of invisible background fields that fill everything around. The universe, indeed, resembles a vast ocean, and some very serious cosmic engineers even envision building spaceships with enormous sails to catch these solar winds and steer their ships to the edges of the universe, like cosmic sailors sailing down the slopes of space-time without any fuel. Night has descended upon the earth, and you still have not stirred. The sky has cleared, and you look at the stars. There aren't many of them, although perhaps it's due to the excessive light pollution. Nevertheless, now you know that the stars you can see here are not the same ones you admired on the tropical island. Now, you are gathering photons emitted by stars living in another part of the Milky Way, and they are quite ordinary stars, enormous spheres whose gravitational energy builds large atoms from small ones by merging their cores together. Quite remarkable, rather contrary to what we humans are used to. Everything in cosmic space seems to be a creative force. It seems so, yes, because you have yet to see everything, already known to science. For this, a third quantum field is needed, a third sea filling the entire universe, just like the other two seas, carriers of fundamental interactions that are neither photons nor gluons, but mesons. And it is precisely this that can be regarded as a field that destroys, annihilating what others have created. It is the last of the four interactions governing the universe. This last interaction is also nuclear, just as strong as you have just discovered. It acts only on the components of atomic nuclei, but is much weaker than the strong interaction, and therefore it is called the weak nuclear interaction. Ubiquitous quantum fields, each with its fundamental particles and carriers of interaction, are called the quantum field of weak nuclear interaction. Spontaneous decay of atomic nuclei, a process known as radioactivity, is one of its characteristics. Now, before seeing the action of radioactivity in practice, it may be helpful to recall that it has taken the lives of many researchers, unaware that the lethally invisible light was irradiating them, slowly destroying their bodies. They worked with raw, highly radioactive materials with bare hands. The remarkable French scientist of Polish descent, Marie Curie, the only two-time Nobel Prize winner in physics in 1903 for her joint research on radioactivity, and in 1911 for the discovery of two new elements, radium and polonium, was one of them. She may not have known what caused her death, but what you are about to witness will be just what both saw. With today's knowledge, along with the convenient ability to turn into less than Marie, you pour the cold coffee down the sink. You shrink back into your mini-copy, and your eyes take a moment to adjust to the darkness. You are back next to the gold atom, right in front of you, and it is so strong and solid that creating it would require more energy than is needed to attract stars. Gold is created during the life and death of stars in an explosion when our sun dies. It too will create some gold. Who knows? Maybe one day a ring will appear on the finger of tentacles of unknown beings in the future. But as you examine it, this atom does not look nearly as valuable as it seems, as significant parts of humanity believe. So what makes gold so desirable? Does its value change over time? Do passing atoms catch it to create extraordinary molecules? You wait a while, observing to see if that is the case. But no, nothing happens. But of course, the fact that nothing ever happens to gold is one of the reasons for its value. Gold does not rust. It does not oxidize. What happens when the electrons of an oxygen atom bond with the atoms of metal? It is not subject to corrosion. Gold is the most ductile of all metals. If you have a sufficiently large piece, you can draw it into an extremely long, thin wire. Platinum and silver will break long before that. From many gold atoms, one can easily create something in virtually any shape, and whatever it is, it will still conduct electricity. This means that an electron introduced at one end of a long chain of gold atoms will make its way through and exit at the other end. All these exceptional properties can lead to practical applications, not always ending in a wedding ring, but invaluable nonetheless. Add to this the fact that gold is a rare, hard-to-extract metal obtained from the death of a star, and it becomes clear why it is so expensive. So let's leave it alone, because indeed, nothing ever happens to it. To see something different, another atom will be needed, which, strangely enough, is passing by, and it is much larger. As far as can be said, it has 94 electrons rotating around a nucleus made up of 94 protons and 145 neutrons. 239 quarks are tangled in it, and it has 42 more than gold. This atom is one of the forms of the notoriously known element called plutonium, and since it has 239 quarks, it is called plutonium-239. There are other types of plutonium, just as there are other types of gold besides the one that was discovered in your kitchen. They may have more or fewer neutrons in their nuclei, but always the same number of protons. Otherwise, they would cease to be plutonium or gold. And since studying gold is not as interesting, something tells you that a strange phenomenon will soon occur inside the nucleus of plutonium-239. Without hesitation, you pass through its electron shell layer by layer, crossing vast voids filled with virtual photons. Here is the nucleus. 239 quarks are right in front of you. The strong nuclear interaction has arranged them in a neat stack, but your intuition suggests that the target should be one of the neutrons. You dive inside. There are 2 down quarks and 1 up quark, tightly held together by strong forces. However, just at the moment of your arrival, a suddenly appearing virtual particle, which you have never seen before, strikes one of the down quarks, only to turn the down quark into an up quark belonging to its neutron. Thus, it immediately becomes a proton, creating chaos. Now the entire atomic nucleus is out of balance. The effect is instantaneous and dramatic. Your sixth sense tells you to escape. The mini-copy flies out of the nuclear electron shells, having managed to see the multiple decay of the plutonium nucleus into smaller parts, which sometimes try to take a few electrons with them. Super-energetic particles fly out at every stage of the process, including yet another one you have not seen before. Plutonium has decayed right before your eyes, and all the products of this decay are now flying apart like fireworks, ultimately destroying themselves, not counting the other plutonium-239 atoms around. But there is no longer any in your kitchens. Everything quickly settles down. You have just witnessed one aspect of the 4 known forces of nature, the weak nuclear interaction with its virtual interaction carrier particles capable of transforming quarks into one another. These interaction carriers are called W and Z bosons. What you have just seen is the decay of an atom into smaller and more stable atoms. This was spontaneous fission of the atomic nucleus, the direct opposite of its fusion, the process of radioactive decay. What is radioactivity? Weak nuclear interactions are responsible for it through the carriers of W and Z bosons. Wolfgang Pauli, the same Pauli who came up with the exclusion principle, studied such atomic decay nearly a century ago. Unlike you, he was unaware of the existence of neutrinos, but by comparing what he observed before and after radioactive decay, he realized that some energy was disappearing. Thus, he hypothesized the existence of an unknown particle responsible for the energy capture, a particle with an extremely small mass and no electric charge. This particle is so elusive that after its emission, it passes through all known matter almost effortlessly. It is now known that this new particle exists. You just saw it. Of all the particles emitted during radioactive decay, this is the only one that had never been seen before. It is called a neutrino. American physicist Frederick Reines and his colleagues experimentally proved its existence in 1956. Almost 40 years later, in 1995, Reines received the Nobel Prize in Chemistry. He once stated that neutrinos are the smallest particles of reality ever conceived by a human being. Today, we know that these neutrinos, of which there are many, only interact with the weak nuclear force and gravity. They are completely insensitive to electromagnetic fields and strong interaction fields. From their perspective, atoms are just as empty as they may have seemed to you at first glance. And that is a good thing. Why? Because if neutrinos interacted with atoms, we would have serious problems, as they are produced in vast quantities within the sun. More precisely, an estimated 60 billion neutrinos collide with every square centimeter of your skin every second, and they do not even notice you. No one does. However, as unfortunate as it may sound, to them, there is no difference between you and anything else. They pass through you, then through the Earth, and continue their journey through space as if you and our planet never existed. Furthermore, we have all been taught that radioactivity is dangerous, that we should avoid radioactive materials like plutonium, uranium, radium, or polonium whenever possible, and rightly so. But since neutrinos do not distinguish between you and anything else, there is no need to fear them. The reason lies with other particles emitted during the process of radioactive decay, and fortunately, you are already familiar with them. When the nucleus of an atom decays, it splits and can emit neutrinos, quark prisons, and electrons. Light, the last trio, the most dangerous and largest part of the three, in turn, consists of a bundle of 4 quark prisons, 2 neutrons, and 2 protons. It is called an alpha particle and corresponds to a helium atom devoid of electrons. Therefore, for the nucleus to become an atom, it must steal 2 electrons openly. A trick it can perform in several ways. It can snatch a couple from a neighboring atom, altruistically share with a neighboring atom, or benevolently capture stray electrons. In the first case, the electron-deficient atom begins to seek out other electrons. If living beings, like you and me in the kitchen, happen to be nearby, a strange chemical reaction may occur with the electrons stolen from the atoms of your skin, leading to so-called radioactive burns. That is why alpha particles are dangerous. The second type of particles emitted during radioactive decay, beta particles, which are emitted, for example, during radioactive decay, are charged electrons that can push out other electrons, leading to the same danger. The last ones are high-energy photons, gamma rays. We encountered them in the previous cosmic journey, noting their incredibly high energy frequency. When a gamma ray hits an atom, it can strip it of one of its electrons, turning the atom into one that seeks another electron. thereby creating burns on our skin again. But gamma rays can also have far worse consequences. Nothing compels them to stop at the surface of our bodies. They can penetrate into us and cause local chaos deep inside, not only ejecting electrons from atoms, but also breaking molecules, like DNA molecules in the very heart of cells, thereby altering the commands used by the body to sustain our lives. The usual result is cancer and/or genetic mutations. All these potential consequences are frightening. It would be hard to argue otherwise. But there is a silver lining. Like gravity, electromagnetism, and strong interaction, radioactivity, even as a destructive force, is a natural process that occurs always and everywhere, even within your body, at a very slow rate. There is no need to worry unless someone is exposed to high levels of radiation. In fact, we should be grateful that radioactivity exists at all. It can kill, but primarily, without it, you would not be here. Deep beneath your feet, our planet contains countless atoms that are constantly decaying. There are fewer of them now than in the past, but the Earth's mantle is still radioactive. When atoms decay, the emitted neutrinos collide with their neighbors, generating heat that significantly contributes to the heating of the planet. Without radioactivity, there would be no seismic or volcanic activity. The surface of the Earth would have become a dead, icy place a billion years ago. Life, as we know it, would not exist at all. Radioactivity destroys atoms. Radioactivity kills. But it is necessary to warm our world, returning a portion of the energy accumulated by stars within the atoms that formed our home planet. And finally, some brief comments before allowing you to embark on a journey to the origins of space and time. Nuclear energy, through the fission and fusion of atomic nuclei, harnesses immense energy, and humanity is trying to harness it with varying degrees of effectiveness through nuclear installations. We can only hope that such technologies will one day become environmentally friendly and safe, as the potential is astounding. Despite the rather negative press and the unjustifiable use of nuclear energy in the past, we must not forget that without it, our existence would be impossible. Without radioactivity, life on Earth would cease. This is life as we know it. Part 5. At the Origins of Space and Time. Chapter 1. Confidence. When I began to take an interest in what some would call classical theoretical physics, I was 22 years old. I had been studying pure mathematics for several years and loved it for its beauty. As the Greek philosopher Plato said 25 centuries ago, when no one had any idea what was happening in the heavens, mathematics is the language with which God speaks to man. When I enrolled at Cambridge University to study mathematics and theoretical physics in depth, I immediately thought, great, time for deep reflection. And I knew as little about the real world and what would happen to me as you probably do about what will happen to you in the following chapters. During the summer preceding my first year at Cambridge, I read several textbooks, as well as works by scientists of the past and present, to gain a clearer understanding of what science could say about the world around us. I paid special attention to the study of the quantum world. After all, as we discovered in the fourth part, the micro world underlies everything we are, and it is there that we found the building blocks of everything contained in the universe. Moreover, to use Einstein's general theory of relativity, one must understand what the universe contains. Otherwise, its equations will not tell you how it looks on a large scale. Many Nobel Prizes in physics have been awarded to scientists for breakthroughs in the study of the micro-world. Naturally, I was very excited about the upcoming education, and as soon as I began to engage with the theories of these pioneering thinkers, I started jotting down some of their incredible statements to ensure I understood them correctly. I believe I can confidently say that no one understands quantum mechanics. Richard Feynman, the Nobel Prize-winning physicist of 1965, said, "God is subtle, but he is not malicious." Albert Einstein, the Nobel Prize-winning physicist of 1921, noted, "No language suitable for visual imagery can describe quantum jumps." Max Born, the Nobel Prize-winning physicist of 1954, asserted, "Anyone who was not shocked when they first encountered quantum theory probably hasn't understood it." Niels Bohr, the Nobel Prize-winning physicist of 1922, added, "Maybe God is indeed malicious." Such statements from the founding fathers of this branch of science are enough to shake the confidence of even the most self-assured students. Nevertheless, along with 200 other young men and women from around the world, I attended awe-inspiring lectures, went through what was once called the third part of the mathematics tripos, possibly the oldest mathematics exam on the planet. It consisted mainly of pure mathematics problems, and the volume of new material we were studying was so vast that we had little time to truly reflect and philosophize in general. Then came the momentous day. 9 months after my arrival at Cambridge, Professor Stephen Hawking, one of the most renowned and brilliant physicists of our time, offered me the opportunity to become his graduate student in the study of black holes and the origins of the universe. Deep reflection was part of the curriculum, so I spent the next few years gaining an entirely different perspective on everything I could encounter. But well, absolutely everything. And to a significant extent, the guests at the point you have reached in the book have such a scientific supervisor as Hawking. I was going to gather everything I had learned and achieve much more. Now it is your turn to do the same. And what remains to be seen? Well, here's a teaser. In 1979, a special Nobel Prize in Physics was awarded to 3 theoretical scientists: Americans Gordon Liddy, Steven Weinberg, and Pakistani scientist Abdus Salam. For many years, scientists had been trying to understand some very specific aspects of the weak nuclear force that you have recently observed. Gell-Mann, Salam, and Weinberg discovered something incredible. The electromagnetic and weak interactions are nothing but 2 aspects of the same interaction, the same field that existed long ago. They found that in the early days of the universe, at least 2 of the invisible quantum seas filling our reality were one so-called electroweak field. The discovery itself was an extraordinary breakthrough, hence the Nobel Prize. But it also paved the way for something much greater: the enticing prospect of unifying all known forces of nature into one coherent theory. The quest for such unification lies behind everything you will experience from this moment until the end of this book. I mean this goal. You will reach the origins of space and time, into a black hole, and even leave the boundaries of the universe. However, to get there, we first need to figure out what remains if we remove all its contents. Chapter 2. There is no such thing as nothing. You are still in the kitchen. The night is dark. I am quietly eating. You used to think the world was beautiful, but with the baggage acquired during your travels, everything has completely changed and seems somehow deeper, charged with the power of mystery. Even your humble kitchen, the air around filled with floating atoms, gliding down the curve of earthly space-time. Atoms that were originally created in the cores of long-dead stars. Atoms within you, everywhere splitting due to radioactive decays. Beneath your feet, the floor is electrons that refuse to let you in, allowing you to stand, walk, and run. The Earth, your planet, a chunk of matter created from 3 known quantum fields held together by gravity, the so-called fourth force. Although it is not a force, it flows within and through space-time. All this sounds so absurd or wonderful that you decide to brew yourself another cup of coffee and head to visit the cozy, solid, comforting old couch. You try to sort through all the thoughts swirling in your mind. Perhaps somewhere beyond where we have already been lies the meaning of life. And does what you have encountered so far make sense? Before venturing into places even more distant than those seen so far, let me say this. The mystery of the world is far from solved. Science cannot provide answers to all questions, although it has many. In fact, they depend on what your expectations are. So here, I must warn you, there may be less meaning at the end than at the beginning. American theoretical physicist Edward Witten once said, "Excluding the safety of your home, the universe is not designed for your convenience." It might be worth keeping this phrase in mind as you embark on an absolutely uncharted voyage. Because, as humiliating as this statement may sound, it offers all of us an extraordinary freedom to interpret what we see in our own way. And that is good. The more diverse perspectives, the better for humanity and for science. Now, as I hinted at the end of the last chapter, before we confidently open the door to the unknown, it is necessary to familiarize ourselves with the concept that scientists call the vacuum. It is the foundation of how our quantum reality is currently understood by theoretical physicists. It is a mental construct that has helped us make incredibly precise, repeatedly verified assumptions through countless experiments. Take any place, a region of the universe, rid it of all its contents, and I mean everything at all. Strangely enough, what you are left with is not emptiness. Even if you meticulously cleared everything out, does it make sense? Hardly. But nature does not care what we consider reasonable. So now close your eyes. Why? Because some things around us do not tolerate observers, and the vacuum you are about to encounter is one of them. To make sure you are ready, take a moment to relax and think of an airplane flying home from a beautiful tropical island. You may remember that you fell asleep right after takeoff. And indeed, if you were to ask that strangely looking neighbor, he would probably tell you that for most of the flight, you were snoring loudly. So what exactly happened during the flight while you slept for 8 hours? What time zones did you cross on your way? Interestingly, what path does any flying airplane take when no one is watching it? All you know about the flight is what you observed before falling asleep and after waking up. You looked out the window and saw the plane lift off from the runway of a distant island, and later it safely landed at home. In the interval between these events, your brain retained absolutely no impressions of the flight path. You simply do not know what happened. Now, what if someone told you that the plane took quite an unexpected route through Jupiter, for instance, or through the Earth? Like neutrinos, 3 weeks forward or backward in time. I assume it would be hard to believe. However, whether in a dream or not, you made such a strange journey 300 years into the future, to the future of Earth in 8 hours of your own time. Thus, we must look at what happened more clearly. Now you know that if this had actually happened, your plane would have had to fly at an extremely high speed. Moreover, it would have had to venture far into space at near light speed before returning to Earth nearly 300 years later. In real life, you can find compelling arguments against such a route or other similar strange flight paths. But still, what if I told you that while you were asleep, the plane not only made a flight to and from space, but also simultaneously took every possible and impossible route from there, from the moment you fell asleep to the moment where and when you woke up, through the Earth, back, around Jupiter, and back, every possible route. You probably will never take my words seriously again, right? Good. This means you are finally ready to look at the vacuum. Coffee, vases, couch, home, everything fades away. You return to a world that can only be visited by the mind, and you are something slightly more than a shadow. Completely transparent, barely having outlines, impervious, not affecting the surroundings. Nothing. However, what surrounds you is not entirely clear. As far as you can tell, there is nothing here, only darkness extending into infinity. Already accustomed to such a sharp change of scenery, you drift slowly, as it closely resembles a universe cleansed of all contents. At first, it is quite soothing, but soon, admit it, it becomes boring with nothing to do. You begin to rethink what I just told you about the dream on the plane. Can a real plane, really fly in a completely unpredictable manner? Impartial judgments about various emerging routes are one thing, but a real flight through the center of the Earth or back and forth in time? Well, come on. What? Well, you are right. Come on. The only natural reaction to such a ridiculous thought. And yet you must remain impartial, as what may seem crazy for a plane can be very real for particles. So let's start thinking about particles that no one is observing. Imagine them moving from one place to another, only discovered by you at the endpoints of departure and arrival. Now the same question again. If you cannot see, what trajectory do particles take to get from one point to another? Of course, it depends on... No, regardless of the plane. The idea may seem abstract, but for particles, it is a fact. A particle indeed takes every imaginable path, whether rational or not, until someone observes it. Particles move and behave quite differently than anything you have ever seen or felt in everyday life. You have probably already gotten an idea of this during your observations of the internal structure of an atom. We see that electrons and everything else are not just spherical blobs of matter. Now we approach an even deeper truth. Quantum fields do strange things to particles. Belonging to a quantum field means that particles are indeed doing what they constantly divide into multiple images of themselves, and the paths chosen by all these images fill every spot in space-time. Do you have any chance of reality, and only the probability of finding a particle at that specific place and time where you mentally try to detect it? What's worse, before the detection of a particle of matter or light, they can split and become something else before turning back into the particle they were originally. Just as light can become an electron, and electrons can become light, all particles in the universe can transform into something else while we are not watching them. Quantum particles are cunning gnomes. Everything that can happen happens if nature is left unobserved. And if you don't believe me, see for yourself. Something is happening with the endless night of space in which you are drifting. A white cube in the form of a room without doors begins to materialize around you, and soon you find yourself inside this room, whose walls are covered with tiny, completely white sensors. Millions of sensors. Right in front of you, at the center of this windowless and doorless room, stands a vertical metal column, reaching from floor to ceiling. The only other thing in the room besides it is a yellow machine that looks like one of those mechanical devices for throwing tennis balls. A tennis ball launcher. This nondescript little robot seems to be looking at you through a pipe opening. Apparently programmed for politeness, it says, "Hello." You respond, preparing to ask it a question just in case. The robot interrupts you, explaining that it is filled with buzzing particles, which it will now eject one by one to the opposite side of the room. If you inquire whether these will be particles of light or matter, the answer will be, perhaps, that's how you will find out. Matter and light, for the most part, will behave the same way. Apparently, unable to wait for a response, the robot immediately starts a countdown. 3, 2, 1. The pipe ejects particles, and a moment later, a signal sounds on the other side of the room. You get a strange feeling that the robot is quite pleased with itself. You lean slightly to the side and see that one of the sensors behind the metal column has turned black. Question number 1. How did the particle get there? The machine asks, ignoring its colorless, mentor-like tone. You walk across the room, stopping in front of the robot. A straight line connects the point from which the pipe spat out the particle to the blackened sensor. The straight line of this visible trajectory almost touches the metal column, but not quite. There, I have the trajectory, you declare, raising your finger to point to the only possible direction the particle could have taken. Incorrect, the robot immediately responds. What? You ask, surprised. The answer is incorrect, regardless of the directions taken, the robot states, making you rethink its supposedly programmed politeness. But there is only one possible path, and I am currently looking at it. Relying on your senses and intuition, the machine continues. You will continue to answer incorrectly. Every person who comes here for the first time makes the same mistake. The laws of quantum particles do not conform to those that govern your everyday life. Your senses and intuition cannot be applied to particles. Forget about them. However familiar its address may seem, the robot is completely right. Despite its rather unremarkable appearance, it plays the role of the most advanced computer in the world in this book. And just as computers are often the best friends of scientists in real life, helping visualize their theories, our robot supercomputer will be useful in the remainder of the book. It can simulate everything that obeys the laws of nature. In the known form, the white room you are in, for example, is created by a computer, but everything happening in it follows the known laws of nature. Now it may seem that the particle thrown by our robot flew perfectly straight, but particles belong to the micro world, and therefore are beyond common sense. The computer said you were wrong because what just happened had nothing to do with what the eyes can detect or how developed your logic is. The computer speaks of nature, and nature in this matter expresses itself clearly and distinctly. Quantum particles do not behave like a tennis ball, but as quantum particles. To move from one place to another, they take all possible trajectories in space-time until those paths connect their starting point to the end point. The particle released by the robot literally traveled in every direction simultaneously, to the left and right of the column, through the wall, and out of the room. Their future is back until it hits the sensor on the wall. Don't worry, you don't have to understand. In fact, It doesn't matter whether you understand or not. It's just how nature works. Particles, whose actions are not observed by anyone, indeed traverse all possible paths offered by space-time. The metal column in the center of the room does not change anything. In fact, it is there only to convey the main idea visually. Remove it, and the particle will still travel to the left and right of it. The walls and sensors on the other side made the difference. By hitting one of them, the particle eventually allowed itself to be detected somewhere. The yellow robot next to you begins to tremble and heat up. You wonder if it has broken down. But anticipating this, it suddenly starts to speak. Everything is fine. I am slowing down time. This takes energy. The next time you blink, I will eject another particle. You will see what the room would look like if it were possible to notice all the particles traveling from the pipe opening to the wall. Unbeknownst to you, you have inadvertently become a witness, and the robot indeed begins a new countdown, and the flow of time starts to slow down. A particle flies out of the robot in slow motion. At first, it appears as blurred clouds, changing position, finding itself right behind the robot. You see the particle splitting into what seems like an infinite number of residual images of itself. This is a real wave, a pulse spreading across its background field in all directions of space-time, including to the right and left of the column, through it and the room's walls, splitting into as many possibilities as the mind can conceive before suddenly focusing into a single point at the other end of the room. Upon hitting another sensor, a signal sounds. The sensor malfunctions, and time resumes its normal speed. What you just witnessed, courtesy of computer modeling in the White Room, is what scientists believe happens to unobserved particles when someone observes them. The set of rules changes. When radars track an airplane throughout the flight, the airplane cannot be in any other position but fixed. Similarly, when a sensor, like the one on the wall, tries to detect a particle, it is no longer everywhere, but somewhere. However, unlike an airplane with passengers inside, when no one is watching, particles are indeed everywhere. At first glance, this may resemble the fallen tree in the forest. If no one heard the sound of its fall, did it make a noise? And since we are talking about it, did it really fall? But we are not discussing philosophy here. We are talking about nature, about what these particles surrounding us are made of and how they behave. Furthermore, why does the nature of particles matter, whether they are observed by a person or not? Well, many scientists have pondered this question, and it has led some of them to some crazy answers, which we will encounter later in the 6th part. For now, it is enough to say that what you just observed turned out to be true. After countless experiments, particles first appear everywhere, and then they are no more. In the robot model, the sensors, by observing, force the particles they ejected to move away from the wall, somewhere in the room. If you are confused, you are right, says the robot. I showed you that the very act of probing reality changes its nature. Excuse me, what did you say? You ask, frowning. Reality changes when you observe it, the robot repeats dully. You are right to be confused. It seems that the microscopic quantum world is a mixture of possibilities. Quantum fields, to which all particles belong, are the sum of all possibilities. For some reason, out of all the existing options, only one is chosen. Simply the observed one, merely due to the act of detection itself. This happens every time someone attempts to explore the nature of particles, and no one knows why or how this occurs, but the result is always the same. Diversity becomes singularity. When you interact with the quantum world, it seems that everything you could or could not have in your life on a given topic suddenly reduces to just one. When someone hears you pronounce a word, the sensors on the other side of the white room do the same. They force the particle emitted by the robot to ultimately come to a stop somewhere. They continue to wander everywhere, stripping it of its universal character. As soon as the possible consequences, the facts, begin to reach your consciousness, your skin breaks out in goosebumps. Even if you are just a shadow, could it mean that, with the right detection device, you can create your own reality simply by trying to detect particles? Could you make them, and matter itself, move in such a way as to shape the entire universe to your will? Vidon said that the universe is not made for your convenience, but perhaps he was mistaken. Before you start boasting, I'm very sorry, but I must tell you that Vidon was ultimately right, and the newly acquired power is an illusion. You cannot create a universe because, despite all the possibilities of the quantum world, it is impossible to predict which of them will become real after detection. And this is part of the magic of the fields that form universes. The quantum world transforms what we considered certainty into possibilities or probabilities to conduct experiments, the results of which no one can guess with complete confidence, just like flipping a coin in the air or rolling dice. Scientists thought that this uncertainty was related to gaps in their knowledge, but it was later proven that this is not the case, thanks to the famous theorem published in 1964 by physicist John Stuart Bell from Northern Ireland. His inequality allowed French physicist Alain Aspect to experimentally demonstrate that the existence of possibilities instead of certainty is a property of the micro-world that simply must be accepted. And that's fine. But what does all this have to do with the vacuum you were about to explore? Well, that's precisely what you are going to delve into now. The sensor-filled white room disappears along with the metallic pillar in the center, and without even bothering to say goodbye to the yellow robot, you return to the middle of what seems to be a cosmic night, alone, surrounded by nothingness. You have shrunk to the size of miniatures and observe some movement. It's like eating, haphazardly, and cleansing oneself, perhaps even two. You are quite sure that a line just appeared, interrupted before disappearing in a flash of light. There was nothing around. Then something appeared, and then there was nothing again. Strangely, this happens over and over again, countless times. Everywhere, what you observe seems to be the spontaneous birth of particles from nothing, and before they disappear for some reason, these particles take all possible paths they can traverse. Quantum freedom. You may allow yourself to accept the last part of this statement. You saw it in the white room, how quantum particles behave uncontrollably. But how do they manage to just fly out of nothing? Well, they are surrounded by not nothing. Quantum fields exist around them. For particles to arise, they need to borrow some energy from the quantum fields. And since these fields fill any place in space-time, particles can literally appear anywhere and at any time. That's why there is no such thing as true emptiness anywhere in the universe. You continue to look into the darkness, and suddenly, as if a blindfold has been removed from your eyes, the truth and its contents are instantly revealed before you. Particles merging everywhere, filling everything, shooting through the boiling background field, pulsating loops of virtual particles, moving and interacting with each other, appearing and disappearing in flashes of light or energy. An unusual fireworks display occurs everywhere, leaving no spot empty. It is practically the complete opposite of what you probably once thought filled the vast emptiness of cosmic space. And this is precisely what scientists call a vacuum. It is what remains when all quantum fields are removed at their lowest possible energy level, with virtual particles spontaneously flying out of them only to move everywhere before retreating back into nothingness. Once again, I repeat, there is no such thing as emptiness in the universe from which everything has been removed. How could one expect that nothing would remain? But the fact is that just as it is impossible to extract space and time from anywhere, it is also impossible to extract the vacuum of quantum fields. But if there is truly no emptiness in the vacuum, if the vacuum of the quantum field is defined by the omnipotent particles that fly out of it, then a rather logical question arises in your mind. Is the vacuum the same everywhere? Or can nature change depending on the place? Please use the plural form grammatically. There are many vacuums. In 1948, Dutch physicist Hendrik Casimir hypothesized that the vacuum, defined as described above, is a real fact of the universe, not just a theoretical fiction, and that various types of vacuum must exist around us, and they should also have a very specific influence on our world, an effect that can be detected. Imagine a wall on roller skates separating an air-filled room from another room filled with water. One would expect to see the wall flickering, pushed by the water pressure, moving on its rollers towards the air-filled room. Now imagine two tiny parallel metal plates facing each other. If left to their own devices, just like the truth separating the water-filled and air-filled rooms, they should move, repel, or attract each other due to the difference in the vacuum separating them and the vacuum in the free space between them. Why? For the simple reason that there is more space outside the plates than between them. Therefore, the virtual particles flying out of nowhere between the plates differ from those appearing outside, which makes the vacuum different. As a result, the plates should move, and they do, which was experimentally proven in 1997 by American physicist Steve Lamar and his colleagues. This phenomenon is known as the Casimir effect. The Casimir effect confirms that emptiness does not exist and goes further to show the existence of different types of vacuum that can lead to the emergence of force. Vacuum forces. By the way, you may have already noticed that you just found the solution to a rather complex puzzle. As you have recently learned, these particles in the universe are nothing more than expressions of quantum fields. They are like waves in the sea. They resemble balls tossed into the air. They are simultaneously particles and waves generated by the quantum field to which they belong, spreading through it. Now recall how, while exploring the micro world, you noticed that all fundamental particles you encountered were always the same, and any two electrons invariably turned out to be absolutely identical. How could this happen? In everyday life, such perfection simply does not exist. No matter what you do or build, no matter what you look at or think about, there are no two perfectly identical objects or people, not even twins or birds or thoughts, nothing. Even if objects look identical, they are not identical. So how is it that all electrons and other fundamental particles are always absolutely and completely identical to any other of their kind? The answer is that all elementary particles throughout the universe thrive on the same objects that can swallow them back at any moment. in the vacuum of the quantum field, in the invisible background seas that fill the entire universe. All electrons are identical expressions of the electromagnetic field. They all fly out of its vacuum, spread within it, and so do all photons. Every time an electron becomes real, it awakens from its ghostly lethargy as a result of a surge in the surrounding vacuum of the electromagnetic field. Every time a gluon appears, it arises from some energy given or taken from the vacuum of the strong interaction field. Every time radioactive decay occurs, the vacuum of the weak interaction field is involved, from which elementary particles are shot out. And the more energy the vacuum possesses, the more elementary particles can fly out of it. All right, we are getting closer to the topic. Let's continue. It seems that all fields behave the same, that they all obey the same laws. Now, what about gravity? Wherever there is gravity, there are also gravitational fields. Although this field is different, at least for now, because no one knows how it can be quantum. As you will see later, no one knows how to make particles fly out of the vacuum of the gravitational field without creating catastrophic problems. But if it were possible, gravity would have its own particles that, like those of all other fields, would indeed fly out of the gravitational field, carrying its interaction. These particles are called gravitons. They have not yet been discovered, and the curved space-time remains the best way to explain the action of gravity. But even without gravitons, and even if it is not quantum in nature, gravity is still a field. Thus, the total number of fields used by humanity to describe everything is known to be 4. But why 4? Why should there be 4 fundamental fields? Why not 5, 10, 42, or 17,900,208 fields to explain the behavior of nature? And what about the corresponding vacuums? Perhaps they simply coexist, unaware of each other's presence. Sounds strange, doesn't it? Wouldn't life be simpler if there were only one field? Would it? Just what theoretical physicists always strive for early captivates their imagination, and therefore they have not attempted to unify the 4 aforementioned known fields into one, a single field that governs all, you might say. Although it is easier said than done. The elementary particles of each field are not the same, and one of them, gravitational, does not have any discovered particles at all. And the excitation of one field leads to different consequences compared to other fields, and they do not imply the same electric charges and do not actually possess the same properties at all. For example, the magnetic field has a wide range of action and can attract or repel, while the gravitational field only attracts. And the strong interaction field has a very small range. Yet, to create an alloy of 2 different materials, they must be heated. If this is done at a sufficiently high temperature, they merge into something completely new, a new material that combines the properties of both. The theory may also work for the merging of fields, but it would require an unimaginable amount of energy to combine the electromagnetic field and the weak nuclear interaction field into one. It would require a temperature of around 1,000,000 billion degrees. 1,000,000 billion degrees is certainly beyond the limits of nature as we know it today. But it may not always have been so. In fact, such an enormous amount of energy existed long ago when the universe was younger and smaller. And those who tried to figure out how nature behaved back then, Glashow, Salem, and Weinberg, managed to unite the electromagnetic field with the weak interaction field, thus discovering the electroweak field. They found that under extreme conditions, one field contained the two fields that today separately govern magnetism and radioactivity. The next step is to unite this new field with the third known quantum field, the strong interaction field, which governs the interaction of quarks and gluons within atomic nuclei. By doing this, we could create something grandly dubbed the theory of grand unification. To bring it into existence would require even more energy. How much more? An astounding amount, so unimaginable that adding a couple of billion degrees would make little difference. And so, how do we know this is real? How do we know that Salam, Glashow, and Weinberg were right? And aside from the feeling that one field is more sensible than three or four, how do we know that a theory of grand unification is truly expected to be discovered in the end? Because physicists predicted that when uniting fields to create one new one, it should have its own fundamental particles and force carriers. To test this, particle accelerators were built in which already existing particles collide with each other. In such colliders, particles not only break apart, showing us what they are made of, releasing enormous energy in the process of collision, but also excite all the resting fields of our universe. The maximum energy achieved in such collisions as of 2015 corresponds to the mark of 100 million billion degrees. It sounds like an enormous amount of energy, but it is important to remember that we are talking about particle accelerators. They do not accelerate cows or planets, but incredibly tiny particles. In real terms, the energy produced by the collisions of microscopic particles would barely be more powerful than the flight of a mosquito. Locally, however, the energy released is immense. And, as predicted by Salam, Glashow, and Weinberg, completely new particles emerged, particularly the W and Z bosons, particles that only make sense in terms of electroweak interaction. I don't know about you, but such achievements never cease to amaze me. And what is the role of gravity in all this? To turn four fields into one, gravity must play a specific role. So why was it left out? The answer to this tricky question will be the goal of the seventh part of the book. Don't be impatient, because from what you have seen so far, you have learned almost everything necessary that makes up matter, with one big exception: mass. Since we are at it, one might wonder why you haven't heard about this before, as it seems to be quite an important topic, doesn't it? So where does mass come from? As you know, in their cores, stars create large atomic nuclei from small ones. So, do stars create mass? Actually, not quite the opposite. By ejecting excess gluons during the fusion process, neutrons and protons lose some of their energy, sequential mass, as Einstein's equation EEmc2 states, thus creating a source of energy that makes stars shine. You have seen this happen. But the equation also asserts something else. If atomic nuclei lose mass by getting rid of gluons, then gluons were indeed that mass, which indicates that part of the mass of an atom comes from the very existence of the soup of virtual gluons that keep quarks imprisoned. In fact, when scientists closely examined this hypothesis, they realized that the energy of the gluon soup existing inside all the neutrons and protons of the universe accounts for not just some part, but a huge fraction of the mass of the matter we know. A huge fraction, but not all the mass. The equation does not explain to us, for example, why quarks and electrons have mass, or rather, how they acquire it, because at one time they were massless. Salam, Glashow, and Weinberg showed that long ago, when our universe was still extremely young, it expanded and cooled. The electroweak field split into the electromagnetic field and the weak interaction fields. But I didn't tell you before that this should give rise to another field, another quantum field with its own interaction carriers. These carriers cannot convey any of the forces we have encountered, and there is no other force. So what do? Well, they give mass to some particles while leaving others massless. Photons and gluons, for instance, have never felt and do not feel the presence of mass. They can travel through their field. Hence, they remain massless and continue to move at the speed of light. But quarks, electrons, and neutrinos did notice its presence and acquired mass, so they can no longer reach the speed of light. Again, how do we know this is true? How do we know that this mysterious field is responsible for the mass of these particles? Well, like all fields, this new field must have its own fundamental particles. However, as expected, they are not so easy to see or detect. According to calculations, it would take an enormous amount of energy, even more than for the electroweak field, to awaken the sleeping field and bring its fundamental particles into existence. Nevertheless, in 2012, astonishingly enough, scientists managed to do just that at the most powerful particle accelerator at the European Organization for Nuclear Research. In U mode, they discovered a fundamental particle belonging to this field. It was the missing piece of the puzzle, known as the origin of all the known mass of the universe. Whether due to gluons or not, it indeed confirmed that physicists were on the right track from the very beginning. The media calls this discovered particle the Higgs boson, although there may be many different kinds, and the field that produced it is known as the Higgs field. British theoretical physicist Peter Higgs and Belgian theoretical physicist François Englert instead received the Nobel Prize in 2013 for their discovery, which was predicted over 40 years ago, along with Brute, who unfortunately passed away in 2011. In other words, they discovered how 13,800,000,000 years ago, when our universe cooled, a portion of mass arose, a highly impressive achievement for them and all of humanity. Despite the fact that the discovery caused a sensation, it must be reiterated that the Higgs field does not account for the mass of everything we are made of, only for a portion of it. The majority of the mass of neutrons and protons comes, as mentioned earlier, from the force holding quarks within their boundaries, and from the quark-gluon soup occurring there. If the Higgs field were to suddenly shut down, quarks would become massless, and we would die. But the mass of protons and neutrons would hardly change. Now that the role of the strong interaction field in possessing our being mass has been proven, when you know where all the mass of all known matter comes from, recall all those particles you saw flying out of the vacuum earlier in this chapter. You saw them, but you weren't supposed to. Nature does not allow particles to appear on their own without paying the price. This price, as you will now see, is the existence of a new type of matter called antimatter. Chapter 3. Antimatter. For nearly all of Earth's history, its surface was virtually unknown to human beings. Today, we can easily access satellite images of the entire planet. But just as now, several centuries ago, when only a few patches of land in Europe, America, and Asia had been mapped by the people living there, the world was absent. Therefore, fearless explorers from many civilizations had to leave safe shores and sail through storms and tempests to find out what, if it existed at all, lay beyond their homeland. One by one, they discovered remote pieces of land that had never been touched by human feet. They also discovered other civilizations, small territories surrounded on all sides by water, called islands and large continents. Each discovery expanded the realm of humanity, and at the same time, it pushed further. Our ancestors understood a very simple fact. We all live on the surface of an incredibly rich but rather small ball flying through the vastness of the enormous universe. Decades passed, traversing a mix of violence, greed, and curiosity, and Earth became better known. The unknown gradually shifted from what lay somewhere beyond the horizon to everything above our heads. The cosmos became a new mystery that anyone could ponder simply by looking up. But the distances within it are mind-boggling. While this book was being written, anthropogenic satellites were sent hundreds of millions of kilometers from Earth to try to determine the origin of water and possibly the building blocks of life itself on our planet. People have stopped going on risky adventures. Robots do that for us. But since the excitement about interplanetary travel is back in vogue, is it possible in the early 21st century to remain on Earth and still be an explorer? Of course, one can strive to descend to the bottom of the ocean, an environment so hostile to our technologies, not to mention our bodies, that far fewer people have taken steps down there than have set foot on the moon. Or one can take a completely different approach and engage in science. Although science may not be as glamorous as a sailing ship or a manned spacecraft, it can take you anywhere, from the depths of the sea to the edge of our visible universe and beyond. As you have probably noticed while listening to this book, the phrase can take you to places inaccessible to the body, to places where no one has ever been before. If you deeply immerse yourself in the nature of space and time, or the quantum behavior of light particles, I may find two readers of the book making exactly the same journey. No one will imagine the same things while creating galaxies of virtual light particles in their minds. You have entered the world of theoretical research, a world without limits. No one ever knows in advance which direction may be alone with the open islands or continents, and many explorers had to fail to pave the way for great discoveries. Undoubtedly, there are strokes of luck, but they are not guaranteed. Given the latest discovery, however, there is a chance for it. The same is true for science. The discovery of antimatter follows this ancient path of pioneers. One person's genetics helped everyone else see the next amazing fact. The matter that makes us up, the matter that forms planets, stars, and galaxies, is only half of the matter. And he did not realize this by pure coincidence. He relied on what Dirac had done. It is evident that he built upon Einstein's work on how things move if they do so very quickly, and on the curious way quantum particles behave. This person was Paul Dirac. He created quantum field theory, thereby discovering antimatter. Dirac was a British scientist from 1932 to 1969, serving as Lucasian Professor of Mathematics at Cambridge University, holding one of the most prestigious scientific positions in the world, which had been held by Isaac Newton from 1669 to 1702, and by Stephen Hawking in 1979 and 2009. So what is antimatter? You already know what E equals mc squared means. Mass can be converted into energy, and energy into mass at a fairly high rate of exchange. And, as you just saw in the previous chapter, this energy can be borrowed for a short period from the vacuum, from the fields, to create particles. Now let's return to the miniatures. You are still in an empty universe surrounded by vacuum, namely the vacuum of the electromagnetic field. Right before you, an electron flies out of it. Why? Because it can. That's how you see the appearance of an electron. Bam! Just like that. A minute ago, there was nothing but vacuum, and now there is an electron. The electron has mass, and the very fact of its appearance means that some amount of dormant energy has been converted into mass. The equation E equals mc squared in action is easy to understand. But the electron also has an electric charge. And here the question arises, where did this electric charge come from? Mass arises from energy, and mass and energy are equivalent. So the appearance of mass and borrowed energy is a balancing process, merely a transition of energy from one form to another. But electric charge is a completely different issue. After the electron appears, it carries a negative electric charge. Up to this point, it did not exist. After it, it does, and this is undoubtedly unacceptable. As I mentioned at the end of the previous chapter, you cannot create something from nothing without paying a certain price. In real life, this never happens. I hear your sigh, but at least in the quantum world, this does happen. So how do we deal with this charge? We cannot simply turn a blind eye to it because there are too many. Every electron in the universe carries a charge, and many other fundamental particles do too. So where does the charge come from? Well, the simplest answer is often the most correct. Here it is. An electron never appears alone. It must fly out together with an identical particle, except for its charge, which is opposite. What is this particle called? The anti-electron. This concept was introduced so that the total charge of all pairs of electrons and anti-electrons ever created would equal zero. There is no need to resort to E equals mc squared or anything else. Such a phenomenon does not violate any laws. The total charge was zero long before the appearance of electrons and anti-electrons and remains zero. This is precisely what Paul Dirac brilliantly figured out. So what's special about this, you may ask? Well, the fact that there exist particles exactly like electrons with opposite charge was previously unknown. No one had seen an anti-electron. Today, we find them everywhere. The process by which an electron and its anti-electron appear from nothing is called the birth of electrons and positrons. Their pairs also exist in the reverse process when an electron meets an anti-electron. They annihilate, that is, they disappear, poof, and vanish, and their mass is converted back into energy, into light. For a moment, electrons and anti-electrons are created from the electromagnetic field, and they return to it upon annihilation. Furthermore, electrons exist on their own. They are all created from the electromagnetic field during the birth of electrons and positrons. Therefore, anti-electrons must also exist on their own. What do? But they cannot be found everywhere. In 1928, Dirac referred to the anti-electron as a hole in the sea of what we now call the quantum electromagnetic field, as it corresponded to some missing charge. His hole, the anti-electron, was experimentally discovered 5 years later, in 1933, and it was then that Dirac received the Nobel Prize in Physics for his extraordinary insight. His field theory encompasses all these fields. They are unified, and you have encountered them everywhere since you began exploring the micro world and discovered antimatter. American physicist Carl David Anderson was the first scientist to actually discover the anti-electron of Dirac. But instead of calling them anti-electrons, he gave them a new, still used name, positrons. Anderson received the Nobel Prize for his research work 3 years later, in 1936. Thus, antimatter was born. I have already mentioned that half of the matter is antimatter, but if it were only anti-electrons, they would not constitute half of all matter. What about antiquarks, these holy antibaryons? What can I say? What is true for the electron is true for all particles. Each of them has its opposite. There are antiquarks, as well as antineutrinos and antiphotons. However, some particles that have no charge can act on both sides and be their own antiparticles. A good example of this is light. Photons and antiphotons carry no charge. They are identical. So why don't we see all these other particles around us? The answer is that they exist. They are around you, but not in large quantities, because every time they appear, they only live for a very short period. Remember that any of these particles colliding with their opposite particle immediately annihilate with it, only to disappear in a burst of light energy, according to the equation E equals mc squared. However, somewhere else in the universe, the whole world could be made of antimatter in an anti-world. And if you like that definition, no one knows if anti-worlds exist. But if they do, and if you ever happen to encounter someone from there in space, do not shake hands. You are their Shanti copy, and you will turn into a bomb and immediately explode spectacularly. Nevertheless, there are some pieces of antimatter around, even inside you, right now. For example, during radioactive decay, some antimatter is created only to annihilate with its sister matter, becoming such a powerful beam of light that it usually shoots through your body. But neither you nor anyone else even notices this. Your eyes cannot see such beams because, as we discussed earlier, the eye simply did not need to develop the ability to detect them. But what cannot be seen can be detected by technology, and some clever engineers have managed to turn this discovery into effective medical diagnostic and research tools. For example, PT scanners. They are used in hospitals. PT stands for positron emission tomography. Doctors inject radioactive liquid indicators that emit positrons into the body. During the decay reaction, positrons annihilate with electrons they encounter, turning into powerful gamma rays that are detected outside your body by the PET scanner to create three-dimensional images of how your body functions. A truly brilliant technique. Well, now you know about fields and their vacuums, their possible unification, mass, charges, and antimatter. This means you are ready to travel beyond what you saw in the first part, towards the Big Bang and beyond, to the origins of space and time. So I would take a deep breath before switching tracks. Chapter 4. The Wall Behind the Wall. For many years, without specifically questioning it, you unconsciously assume the probability that the universe is mainly composed of emptiness, completely motionless and unchanging. Unlike our ancestors, you have probably heard of the Big Bang, but perhaps you have never thought about what it truly means. In many ways, we all resemble those floating in the sea, except that, as you already know, we float in a sea made of water. But in many seas, immediately classified by our friend Derek, seas are called fields and fill the entire universe. We are fields, an uneven and rather complex expression. Upon reflection, you come to the conclusion that this statement is probably logical. Thus, it becomes much easier to understand time, mass, speed, distance intertwined within these fields. The universe is vast. Unimaginably large spaces lie between any two stars and galaxies and clusters of galaxies. But there are no voids. There are only fields that allow distant objects to interact by exchanging particles, known as force carriers. Fields never intersect, binding everything together. There is something almost profound in this thought. And as you are about to rewind the entire history of the universe back to the birth of space and time, you may wonder, could all these drinkers, weepers, singers, writers, painters, shamans, saints, and blessed ones on the theme of God is one and multifaceted at the same time throughout the ages of human history have been right? In a sense, perhaps, but they certainly did not know why. And our robot supercomputer knows. And once again, the bright yellow tennis cannon comes back into the scene, appearing right before your nose. It still has no face, and it looks at you through a protruding tube. But this time, you are wise enough not to regard it as just a mechanism. Feeling strong and inspired by the reliability of all acquired knowledge, you prepare your mind for a second attempt at imagining the entire history of the universe. A metallic voice echoes from the void. Ready? It asks. You know that the machine is about to take you to the origins of space and time, but the robot gives you no time to respond, and a moment later, you find yourself in the sky above your home. Your home. The computer has moved you from where you were into the sky, but not to your hometown. And now you both soar upward like an arrow. You cross various layers of the Earth's atmosphere and emerge into open space above your native world. I am going to take you on a flight through the best computer simulation in the world, declares the robot. Programmed this way, it does not obey the already deciphered laws of nature. Even the most powerful supercomputers on Earth struggle to see what you will see. So, onward. Feeling the excitement of the upcoming journey, the impatience to go beyond the visible, to cross the alternating layers of the past wrapped around the Earth, you know that if you were to set off for the stars on an ordinary morning, with a body and not through reason, the journey would take a significant amount of time. And when you reach your destination, the star will not be the same as it is now. It will have changed, just like if you wanted to travel to New York right now. The trip will take several hours, and the New York you arrive at will be different from the one you departed from. People, cars, clouds, and raindrops. Nothing will be in the same place anymore. When flying to a distant star in a remote galaxy, the difference will be even greater. By the time you arrive at your destination, the universe will have expanded, and the relic radiation of the universe's average temperature will have cooled down. However, during an ordinary spaceflight, the past can never be reached. So how can computer simulation take you back to the past, even a very distant one? The answer quickly comes to mind. To be present at the moment of the universe's birth, to see and witness it, you do not need to fly anywhere. You simply let time move backward, and that is exactly what begins to happen. Without a flicker of a face, you embark on a new journey. A journey back in time through the core of the universe to reach the Big Bang, to go beyond it from your point of origin. Displaying unexpected sensitivity, the robot computer even kindly dims itself so that its presence does not hinder your view. In an instant, you find yourself 7 million years ago, on the surface of the last. Russia, my limiting end of Earth's visibility. The universe becomes a little closer, and it is filled with slightly hotter relic radiation. But 7 million years is not much compared to the history of the universe, 13.8 billion years. And nothing in the sky looks particularly different from what was there a minute ago. However, the Earth beneath you has changed. There are no cities, no metropolises, no flickering streetlights down there. The first humans are just beginning to distinguish themselves from the ape-like creatures. Your distant ancestors are still hairy hunters of wild beasts. Humanity has indeed come a long way. The next flash takes you 65 million years into the past. Dinosaurs have just gone extinct due to a combination of powerful volcanic eruptions and a catastrophic collision with an asteroid 10 kilometers in diameter, leaving only small mammals alive. Some of them, having gone through a series of evolutionary stages, became those very hairy ancestors you just introduced, and then us. Another flash, and you are transported 4 billion years back, when the Earth has just collided with a Mars-sized planet, tearing off a piece to create the Moon. The relic radiation is definitely starting to get hotter, and the surface of the last planet now looks much closer than before. The entire visible universe from here is less than 70% of its size. In 2015, you rewind a couple of billion years back. The visible universe is already less than half of its original size. The Earth does not yet exist. In its place, right before you, stars are dying, their colossal explosions spreading matter throughout the cosmos. After a few 100 million years, their remnants and dust will gather into massive clouds, and gravity will aid in forming at least one new star, the Sun and its planets. Another flash, and you are 5 billion years before the birth of the Earth, 1.5 billion years before your own birth. The visible universe is less than 25% of its size. In 2015, the surface of the last Russian is now much closer between you and that wall. Galaxies are forming around giant black holes, sometimes leading to collisions, not in a show of force. Another flash, and you are thrown back 13.7 billion years. You are still where the Earth will one day appear, but the surrounding visible universe is now less than 1.5% of its original size. You are in the Dark Ages. The Dark Ages through which you traveled in the first part of the book were cold because your moment of flight coincided with the visible Earth in 2015, after more than 13.7 billion years of expansion. However, 13.7 billion years ago, it was neither cold nor dark, and now you are right there. The first stars have not yet ignited, so none of the visible matter has arisen from nuclear fusion in the cores of stars. Therefore, you are surrounded by the tiniest existing atoms, mostly hydrogen and helium, and brightly glowing radiation, microwave background radiation. Not microwave at all. You can see it with your own eyes. This is the light that initially filled our universe. Light, shining brightly everywhere. Light that became microwave radiation much later, after several billion years of the universe's expansion. And another flash, another 100 million years further, 12.8 billion years ago. The surface of the last scattering, the surface at the end of the visible universe, is now 1 light minute away from you, meaning that the visible universe has a depth of only 1 light minute, less than 1/8 of the distance separating the Earth from the Sun. The entire universe has been transparent for 60 seconds and is 3,000 degrees Celsius hot. Anywhere you look, You are still in the dark ages, but everything around you glows so brightly that you wonder if the chosen term truly fits them. You stop, and after a moment, the computer instantly begins to rewind time a little further, albeit at a slower pace, and you find yourself in a strange, literally invisible place. Another minute back in time, and you begin what sounds like the final journey. The surface of the last Russian is right before you. You take a deep breath, ready to cross it, to go beyond the wall, to reach the invisible. Time rewinds further, and now you are behind the wall. You have entered a part of the universe's past that has never seen light. You truly cannot see anything more. Light does not spread around here. There is simply too much energy. But you know what to do. You immediately switch to the methodology of yogis and are surprised to realize that the universe beyond the surface you just crossed is vast and ancient, at least 380,000 years old. Your journey is still far from over. You refocus on what is around you, what is happening now beyond the wall. At the end of the visible universe, the ambient temperature is 5,000 degrees Celsius. All electrons will one day begin to bind with free atomic nuclei to become hydrogen and helium. There are photons here themselves, colliding with them, getting excited, before their radiation bounces back to collide again with another electron. The electromagnetic field is so filled with energy that all its fundamental particles transform into one another almost instantaneously. Another flash, and you find yourself at least 1,000 years before the universe became transparent. You are surrounded by a dense soup of particles, representing a mixture of all excitations of quantum fields, their elementary particles, and force carriers. Everything collides with one another, leaving nothing with anywhere to go. There is too much energy around. Everything appears, collides, and disappears. And as time continues to rewind, the universe is still contracting. The energy density is rising, and the reinforcement is becoming more and more violent. Nevertheless, you try not to get confused and focus on your journey back in time. You are honest. The mind and the journey through the methodology of yogis seem like a very realistic simulation. The universe continues to contract, and the fabric of space-time bends monstrously. Nothing you know or can imagine possesses such destructive and deforming power. For a split second, you wonder why you haven't heard more gravity at this stage, but you have no time to ponder. You have gone back in time a few thousand years and are now surrounded by unimaginable ash. Your virtual heart begins to race faster and faster as the temperature, pressure, and gravitational influence on what you see around you reach incredible levels. Now, you are 380,000 years before the universe became transparent. If you were to look through a telescope on Earth at more than 13.8 billion years ago, you would be 380,000 years behind the wall, marking the limit of the visible universe. Looking in the opposite direction, you are almost 3 minutes away from what could be called the birth of space-time. Time continues to flow backward. Even atomic nuclei are breaking apart, allowing all quarks, neutrons, and protons to move freely at their own discretion. Strong nuclear interactions flood the surrounding energies, protons and neutrons, and the stable structure itself begins a frenzied dance in which battered quarks, stunned by the force carriers, turn protons into neutrons, disappearing from the universe. The surrounding temperature is 100 billion degrees everywhere. But you do not stop. You continue to move through time, rewinding second by second. All surrounding particles of light transform into pairs of matter and antimatter, everywhere, and it seems that the last is just as much as the previous one. And as then, you wonder in a half-trance how one of them ultimately managed to become predominant. For the balance to be disturbed, something extraordinary must have occurred here. A mystery that may even be uncovered this year or next, when the upgraded, more powerful particle accelerator at CERN is restarted in June 2015. We'll begin to unravel it. You would like to linger here a little longer to clarify it for yourself and report to Sir, but you are not in charge here. You are already racing toward a universe filled with a soup of such immense energy that everything around is shaking. Gravity bends and breaks everything. Fields are excited to levels beyond comprehension. It is not the weight of stars that causes gravity to impose itself on every field around by curving space-time, but the energy of the entire universe being expelled through a sphere 100 light-years in diameter. Such a sphere, with today's Earth at its center, could contain no more than 5,000 stars. At that time, it held the energy to form hundreds of billions of galaxies, each containing hundreds of billions of stars, not to mention. Or, however much you might like to consider everything around, you continue to fly against the current of time. Now, you are just 1/1,000,000th of a second from your final destination. The temperature has reached 100 million billion degrees. With such an immense amount of energy around, even the guards of quark prisons, gluons, cannot hold their prisoners. Neutrons break apart. Quarks are now free, beginning to interact with their antiparticles, turning into pure energy. Looking around, you realize that discussing the difference between matter, light, and energy is now entirely unnecessary. The fields that were independent entities throughout the journey from Earth to here, the fields that describe all conceivable processes on Earth through various interactions, now merge into one. As expected, the electroweak field is active, as some familiar particles that you have become accustomed to seeing everywhere disappear. New fundamental particles belonging to the electroweak field fly out from all sides. The Higgs field disappears, along with the massive Higgs bosons that have long remained hidden from human knowledge. The particles you now see, W and Z bosons, which we encountered earlier, are the force carriers of the electroweak field. Around these particles, there is so much energy that they are so hard to produce on Earth, yet they are everywhere here. The universe is now heated to 100 billion degrees, and the laws of nature begin to differ significantly from those you have known throughout your life. Quarks and antiquarks and gluons are absorbed by the background radiation. 1,000 billionths of a second after what is nothing less than the presumed source of the origin of space-time. An event we could call the beginning of all beginnings, that which will one day become our entire visible universe, now exists as a sphere 10 meters wide, continuing to shrink. Everything it contains is currently heated to fantastic billions of degrees. And as it heats up, more and more of the components that make up our matter, the fields combine to become one great unified field. Only gravity remains outside this unification of forces. Being so close to the beginning of beginnings, you begin to think that not much remains to happen. In fact, you have just reached the place known as the Big Bang. The moment when the energy accumulated in the great unified field began to transform into particles. But surprisingly, despite the fact that experimental physics has never reached such a place, the computer seems unwilling to stop in the first place to show that the history of the universe does not begin there. Indeed, to great surprise, as time continues to rewind, the matter and energy of the entire universe suddenly vanish. And, contrary to what one might expect, everything cools down sharply as all available energy transforms into another field with which you have not encountered before. A field filled with its own particles, known as the inflationary field. This field is believed to be responsible for the initial expansion of the universe. No matter how crazy it may seem, everything suddenly accelerates again, and the entire universe incomprehensibly crashes into itself at an unimaginable speed, dragging you along with it. In less time than it would take light to pass through the core of an atom in your kitchen, the entire universe shrinks from 10 meters in diameter to a size billions of times smaller than a proton. Scientists have named that stage the inflationary model of the universe. You have just passed, moving backward, behind it, where there is no matter, nothing. 1,000 known scorching laws of nature are completely unlike those familiar to you from everyday life or from your journey up to this moment. At this point, the three forces or fields governing all known matter and antimatter in the universe, including the matter that constitutes you, are believed to have merged with gravity. You would continue to rewind time further beyond the Big Bang, following the entire path of our universe's birth. But something is amiss. The concept of space and time that you have been using until now is no longer applicable. The gravitational curvature of space-time is too strong, and quantum effects are too. Without time, without space, without space-time, traveling further is impossible and makes no sense under such circumstances. You have not yet reached the beginning of beginnings and have no idea how to come up with a way to get there. How frustrating. And suddenly, you want to look at everything from the outside, because until now, you have always remained inside the universe. But the very concept of outside seems to make no sense either. What you have reached here is the surface of two walls, distinct from the surface of the last plant that limited what could be seen from Earth. This wall is impermeable not to light, but to modern knowledge. Behind it lies the realm of quantum gravity, where all known fields of nature can be unified into a whole in a quantum way. There, the universe becomes a mystery, intertwining the sciences of the 21st century, faith, and philosophy. In a sense, this is the place where our knowledge stops, replaced by purely theoretical inquiries. For journeys beyond the surface of the last plant, you cannot use telescopes that gather cosmic radiation, but scientists have built a particle accelerator that allowed them to achieve temperatures and pressures they hoped to discover beyond the universe. And it worked. Scientists have discovered new laws and managed to swim back through the flow of time, albeit indirectly. As you read these lines, they have already constructed and continue to create next-generation telescopes to detect not radiation, but gravitational waves, ripples spreading through the very fabric of space-time. Such telescopes can detect signals coming from beyond the surface of the last plant, from that distant past where you have just been. But traveling beyond the wall of quantum gravity, also known as the Planck wall, oh, that is a completely different matter. No one is even sure how to think about what lies beyond it. The entire visible universe was then so tiny that to conceive it in your mind requires a theory of something extraordinarily large, folded down to minuscule sizes. A theory in which quantum laws, with their quantum leaps and so forth, apply to the universe itself, requires gravity and quantum effects. Quantum gravity is needed. Much more, and we do not have it. We have no research frameworks. Thus, you cannot penetrate further. In fact, you do not even allow yourself to speculate about what lies beyond the Planck wall, neither in space nor in time, because those two concepts make no sense there. When scientists say that the age of the universe is 13,800,000,000 years, they mean that 13,800,000,000 years have passed since the concepts of space and time we use became meaningful. That moment occurred approximately 380,000 years before the relic radiation filled cosmic space, and that moment happened a few million billion billionths of a second before the Big Bang. Ultimately, scientists can rightly say that this is the amount of time that has passed since the emergence of space and time. But that does not mean that our universe was born then, nor does it mean that it is the only existing universe, or that it is the only one that has ever existed. You are back in your living room, on the worn old couch, so deeply astonished that, gripping its armrest, you travel through space and time, seeing galaxies, stars, fields, observing how gravity works, what its influence is on the shape and destiny of space-time, depending on the contents of the universe. Before you did this, something amazing begins to happen to you. As if you are on the verge of making a stunning discovery, thoughts swarm in your head. You feel like a child again, realizing that the world can be understood, that it has somehow already been understood up to a certain point, and the computer has shown all this to you. From Einstein's general theory of relativity, you learned that you could figure out the history of the universe from beginning to end, knowing only what it contains. Now you know that the contents of the universe consist of quantum fields, moving, evolving, and interacting with each other, more of which, at this moment, are three, but which were once a single whole a very long time ago. These fields are the mother and father of all particles and antiparticles in the universe, and the reason why all elementary particles are the same, regardless of whether they are here, inside your body, or in any other galaxy, in the present or the past. And all this can only mean one thing. Perhaps you have become a god. This god, you know gravity, you know what lies within the universe. By connecting these 2 points together, you gain knowledge of the entire history of the universe and its past or present, its future. You are almost a god, at least by definition. Your face lights up with a smile. You immediately grab your mobile phone and dial the number of the only person you can think of at that moment. Who is it? The voice on the other end sounds suspicious. It's your cousin's grandmother. It's me. Hello, dear. How are you? Are you feeling better? Better. I feel amazing, you exclaim. Good to hear. Did something happen? I traveled, exploring the universe. Well, okay. I know that sounds silly, but I can create and develop a universe like ours, just using my imagination. It must be that feeling when you feel like a god. Grandma pauses. I see, she says. You understand something? You ask, wondering why she does not seem to share your enthusiasm. Nothing. Nothing. It's just that, well, okay. I've heard that phrase before. I've heard it. People love to portray themselves as gods, don't they? Do you remember my favorite friends, Katya and Gabby? No, I don't remember. But listen to what Let me finish, dear. So, Katya and Gabby went shooting last weekend. The thing is, Gabby really loves this sport and taught me, possessing some quite elementary knowledge about how our world works. Knowing how a bow shoots and where an arrow comes from, you can predict where it will land. Charming, isn't it? Of course, Grandma. That's ballistics, Newton's law, right? Well, it's good that you said that. Can you apply it to the entire universe? You said something at the beginning, or am I mistaken? You apparently found something to which you could apply your ballistics or any other laws of nature. Initial conditions, you mean? And they know. Would you like me to ask Katya and Gabby to call you so you can discuss this? They really understand these things. No, no, no. There's no need for that. But okay. Will you call back when you find your initial conditions? Me? Yes. All right. Thank you for the call, dear. You are very peaceful. See you soon. With those words, she hung up. And while you look at your phone in confusion, let me say this. As you probably understood, she is right. To understand something about the universe, two types of data are necessary. The first is a framework, or a set of laws, and the second is the initial conditions to apply the ideas you have so far to the universe as a whole. Knowing its entire fate from scratch would not be sufficient with all the laws of the world. You still need undeniable initial conditions to which you can apply the laws of evolution, and you simply do not have them. And what's worse, how can you be sure that the laws of gravity and quantum fields you know are applicable at the very beginning of the universe's existence? With a sigh, you settle back on the couch and take a sip from your coffee mug, feeling that some crucial data is still missing. Chapter 5. Lost Pieces of the Past. Everywhere, space-time. What else is there to uncover about it? What have you not seen? Particles, interaction carriers, fields, gravity. Haven't you experienced them yourself? To find out. And why do you feel so anxious? You open your eyes, and to your surprise, you are no longer at home. You are sitting in a cramped seat in a strangely familiar airplane in seat 13, and to be precise, the other passengers are lining up in the aisle, preparing to disembark. In confusion, you look out the window, but there is no doubt. You have indeed returned to your time-traveling airplane, and it just landed in the year 2014. Struggling to comprehend, you stand up, follow the other passengers to the exit, and come to your senses in the midst of long, seemingly endless glass corridors with a view of the sea. How did you end up here? A moment ago, you were at home, just calling your cousin after traveling across the known universe. You remember that around the Earth is a delineated sphere with a radius of 13,800,000,000 light-years, containing all of humanity's past that can be gathered through healing. Beyond it lies another layer of reality that existed 380,000 years ago, and what lies beyond that, no one knows. As you continue walking through the ever-increasing number of corridors, the bright sun of 2014 shines proudly, its rays traveling to the future Earth in 8.3 minutes. A profound sense of loneliness suddenly envelops you. What is the meaning of all this? How can our universe be so vast, and we so small, forever doomed to be lost in space and time, tormented by the awareness of this fact? Or are we, humans, at the beginning of a long path of technological progress that will someday bring distant worlds closer? Perhaps this is where it happens, and you are on the verge of witnessing one of those many possibilities of the future that our planet could achieve. A future where the near and far are indistinguishable, where the past and future are merely directions of movement for our descendants? Time travel has been a human fantasy for centuries, but you have never heard of anyone who has truly succeeded. Stephen Hawking once threw a party for time travelers at noon on June 28, 2009. To ensure that only those time travelers attended, he sent out invitations only after the party, but no one showed up. So what does this new journey intend to tell you? A being of no significance, lost in the vastness of space and time. The winding glass corridor you are walking through eventually leads to the hall of a huge airport, which might rightly be called a time port. Hundreds of people are queuing to pass through something resembling a customs hall, brightly lit. Light streams in through giant windows overlooking skyscrapers rising from the sea. Standing in one of the many queues, mingling with other passengers, you feel a fear that the reality you are currently experiencing is indeed a return home. It's clear that this causes anxiety. If it's real, then what has happened to your past? If you truly flew 400 years from the moment of takeoff, then the past you left behind is still somewhere out there. And can you, if you wish, go back to live that past life to the end? Or is it irretrievably lost? Sending Shea back created a home for you. Friends and family have long since passed away. It dawns on you that this must be the case. Time travel. The interaction of space and time can be complex to grasp, but it's hard to imagine that the same person could live multiple lives in the same universe simultaneously, knowing all about them. Even if fields seem to allow you to do the same as what happens to particles that no one observes, what is possible for single particles seems impossible for their multi-billion-strong assemblies, such as the human body. And while your mind, with nectar and sadness, contemplates this fact, you almost physically feel an insurmountable chasm separating you now from all your loved ones, and sorrow grips your heart. But in what you have seen so far, there is a certain comfort. The past lives of your loved ones have turned into a sequence of images moving through space-time. All the light and other massless particles that ever bounced off or interacted with their bodies, even in passing, created a memory of their existence, a kind of projectile racing at the speed of light from Earth toward a distant, unexplored pulsation of invisible but omnipresent fields. And since you have traveled 400 years into the future, the visible memory of their lives is currently washing over the surfaces of planets and stars lying 400 light-years from Earth. Their image will continue to move, spreading further, possibly periodically entering some radiation-collecting alien device as long as the universe exists. The games regarding the matter that constitutes us, and regarding those atoms that were born billions of years ago from long-dead stars, before coming together to form the bodies of your friends and loved ones. All their billions of particles have now scattered across the world. You might even be near one of them right now, at least with one. Perhaps we are not so small, and in the grand scheme of things, you think, reflecting, our imprint is here, in growth, and not here forever. And it is nice to know that the memory of our lives will always exist, traveling among the stars. Time, space, and fields make us all belong to an extraordinarily vast reality. Stretching your arms out to feel the forming inflammation, raising them high into the air to see and climb the invisible slope created by the Earth in the surrounding space-time, you begin to understand how all scenarios of the past, present, and future could indeed be interconnected. "Are you all right, sir?" asks a friend in uniform. The woman, coming out of her reverie, asks what you didn't notice and approaches. You struggle to squeeze out something like, "Thank you, I'm fine." But some things in life do not change, even in 2014. Everyone immediately feels guilty, facing a well-trained customs officer. "Where did you arrive from?" she asks. "From the beginning of the 21st century," you reply, trying to give your voice as casual a tone as possible in a trip of this kind. "Please follow me, sir," the woman says, her tone unmistakably indicating that this is an order, not a request. And while almost all the other arriving passengers nearby cast reproachful glances at you, the problems you have created, you step out of the queue, following the officer through. "Oh, is something wrong?" you ask as the door opens before the assistant. "Please, come in." This is the only midnight response. Inside, you find another rather hostile-looking officer sitting behind a large desk. Above his head, a big sign reads, "Psychological Relief Department for Time Travelers." Any aggression towards our staff results in immediate prosecution. Clearly, not satisfied with yet another patient, the officer impatiently points to a chair across from him. "Don't look around." You start to feel uneasy. The room is empty, with just a desk, an unfriendly officer, posters, and the already familiar yellow tube peeking out from behind the desk. All your worries instantly evaporate as soon as you recognize your particle-emitting companion. And what's more, another computer simulation poses the question, if so, it certainly made you feel a bit better, to understand your place in the universe, to ponder the nature of life and death. The desire to understand reality is, for the most part, a personal wish, and supercomputers should not impose their views on you. Your right has its own day. However, I must warn you that so far you have only skimmed both theories used by scientists to describe the universe, quantum field theory and Einstein's theory of gravity. Of course, neither looks logical or elegant, but you should know that there are problems with many related concepts. In fact, to be completely honest, no one truly understands the universe yet. Not even the reality around you right now, whether on the couch or on a tropical beach, is shrouded in mystery. But one thing can be said for sure. It is believed that all mysteries, whether they lie around you, within you, or far beyond the Big Bang, ultimately lead to the unification of quantum fields through quantum gravity theory. And although, to be honest, such a universal theory is not yet known, at least one property of quantum gravity has been found. Engage. You like the key that gives a teasing hint of what lies beyond the Planck wall. This is good news. The bad news is that there is only one known window that can be opened with this key. Through it, it is presumed that one day you will be able to travel, even if only in our consciousness, beyond the beginning of space-time. And this is why the robot has come to take you from the time port. The room you are in disappears. Once again, it shifts into the night landscape of deep space. You begin to ask the robot where you are headed, but you are cut off mid-sentence. "I am taking you with me to a black hole," the machine announces. Since you have already been to one at the very beginning of your cosmic adventures, you might wonder what you missed during your first visit. The answer is surprisingly simple. You were not close enough. Chapter 6. Unexpected Mysteries. Chapter 1. The Universe. If you think about it, there is something special about the universe we belong to, and the name universe comes from the Latin universus, where uni means one, and versus means to turn into one. The beginning itself emphasizes a very specific issue that Shea raises. Any experience produced within our universe can be repeated multiple times. Want to test Newton's law of universal gravitation on Earth? Shoot an arrow. Not sure you understood it? Shoot again, again, and again. With patience, you will see that knowing the initial position, angle, and velocity allows you to predict where the arrow will land. That is everything that ballistics is about, and it works. Otherwise, bows and arrows would have long been abandoned, and England would belong to France. Thus, having laws, initial conditions, and evidence, you can predict where the arrow will land and protect an entire country. For the universe as a whole, it is a bit more complicated. Even if you had a law that explained everything and was applicable everywhere, how would you make it work? How would you use it to predict how the universe we live in today became what it is? For that, initial conditions must have existed, which do not exist. But you could try to outsmart nature by starting to rewind time backward from today. Perhaps you would eventually reach the initial event that occurred recently. This is exactly what scientists did, precisely what you were engaged in the fifth part, and you reach the Planck wall. It is a good starting point, as it corresponds to the moment when space and time became what they are now. But it does not eliminate the frustrating fact that unlike the experiment with arrows, you have only one universe. You cannot try to create a second one with different initial conditions to see what comes of it, not in a laboratory, at least. But what if our universe is not the only one? What if we are part of another multiverse, different from the one you encountered at the end of the second part? Could our reality be just one of many possible realities, all with different beginnings, perhaps even different laws, and therefore very different presents? The hypothesis of such a multiverse is a question you will soon have to face, as it is part of the answer devised by modern theoretical physics for the mystery you will experiment with in this part. In fact, this section of the book will differ somewhat from the previous ones. In the first and second parts, you traveled through the mega scale, learned about gravity. In the third part, you saw what our reality looks like when moving through it very quickly. And then in the fourth part, you entered the micro world. In short, so far, you have been familiarizing yourself with the relativity of time and space from quantum physics, but nowhere until now have you mixed gravitational and quantum theories together. This is now going to be your goal. To do this, you need to exercise your mind a bit, just as you would your body in a gym. Mixing gravitational theory and quantum physics means mixing the micro and mega worlds. And to prepare your mind, you will have to jump back and forth in both directions for nights on end. By doing so, you will see what is wrong with the theories considered so far. Having done this, you will accompany the robot to a place where gravitational and quantum effects operate simultaneously. Now, however, let's look at the mysteries of modern science together, just you and me. It can be argued that there are three types of mysteries in physics. The first is inherent to the theories themselves. They are theoretical. The second is rooted in observations and experiments. They are usually, but not always, subject to investigation. The third type of mystery arises when no one can understand anything more. Black holes and the physics associated with the existence of space-time fall into all three categories. They are both bridges and obstacles lying between us and the holy grail of modern research. The theory that connects the quantum world and the dynamic aspects of space-time discovered by Einstein. That is why they are so interesting. This is why the robot intends to take you into a black hole. But why a black hole? Why not the origins of the universe itself? Because, as with a black hole, at the birth of the universe, an enormous amount of energy is confined to a rather small volume. In both cases, a very large amount is compressed into a very small one, and neither gravity nor quantum effects can be ignored. In this sense, black holes and the origin of the universe look very similar. Although, of course, no one can experimentally look at the universe from the outside. Even if we had a law governing the behavior of everything visible and invisible, you would not be able to check whether different initial settings make a difference in the evolutionary model for the universe as a whole. We cannot create a Big Bang in laboratory conditions, and we do not see, which means we cannot analyze new universes appearing out there in the night sky. That is why black holes are useful. To begin with, there are many of them. Take virtually any galaxy in the universe, and at its center, you will probably find a supermassive black hole. There may also be several smaller black holes with masses several times less than our star scattered throughout. As of 2016, the largest discovered black hole is 23 billion times the mass of the Sun. It is located about 12 billion light-years away, a very young galaxy at the time when it emitted the radiation we are capturing today. On the other hand, theoretically, even the smallest black holes can be measured using the so-called Planck system of units, valid in a medium where both gravitational and quantum characteristics are taken into account. In numerical terms, the Planck length corresponds to about 1.6 times 10 to the power of negative 35 meters, a tiny length. So black holes can be virtually any size. Both black holes and the very young universe share some important common features. Both involve boundaries beyond which gravity cannot be applied without including quantum effects. This boundary is the Planck wall, the wall we saw when traveling back in time beyond the Big Bang at the end of the last part, the moment of the universe's birth. This wall existed everywhere. As for black holes, generally hidden from view, only one path opens beyond their gates, the event horizon. You will cross it at the end of this part. This journey will be the key that opens access to the seventh part, where you will embark on your final journey. A tour of the universe from the perspective of the most popular modern theories, in a theory of everything, as a quest to unify space-time and quantum fields. But these theories, known as string theories, are so crazy, combining multiverses, parallel universes, and higher dimensions, that you might start to think that scientists have truly lost their minds. And if it were not for the mysteries they are unraveling, it would indeed be so. After everything you have experienced before reaching this page, it may seem amusing to learn that far from unraveling almost everything, the physicists of the 20th century left us with a picture of the universe largely filled with deep, dark unknowns. However, this should not be seen as a disappointment. These unknowns are opaque windows into the science of tomorrow. And between us, in a way, how much less than a century has humanity's understanding of almost everything grown, observing puzzling ideas sprouting today in the minds of theoretical physicists. Few doubt the upcoming revolutions of consciousness. Some have already matured or are ready to bloom profusely, just waiting for the right experiment to fill our minds with the promise of a magical new reality. So here's what will happen to you now. First, you will take another look at the quantum fields filling the universe and see that, despite everything I have said so far, they make absolutely no sense. Then you will reconsider all the particles of these fields in the context of quantum gravity, realizing that they are not so meaningless. And then you will meet a cat that is simultaneously alive and dead. And finally, after familiarizing yourself with everything, you will stop understanding anything at all. Encouraged by such successes, you will hear about parallel universes branching off from ours like the branches of a tree, ensuring that the quantum world lies beyond what common sense tells us about reality. You will want to return to more familiar territory, ultimately striving to bridge the gap between the micro and the mega worlds. And once again, you will return to the big picture of the world, looking anew at Einstein's theories, at the galaxies of the universe, at its expansion, hoping to find comforting, clear formulations. Strangely enough, you will not find them. You will see with your own eyes that much of the content of the universe is not only invisible to telescopes, but also unknown. The universe on the megascale is filled with mysteries, wherever you look, and this is equally true for microscopic scales. Voluntarily or involuntarily, you will have to digest the fact that no matter how powerful and forever remaining Einstein's theory of relativity is, in terms of curved space-time, it is incomplete. It even predicts its own defeat. Follow the impossibility of a theory of everything. Within our universe, there are places where it cannot be applied, which means that if humanity needs to explain everything, it must find another, more complete theory. And in what places are Einstein's theories powerless? You have probably guessed, inside black holes and before the Big Bang, somewhere along the way to the Planck wall. So far, you have traveled through the best theories humanity has ever created to describe the world around us. In practice, this means that you now know about the universe as much as an average graduate student from any of the best universities in the world. Of course, not in terms of technical education, but certainly in terms of familiarity with hypotheses. And that is more than enough to become the star of any party. Now, it is time to move on and see what does not work. And then you will not only be a star, but will also leave your friends scratching their heads in confusion. Chapter 2. Quantum Infinity. Do you still remember what the cosmic vacuum actually looks like? What until now seemed like emptiness has turned into a riot of pulsating fields. The pulsation occurs due to particles shooting out of all vacuums in the quantum world. If something is possible, it will inevitably happen. So for a moment, forget about your usual, everyday size and gravity. Imagine your copy diving into quantum fields, into the micro world. Sitting in a mini-chair, you resemble a sports referee watching two electrons interact with each other, just as you might watch a tennis match where the players are electrons and the balls are virtual photons dancing between them. One electron is somewhere to your right, the other to your left, both being absolutely identical. They both have the same electric charge. Like magnets, they should repel each other. It must be interesting to observe them. Now the electrons are still far apart, moving through the electromagnetic field generated by me. They are getting closer to each other. They are close to colliding, but it doesn't happen. They interact with each other. They play. Virtual photons shoot out from the electromagnetic field, deflecting and scattering the electrons. Then, just as quickly as it began, the game is over. The electrons and virtual photons disappear. You wait for the next game. Another pair of electrons appears. It seems that since you decided to focus on virtual photons, you are paying attention to the electrons. Your mini classes of electrons are moving, getting closer and closer, then bam, virtual photons appear. Not wanting to miss anything, you slow down the flow of time. The electrons are in the process of interacting with the virtual photons. Everything is fine, but something happens. One of the virtual photons that appeared between the two electrons suddenly transforms in a strange way. It becomes a pair, a particle and an antiparticle, a positron and an electron. You cast a quick glance at the electrons, curiously observing how they might be affected by the loss of the virtual pearl of light, but it doesn't seem like they noticed it at all. As you shift your gaze to the newly formed pair, it is no longer a pair, but 2.5. You close your eyes and rub them. What kind of joke is this? You open your eyes again, and suddenly thousands of pairs of particles and antiparticles appear between the two electrons. You blink. They are already hundreds of millions, and now thousands of billions. You blink again. All disappears. You check the electrons. They have scattered, just like the previous pair of players. Amazing. You have just witnessed one of the consequences of quantum laws applicable to the microworld. If something is possible, it happens. And this is quite possible for virtual photons diving into the energy of moving electrons to transform into virtual pairs of particles and antiparticles. They, in turn, can become the next pair of particles and antiparticles, which then turn into further pairs or annihilate into light. Then you have an idea. Even if only two tiny electrons interact with each other, the possibilities of the processes and actions of virtual pairs are infinite, just as there are an infinite number of virtual pairs participating in the process. You ponder this while comfortably sitting in your referee chair, waiting for the next game to watch the fireworks again. But there are no more players. No electron flies by. However, now that you know what to look for, you see virtual pairs of particles and antiparticles appearing just the same, albeit at a slowed pace. They resemble tennis balls and anti-balls popping up from nowhere in the complete absence of players. This formation of pairs is called quantum fluctuations of the vacuum. They are present here all the time. But if there is available energy to activate them, such as the kinetic energy of some flying electrons, they become much more excited. Suddenly, a pair of electron-positron appears before you, and it annihilates into a photon, spontaneously turning into another pair, a quark-antiquark pair. And now, one of these quarks emits a gluon, which, in turn, even in a vacuum, where it seems there is nothing, always and everywhere, must take into account all the infinite possibilities of creating particles and antiparticles, having rather catastrophic consequences. The possibilities are so important and numerous, in fact infinite, that there must be an infinite amount of energy at all points in our universe, even where there seems to be nothing. In the vacuum, it is quite evident that this is not the case, or the universe would collapse right now due to the excessive gravitational influence exerted on space-time. So something is wrong with the presented picture. To alleviate this rather troubling problem, quantum field theorists devised a rather clever trick. They simply decided to completely forget about gravity, taking it out of the equation. And while doing this, they banished infinities from the formula, removing them, and made calculations with what remained. And it worked. Just consider Dutch theoretical physicist Gerard 't Hooft, one of the brilliant physicists who founded such a mathematical operation, who received the Nobel Prize in Physics in 1999, along with his scientific advisor, Martinus J. G. Veltman, for it. Thanks to them and other scientists, and despite the mathematical tricks of accounting for infinities, quantum field theory has become, due to its predictive power, perhaps the most successful scientific theory of all time. Getting rid of infinity led to predictions of the appearance of even unseen particles, predictions that turned out to be true concerning the mass or charge of particles with an accuracy of 1 in 100 billion. It can be said that if a randomly chosen person possessed such a counting ability, they could calculate whether they had poured 1,000,000 liters of beer into cups in a bar with an accuracy of 1 drop. Undoubtedly, if we had such an ability, scandals would occur there daily. Quantum field theory is remarkably precise in its predictive power, but this trick leaves us all frustrated for reasons that even 1,000,000 pints of beer cannot wash away. Why do these infinities occur? Can they happen simply because we do not know what is happening in the regions of our universe that are even smaller than text? Theories explore them. Perhaps this is what one extraordinary American physicist, Kenneth G. Swenson, thought, and instead of trying to explain the infinitesimal microworlds and searching for conclusions about particles, he believed that such mind-boggling scales could actually be a problem, and it is not necessary to consider all smaller scales to be able to talk about particles. Just as I need to know about atoms by comparing apples at the market, he argued, and proved that what is unknown can be estimated, classified, and forgotten. It worked. So in 1982, he received the Nobel Prize in Physics. Velas, I decided the problem of what happens with infinitely small particles, eliminating it using rules and exceptions, and the distortion of the unknown, and infinities no longer occurred. The procedure for eliminating infinity is called renormalization. As I mentioned earlier, it works effectively for calculations, but one cannot hope to ever understand everything simply by bypassing the unknown. It is necessary to dive into it, especially regarding the gravitational field, where renormalization does not work. The subject of quantum field theories is the contents of the universe. They are quite accurate, surprisingly accurate in fact, but only when they leave space-time individually, when they are fixed, when gravity does not influence them at all. Not very realistic. We need to find a way to bring gravity back, to turn it into a quantum field. And how to do that? Quantum field theory asserts that since fields exist everywhere, they can create small portions of energy or matter called quanta. The fundamental quanta of the electromagnetic field are elementary particles with the smallest electric charge, photons and electrons. Similarly, the fundamental quanta of the strong nuclear interaction field become quarks and gluons, while the fundamental quantum of the gravitational field, considered as a hypothetical quantum field, refers to the previously mentioned gravitons. You have already heard about them in the 5th part, but we ignored them then. Why do they reappear here? Because we want to see what happens with them. Yes, let's consider that gravity appears in the quantum field, just like all other fields. Then gravitons become the carriers of interaction. If one were to calculate on paper how gravitons could affect their surroundings, theorists would find that this influence is the same as that of the curvature of space-time on paper. They are gravity. This is a very promising start, but upon further reflection, scientists realized that then these very quanta of the gravitational field, gravitons, would completely fail in the established theory of gravity. Not very good news. Why? Firstly, gravitons have no reason not to interact with each other. If they exist, they must be subject to gravity, just like everything else, and therefore they affect themselves. Secondly, being elementary particles of the quantum field, they must appear from everywhere out of the vacuum of their field, which leads precisely to the infinitely large problems that were eliminated in previous theories. However, gravitational quantum infinity cannot be removed using the renormalization procedure. Here, the renormalization mechanism completely fails, and the approach becomes entirely inapplicable as it ignores the very distance at which gravitons act. Ultimately, this means the emergence of truly problematic infinities when attempting to turn gravity into a quantum field in the standard way. And it is evident that one cannot ignore gravity to get rid of gravitons because they are gravity. If gravity were a quantum field, as just mentioned, if gravitons were the correct description of how gravity works in nature, then space-time would have to react to infinities and practically collapse, which does not happen. Or we wouldn't be mentioning it. Strangely enough, despite all of the above, many scientists, including myself, I'll discuss this in the 7th part, and you may consider them abnormal. I believe that gravitons exist, at least as part of the all-encompassing theory that everyone is searching for. Now that we have touched on this topic, let's go even further, so you will immediately see several reasons why Einstein's general theory of relativity and quantum field theory diverge. Gravity relates to space-time. In other words, they are intertwined. In quantum field theory, which emerges from the vacuum, elementary particles are the products of the field itself. Therefore, for quantum field theory, gravity must also produce elementary particles from its field, but from the field of space-time. Thus, the particles themselves must consist of space and time. This means that substantial portions of space-time must exist everywhere. And by the way, neither space nor time should be continuous. Worse still, these portions of space-time must have the ability to behave simultaneously as waves and as particles and undergo quantum tunneling and quantum leaps. Good luck trying to imagine such a picture in your mind. In fact, if you are a normal person, the simple attempt to think about it all will make your brain melt. However, from the perspective of nature, there is no cause for concern. But the real problem is that even if we forget about the difficulties with infinity, all other aspects of quantum field theory are so advanced in describing all the particles that make us up that they only work as long as there are no such portions of space-time around. In other words, this means that the general theory of relativity and quantum field theory do not use the same concepts of space and time. And this problem is a very big problem in the absence of an obvious solution. Therefore, there remains only a curious feeling that we are stuck somewhere in the middle. Humanity has developed two extremely effective theories. One describes the structure of the universe, Einstein's gravity in the general theory of relativity, and the other describes the contents of the entire universe, quantum field theory. And these two theories do not want to communicate with each other. For a very long time, Even physicists working in each of the two fields behaved similarly. They did not talk to each other. The American theoretical physicist Richard Feynman, a Nobel laureate for his work in quantum field theory and one of the brightest scientists of all time, wrote a classic illustrative letter to his wife explaining such an attitude. "I gain nothing from our meeting," he stated in 1962 after attending a conference on gravity. "I learn nothing because there are no experiments, so this area is not active for research, and only some of the best minds are engaged in it. As a result, there is a whole bunch of incompetent people here, which adversely affects my blood pressure. Remind me not to go to any more gravity conferences." Nevertheless, thanks to new technologies and the work of theoretical physicists like Stephen Hawking, scientists soon realized that they could not ignore what they did not know, and ideas from both sides began to be exchanged, spawning crazy hypotheses that I will discuss in the 7th part. Do you remember those quantum particles that the robot was playing with in the White Room with the metal table? There, down in the micro world, particles really take all sorts of impossible paths to get from one place to another, from one time to another, while no one is observing. So why do all the quantum aspects of all the particles that make up your body not turn you into a quantum being? Wouldn't that be cool? All the different life scenarios that you could possibly imagine would be happening simultaneously. You could be very rich and very poor, a family man and a bachelor, happy and sad, win a Nobel Prize, be mute from birth, live here and there, now and later. You could really live the entire life you have always dreamed of, and all those lives you would not want to have. But it seems that this does not happen. You are made of quantum matter, aren't you? So it should be the case, but it isn't. Why? But strangely enough, no one knows. In fact, this is related to one of the greatest mysteries of the quantum world. Why do we not see quantum effects all around us, being made of quantum particles, expressions of quantum fields, just like everything else? Why do we perceive the world the way we do, and not as particles? At the tiny subatomic level, one could argue that this is the state of affairs, that physics exists not to question its laws, but to try to decipher them. However, there is a small problem with such a modest statement. The laws of the quantum world differ so greatly from our everyday reality that there must be some sort of transition between the quantum and classical worlds, the so-called world we are accustomed to. If the particles that make up our bodies, or those in the air or in outer space, behaved like normal tennis or baseballs, everything would be wonderful. We would understand everything from the tiniest elements to the largest, but they do not behave that way. You have seen this several times during your journey through the micro world, trying to catch an electron spinning around a hydrogen atom, for example. Remember how hard it was for you to understand where it was due to its speed? Please, let's look at this fact from a different angle. Imagine that your state exchange. You are smaller than an atom. A particle is on its way to you. You know nothing, neither its size, nor its location, nor its speed of approach. You just know that it obeys the laws of the quantum world. You pull out a mini flashlight that you have with you and are ready to turn it on, expecting its light to reflect off the particles wherever they may be and return to you, informing you of its position. But to do so, you cannot take any color. You must use only the right light. Remember that light can be considered a wave. The right light here means that the distance between two successive wave crests, wavelength, must be approximately equal to or smaller than the size of your target. If you take a wavelength that is too large, the light that is present will not notice the particle at all. It will shoot right through it, like radio waves passing through the walls of a house, not even noticing them. However, light with the correct wavelength will reflect, and you will be able to determine the position of your particle with the precision of that wavelength. At the same time, you will be able to check the particle's speed and learn everything you want to know. Elementary. You twist the knob of a state-of-the-art mini flashlight to get a very powerful pulse. Adjusting, you shoot. Bam! You hit something, a particle there in front of you. The light bounced off it and returned. The time it took to travel in both directions allows you to precisely determine where the particle was at the moment of impact, and therefore the particle cannot be anywhere else. After detection, the particle loses its quantum wave characteristics. From all possible positions, it instantly occupies a position in a fraction of a second before being caught by your flashlight. During the experiment, just like when the robot threw a particle into the white room, it moved everywhere until it was detected by the sensor. This irreversible process is called the collapse of the quantum wave. After the collapse occurs, you know where the particle is with the precision of the wavelength. Now you want to know how fast it was moving at the point of detection, but that is not so easy. In fact, you will never be able to answer that question accurately. Never. Remember, the shorter the wavelength, the more energy the corresponding light must possess. Thus, the more precise the position you obtain, the more powerful the light you need to use for the flashlight, making it harder to hit the particle, and therefore the less is known about its subsequent speed. For our world, this is trivial, and this statement is: try to accurately determine the position of a moving object in the dark by shining something glowing at it. The impact will affect what you are going to investigate. If the light returns to you, you will know where the object was at the moment of collision with it. But if you shine the light again to find out where the object has moved, you will see that its speed has changed due to your first impact on it. And it is indeed trivial. However, in the quantum world, this is not just trivial uncertainty. It is a profound property of nature. It states that, for the most part, you cannot know where a particle is and how fast it is moving. This rule is called the Heisenberg uncertainty principle, named after the German theoretical physicist Werner Heisenberg, who discovered it. Heisenberg is one of the founding fathers of quantum theory of the atomic world, and in 1932, he received the Nobel Prize in Physics for it. He knew what he was talking about, but like everyone else since then, and to this day, he did not understand it. It lies beyond our intuition and contradicts common sense. The uncertainty principle immediately makes the quantum world very different from our everyday classical world. Right now, you know where the book you are listening to is in relation to your body and how fast it is moving or not moving. Therefore, you know both the position and speed with a fairly high degree of accuracy. Nevertheless, there is some uncertainty regarding both parameters, an uncertainty too insignificant to notice, and therefore it does not matter. However, in the micro world, at your micro size, you would not be able to hold the book or even the flashlight in your hands. If you knew exactly where a mini copy of that book lay, the uncertainty regarding its speed would be enormous, since you would have directed many particles at it just to determine its location and would never be able to see it. Or conversely, if you knew exactly how fast the book was moving, you would not be able to detect it by any means. It is inaccessible to observation in the micro world. Position and speed merge into a hazy concept. The same thing happens with the Casimir effect, and as technologies become increasingly refined, engineers are facing this problem more frequently. Nevertheless, the Heisenberg uncertainty principle is not a mystery. It is a fact. Strictly speaking, it is not even uncertainty. It simply states that our classical notions of position and speed are inapplicable. Nature works differently there, and we have explaining and predicting theories, quantum physics. These strange effects do reach our scales. We just are not made to feel them. They become negligible when too many particles are involved, and this is also a well-known fact. So what about the mystery we are seeking? It exists. We have released something from the calculations you just made. The collapse of the quantum wave occurs. That is the mystery. And indeed, the mysterious part. When left undisturbed, quantum particles behave like multiplied images of themselves, effectively as waves, simultaneously moving along all possible paths in space-time. Now again, why do we not sense this multitude around us? Because we are constantly probing the things around us. Why do all experiments suggest that the position of a particle suddenly makes it be somewhere rather than everywhere? Not that they knew before the experiment. The particle represents a wave of possibilities. After it, it ends up somewhere, and then somewhere forever. They are again everywhere. Strange. Nothing within the laws of quantum physics allows for such a collapse to happen. This is an experimental and theoretical mystery. Quantum physics stipulates that in all cases where there is something, it can naturally turn into something else, but it cannot simply disappear. And since quantum physics allows multiple possibilities to exist simultaneously, these possibilities must persist even after calculations are made, but they do not. All possibilities, except one, vanish. We do not see any others around. We live in a classical world where everything is based on quantum laws, but nothing resembles the quantum world. Thus arises the question, how can we make quantum effects manifest in our human scale so that we can explore them, see the wave collapse? Is it really there, with our own eyes? Is it possible? And if it were possible to see quantum effects like this, what would we expect to see? In 1935, 2 years after he was awarded the Nobel Prize for his work in quantum physics, Austrian physicist Erwin Schrödinger devised an experiment to introduce quantum effects at our scale. It involved a cat and a box. And although this was merely a hypothetical experiment, scientists continue to ask the question, is the cat alive or dead? You are about to conduct Schrödinger's experiment again, and I hope you do not love cute, purring, innocent, playful kittens too much. There is a good chance that during the experiment, something may get hurt. In any case, keep in mind that the main idea here is to make quantum effects manifest at the macro level, so sacrifices may be necessary. With that caveat, let's proceed. For those of you who do not know, a cat is a four-legged, usually furry, tailed mammal that exists in the same reality scale as most humans. They love to cuddle with them, but not all do. They come in virtually all colors except green. As far as is known, to carry out Schrödinger's thought experiment, you decided to choose a charming little black and white kitten and look for a box that closes so tightly that subsequently no one outside can learn anything about its contents, except for the cat and the box. You also need a radioactive substance, something very special, known to have a 50% chance of undergoing radioactive decay during the experiment. Radioactive materials are very unpredictable. According to quantum laws, there is no way to know in advance whether they will decay and emit lethal radiation or not. There is only a probability, one chance in two, for the substance you found. Now, you will need 3 more items: a radiation detection device, a hammer, and a vial of deadly poison. Then you connect everything together, so that if the device detects any radiation emitted by the radioactive substance, the hammer will break the vial, and the poison will spill. Nothing terrible, except for the fact that you placed all these items, the hammer, radioactive substance, and poison, inside the box and sealed the lid, and then you wait. So what happens next? There is a 50% chance that the cat will be poisoned. It all depends on the radioactive decay. A crazy experiment, you would agree. Certainly, it is not something to conduct at home. And now, the question arises, is the cat dead? Quantum effects are at play here, as desired, and the result becomes noticeable at the macroscopic level enough to see. But if you do not open the box, there is no way to know whether the radioactive decay occurred or not. So there is no way to assert whether the vial is broken or not, and consequently, whether the cat is dead or alive. Nothing new, you think. With all quantum things, one must be vigilant and use common sense sparingly, or not at all. To draw any conclusions there in the micro world, one must abide by the laws of the quantum world. In real life, one might expect the cat to be either alive or dead in the box. But then both of those answers would be incorrect. In the quantum world, whatever can happen, happens. You should use that statement now. Here, the decay and non-decay of the radioactive substance can occur with equal chances. So what happens? Both outcomes, just as a particle can move left and right from a solid post simultaneously, the radioactive decay occurs and does not occur at the same time until someone observes. As mentioned earlier, most of the time such a superposition of possibilities goes unnoticed by us because for some unclear reason it does not happen or does not reach our scales. However, in our particular experiment, the settings are made so that our eyes can see it. The simultaneous outcomes of decay and non-decay are directly linked to either the dramatic death or survival of the cat. So what do the laws of the quantum world say? They state that in events of decay and non-decay directly related to the poison, the cat, until the box is opened, cannot be considered either alive or dead, but exists in both states simultaneously. Before you open the box, decay occurs and does not occur simultaneously, just as the poison spills and does not spill, just as the cat is dead and not dead, dead and alive. Hearing this, you immediately open the box to check. The cat jumps out whole and unharmed and very cute, and there is no dead cat at the bottom. You scratch your head. All these superpositions of states, the subsequent collapse of quantum possibilities, suddenly seem like quite a complex trick rather than a real phenomenon. Perhaps you misunderstood that the cat was actually dead or alive for some time. Or is it all a deception? Let's see. Opening the box causes you to interact with the experiment, does it not? It must be so that you intervened. You observed, and when observation occurs, nature must choose. So the choice of collapse happens. It is real. It must have happened, leaving the cat alive. But did the fate of the cat freeze before you opened the box? Or did it happen to it afterward, lightning fast? You return to the original questions. Does this actually happen? Schrödinger devised his thought experiment in 1935. For many years, no one could unravel its mystery until French physicist Ewald Junger and American physicist David Deutsch developed a real experiment capable of detecting those very superpositions that existed when they should have already collapsed. Although they did not use a cat, they used atoms and light, and they saw that quantum superposition is indeed real. Any quantum particle can simultaneously exist in different mutually exclusive states. Essentially, to this day, this is the main reason engineers are trying to create quantum computers, using the ability of quantum particles to be in different states simultaneously. Computers could, in principle, achieve exponentially greater performance than what our classical computers can reach, allowing for parallel calculations to be performed simultaneously. Arash and Vine received the Nobel Prize in Physics in 2012 for this. In any case, they proved that Schrödinger's cat was indeed dead and alive at some point during the experiment. What is the secret here? It relates to the fact that superpositions disappeared. In reality, that is what Arash and Wine proved. We will have to accept this as a given. But when you open the box, when the collapse occurred and the live cat jumped out, where did the unseen possibilities go? And how was that supposed to be real at some point? So where did the dead cat go? That is the secret. Many scientists have asked themselves the same question, and recently, several proposed answers have begun to gain popularity. Some believe that the unobserved possibilities gradually dissipate like a drop of ink falling into a lake, the lake representing the world we live in, as if the pearls of unrealized possible realities disperse into one single prevailing reality of which we are a part. Others believe that our consciousness has something to do with it, and that the very act of the experiment, or even the thought of it, freezes reality in one state, thereby creating it. And here, we need the American theoretical physicist Hugh Everett, born in 1930. He is said to have been quite a strange person. Brilliant and gifted, he studied mathematics, chemistry, and physics, ultimately writing a doctoral dissertation under one of the most influential American physicists of all time, John Archibald Wheeler, from Princeton University. Although Everett stopped working in physics immediately after defending his dissertation, mainly because he apparently found it too strange, failed attempts to break into the scientific community likely also played a role. At the age of 21, forgetting about theoretical questions, he began working on top-secret weapon developments for the armed forces of the United States, and eventually died from an excess of alcohol and cigarettes. For the supernatural similarity of the fates of some well-known poets or artists who silently lived out their talents in their youth and were despised by their peers, Everett's situation, written in 1956, later became a classic. In it, he made an extraordinary statement that since quantum ideas work wonderfully in microscales, they should be taken seriously all the way up to our scale. Everything in our universe is made of quanta, so everything should be viewed as a vast quantum wave of possibilities existing simultaneously. If viewed from this perspective, no collapse will ever occur. Every possibility exists. From this perspective, the entire universe creates a branching every time a choice must be made as a result of an experiment or something else. Therefore, there must exist unimaginably many parallel universes where all possibilities, all alternative outcomes, are facts. According to Everett's theory, You must be surrounded by parallel plots. You hesitate with a decision, standing between two elevators. Before stepping into one of them, your second self, existing in a branched parallel universe, chooses the other elevator. In yet another universe, you bump into the wall between them, and in another, you go up the stairs. Thus, all possibilities are realized. In a sense, a literal understanding of quantum physics and Everett's theory suggests that if you let go of selfishness, you will never have to be upset every time something bad happens to you. In your infinitely many parallel universes, you manage to avoid it and feel happy in yet another infinity of parallel realities. And Everett is still alive and even listening to this book. Some of him like what I say, others do not. He himself wrote this book, and in it, Schrödinger's cat is a green dog. According to this interpretation, no real choice ever occurs. By its nature, all possibilities happen. You just do not know about it. It is not surprising that he turned away from physics. Certainly, Everett's theory is strange, but now it is taken seriously by some of the greatest physicists of our time, along with a wealth of mathematical models used to address the origins of space-time. Of course, there is no experimental confirmation or refutation of this claim, but it serves as an enticing reason why the reality we live in is not a superposition of quantum possibilities. The possibilities remain unused by us, but exist elsewhere. Now that you are accustomed to this idea, let's quickly summarize what you have encountered here. From the very beginning of your journey, you have traversed the microcosm, racing through cosmic realms. You have discovered what the large-scale structure of the universe looks like and how it is governed by the general theory of relativity. In the microcosm, you saw that the quantum laws of nature differ from those we are accustomed to in everyday life. Up to this point, you have traveled through all that is known to humanity, both theoretically and experimentally. You have become familiar with what the universe is, regardless of scale, from the perspective of a scientist at the beginning of the 21st century. In this section, you began to brush against the boundaries of that knowledge. You observed that not only do general relativity and quantum field theory communicate reluctantly with each other, but also that quantum laws seemingly do not govern our everyday lives for reasons that may lead some to the existence of parallel worlds. In the seventh part, you will consider even stranger things. For now, however, let's continue to exercise our imagination and leave the microcosm to return to Einstein. What about his theory? What mysteries can be uncovered there? And do they exist? Are they as long-awaited and ubiquitous as infinities that spoil quantum field theory? The answer to both of the latter questions will be affirmative. Chapter 4. Dark Matter. Forget about cats, dogs, and parallel universes, alternative realities. Forget about the quantum world. Forget about mini-copies. Right now, you are in space, in the form of consciousness. You have seen that the microcosm is filled with mysteries and intend to test whether Einstein's theory works everywhere. It has its shortcomings, even without attempting to turn it into a quantum theory. So you are in space, the Earth behind you, and you are flying forward. You pass by the moon and the sun, heading towards neighboring stars. Up to this point, Einstein's theory of gravity works superbly. Stars and planets move as they should. You are moving from the Milky Way into the intergalactic medium, where you come to a stop. The Milky Way lies directly beneath you, while other galaxies shine in the distance. A massive spiral of hundreds of billions of stars emits light in the impenetrable dark universe. From what you have learned about gravity, you know that just as with planets around the Sun, the speed of any star within a galaxy cannot be random. Stars flying too fast will inevitably leave the safe haven of the galaxy. These lonely luminaries are doomed to wander eternally through the vast expanses that separate individual galaxies from one another. If stars were to fly too slowly, they would roll down the slope of space-time created by all the other stars, a slope that would cause them to indeed move towards the core of the galaxy, the central bulge filled with stars, where they would ultimately be swallowed or destroyed by a giant black hole patiently waiting for its victims. Without the necessary speed to maintain a stable orbit, a star either leaves its galaxy or is doomed to fall, just like a marble. It either rolls to the bottom or flies out of it. Remember how Newton's law of universal gravitation failed when gravity seemed too strong near the Sun? His equation requires correction to account for the precession of Mercury. Einstein discovered these corrections to revolutionize our vision of space-time. And now, after 100 years, it is Einstein's turn to face the change in scale. What about the action of Einstein's theory of gravity concerning entire galaxies? Does his theory of curved space-time work when faced with hundreds of billions of stars instead of just one? That is exactly what you are going to test. You pull out a stopwatch and start timing the movements of stars in the Milky Way, simultaneously counting the speeds of 300 billion stars. And just for that reason, you start at the outskirts of the galaxy, at the end of one of the magnificent spiral arms, far from Sagittarius A, our own supermassive black hole. You time 10 seconds, during which the star you are observing travels 2,500 kilometers. Not bad. That corresponds to an average speed of about 900,000 kilometers per hour around the center of the galaxy. Quite impressive. Neighboring stars move almost as quickly. In fact, any two stars at the same distance from the center of our galaxy have the same speed. The slowest stars are located far from the center, while the fastest, like the sprinter star S2 you encountered some time ago, lie deep within it. And if you are curious about how long it takes for such outliers to complete an orbit around the Milky Way, the answer is about 250 million Earth years. A long journey. The Milky Way is vast. The Sun, and thus Earth, being a bit closer to the center, takes nearly 225 million years to orbit the Milky Way, a period known as a galactic year. The last time Earth occupied the same position in the galaxy as it does today, dinosaurs still had 160 million years of peaceful existence left. If we start counting from today, in another 20 orbits, the Milky Way and the Andromeda Galaxy will come close enough to begin colliding. By the way, the Sun will explode a few galactic months later. Considered in this way, this event does not seem so distant. Wonderful, and thank you for that. It seems there are no issues here with Einstein's theory, except that there is a problem. To be frank, you are not the first to check the dynamics of star rotation around the galaxy. Their speeds have been known for quite some time, since the early 1930s, when Dutch astronomer Jan Oort made measurements. But Oort went a bit further. First, he estimated the amount of matter contained within the entire Milky Way, then checked whether the speeds he observed matched the expected speeds for those stars that do not fall or leave the galaxy. They did not match. Not at all. Being here above the Milky Way. You can check this for yourself by adding up the mass of each star with the cloud of dust and everything else visible belonging to the native galaxy. You will arrive at the same mysterious conclusion. There is definitely not enough matter here to keep any star from being ejected from the galaxy given its speed. And unlike the discrepancy in Newton's theory regarding the orbits of Mercury, the divergence here is far from tiny. There must be 5 times more matter than what you can see. Otherwise, all stars, including the Sun, would be flung out of the galaxy. You must have missed something. And Oort is also missing not just a few 100 million stars and the dust surrounding them. Otherwise, you could blame yourself or Oort for a careless count. By the way, that would be fine. But a 5-fold excess? What is going on? And who exactly is this Oort? Can he be trusted? He was not just an ordinary astronomer. In fact, his incredible ideas helped humanity figure out much of what you saw during your journey through the solar system and the Milky Way. In the first part of the book, he is credited with demonstrating that the Sun is not at the center of our galaxy. This fact may seem obvious now, but it was not until Oort proved it. He is also the person who hypothesized the existence of a vast reservoir of comets, billions upon billions, now known as the Oort cloud, located at the outer edges of the solar system before entering the gravitational field of the red dwarf Proxima Centauri. Oort was an unusual scientist, following up in 1932 by explaining the absurd discrepancy between the visible matter of our galaxy and the speeds of the stars. Making a surprisingly bold assertion, he claimed that the Milky Way is filled with an unknown type of matter that has never been detected in any form, neither here on Earth nor anywhere else, because it does not interact with light, making it impossible to observe with any type of telescope. Oort named it dark matter. According to his work, the effects of dark matter manifest only indirectly through gravity. Dark matter cannot be seen, but it curves space-time just like ordinary matter, although it is certainly not the same. It may not even consist of the same particles that make up everything we are familiar with. Otherwise, we would be able to see it. Such a discovery may seem too enormous and captivating to be true, but as good as Oort was, no one is perfect. He could be wrong. To find out, you decide to look at other galaxies to observe their movements around each other, just as Swiss astronomer Fritz Zwicky did about a year after Oort's initial statement in 1933. If dark matter seemed real, present, and gravitationally active not only within the Milky Way, but also outside and within other galaxies, it would not only alter the orbits of stars moving within a galaxy, but it would also affect the orbits of galaxies rotating around each other. So you closely examine and analyze the captivating cosmic dance of vast clusters of bright stars, and you are left with no more doubts. Just like Zwicky, you are forced to acknowledge that all galaxies are rotating too quickly around each other, without hiding a vast amount of gravitationally attractive dark matter. Dark matter is neither matter nor antimatter. It is something else. No one knows what. All the numerous experiments conducted since the 30s have come to the same conclusion. Dark matter exists. It is everywhere. There is matter, over which dark matter is wrapped, and although I have tried, throughout this book, to show you all the knowledge of the universe that I would like to share with you on this matter, I must admit that I cannot introduce you to it more closely. Why? Because even today, More than 80 years after Oort's bold hypothesis, we still have no idea what this dark matter is made of. We know it exists. We know where it is. We have maps of its presence inside and around galaxies throughout the universe. We even have strict conditions for what it must be, but we have no clue what it actually is. And for every kilogram of ordinary matter, made up of neutrons, protons, and electrons, there are 5 kilograms of dark matter, which is made of who knows what. Dark matter is the #1 unexpected gravitational mystery. It may mean that Einstein's theories do not work at such scales, just as Newton's theory did not work near the sun. But many independent studies have been conducted. Dark matter seems to truly exist all around galaxies, around our own Milky Way, and throughout the universe, and you cannot see it. It seems that there is much more invisible than visible in the entire universe, leading to dark energy. Billions of years have passed since the dark ages of our universe. Numerous galactic catastrophes have occurred. Entire galaxies have collided and merged in the harsh cosmic void. Everywhere you look at galaxies, only the visible part, dark matter exists in overwhelming quantities, 5 to 1. It cannot be seen, and still, there is so much of it that it must have played and continues to play a role in the cosmic waltz you are observing. The waltz performed by clusters of stars wrapped in invisible cloaks of dark matter. The more you observe all these galaxies rotating around each other, the more dancers and figures you see, and the more inhabited worlds with completely different skies from our own. You begin to imagine there, and suddenly you start to wonder, what if some distant civilization has already found answers to our human questions? And then you freeze in place, blinded. A very powerful source of light has struck your eyes. You squint into the night, determining where it came from, and again, just as suddenly, you are hit by another beam of light coming from somewhere unimaginably far away. And another one. It pulls you out of your reverie. We focus on the galaxies from which these light signals seem to originate. For some unknown reason, your heart races like crazy. You watch the beams of light, observing how the galaxies drift apart, continuing to swirl around each other. Something is wrong. The galaxies from which the light is coming are not moving apart in the way they should. We are not talking about their rotation around each other, but about the expansion of the universe, how all galaxies are moving apart, like poppy seeds rising in pie dough. Given what you have learned about this expansion, the galaxies are moving incorrectly. This is the second unexpected gravitational mystery, and it suggests much more hidden energy than dark matter. To understand, you need to know how distances in the universe are measured. When you emerge onto the beaches of a tropical island, just before beginning your journey into space, how might you determine which star in the night sky is closer and which is farther away? Obviously, brightness alone is not enough. Stars come in virtually all sizes, and their practical luminosity can vary greatly. A bright star, viewed from Earth, could be huge and very distant, or it could be small, but much closer. You need to use some other method. Historically, scientists have devised 3 different methods for estimating cosmic distances. The first one pertains to any object, whether a planet or a star, that is relatively close to us. It is the simplest of all and uses common sense. There is nothing quantum about it, so common sense is allowed. Imagine you are looking at a tree through the side window of a car speeding down the highway. Trees growing close to the road rush past quickly, while those farther away seem to move at a much slower pace. Mountains on the horizon sometimes appear to freeze in place. They can be used as a stationary background. The same concept applies in space. As Earth orbits the Sun, nearby objects exhibit a single motion, quite evident against the backdrop of very distant stars that appear motionless. Checking how an object's position changes relative to this background while Earth revolves around the Sun allows scientists to determine how far away the object is in space. The method involves mathematics that Euclid would have understood 2,200 years ago. It works very well for estimating nearby distances within the Milky Way, but it does not work for determining galactic distances. Galaxies are simply too far away. When you are on Earth, rotating around the Sun, your view of the cosmos can change over 300 million kilometers from summer to winter, but that is not enough to see their movements. Galaxies still appear as part of a stationary photograph. To find out where they are, you need method number 2, which involves a very specific type of star called Cepheids. Cepheids are very bright stars whose luminosity fluctuates between maximum and minimum intensity with impressive regularity. Remarkably, scientists have figured out a way to link this fluctuating period with the total amount of radiation they produce, and that is all they need to know to determine their distance. Just as the sound of a horn fades as it moves away from its source, so does light. Studying the light emitted by distant Cepheids, gathered on Earth, ultimately gives distances to them. Fortunately, there are many Cepheids, but this method also has its limits. For measuring large distances in the universe, individual Cepheid stars can no longer be used because even the most powerful telescopes cannot distinguish them from neighboring groups of stars. To explore the farthest corners of the universe, a third method is necessary. You may remember from the second part of the book the work of American astronomer Edwin Hubble. In the 20s of the last century, Hubble became the first person to observe distant galaxies moving apart and the expansion of the universe. Some of your friends have kindly confirmed this fact by observing the night sky around Earth with their billion-dollar telescopes. In the 20s, Hubble used the spectral shift of Cepheids in distant galaxies to determine their speed and found that their tendency to move away from us is proportional to their distance from us. A galaxy that is twice as far from us is moving away from us twice as fast. This law is now known as Hubble's law. Method number 3 involves using Hubble's law from the opposite side. When Cepheids cannot be distinguished from their surroundings by changes in the spectral shift of distant galaxies, scientists can determine how far their light has traveled during the expansion of the universe. Thus, they can find out how far away a galaxy is right now. Hubble's law is quite simple and aligns well with known facts. Space and time have become what they are now. Several billion years ago, space-time has since expanded, and what seems normal in an expansion caused by the intense release of energy from the Big Bang. The rate of expansion slowed down over the next 7 billion years. With such a fairly logical setup, everything goes wonderfully, except that it does not match what you have just seen. The flashes of light you caught with your eyes diverge from the law. The spectral shift does not correspond to the magnificent, beautiful, cohesive picture described above. Something is wrong, and mystery number 2 is stuck somewhere. To find out what is going on, let's take a little walk and look at what caused the extraordinarily powerful flashes of light that struck your eyes. Starting your journey from the Milky Way, you head towards a particularly beautiful and colorful spiral galaxy lying 8 billion light-years away from it. You traverse the vast distances separating our cosmic family from this other island of light, and as you approach it, you swoop in from the side. You zoom past millions of stars, through clouds of dust the size of 1,000 solar systems combined, and suddenly you stop again. Right before you are not one, but two shining objects that catch your attention. They are spinning around each other very quickly in a slightly asymmetrical manner. One of them is a giant, wicked red star. The other is also a bright star, but many times smaller, the size of Earth and Snow White. But do not let the size difference mislead you. Despite the enormous difference in size, the tiny star is the master here. They are a red giant and a small white dwarf, the remnant of a star that exploded several 100 million years before your arrival. During the star's demise, its outer layers exploded in all directions, while its core collapsed into a coma and became what now shines right before you. The white dwarf is an extremely dense, hot object. Ordinary white dwarfs cool down over tens of millions of years and are ejected from galaxies, eventually becoming cold, dark, lonely cosmic wanderers. But this dwarf has chosen a completely different path. To give you an idea of the density of a white dwarf, let's make a baseball out of various materials. An ordinary ball, made of rubber, leather, and air, weighs about 145 grams. The same volume filled with lead would represent a ball weighing 2.5 kilograms, filled with the densest chemical element found on Earth, osmium. The ball now weighs about twice as much, around 4.5 kilograms. Now, let's fill the same volume with the material that makes up a white dwarf, and we get a ball weighing 200 tons. In the realm of extremely dense matter, white dwarfs rank third, right behind neutron stars, which are so named because they contain only neutrons, and black holes. Therefore, inside, just like within stars, one would expect extremely turbulent nuclear fusion reactions, but they do not occur unless they find a way to grow in size. To be honest, a white dwarf remains a white dwarf as long as it contains less than 140% of the mass of our Sun. But this dwarf really has a feast ahead with the red star. This red giant will be devoured alive right before your eyes, as the helpless gravitational field caused by the supernatural density of the white dwarf dooms the star. It cannot even hold on to its own outer layers. As it orbits the dwarf, its surface is torn away, creating a long trail of bright, searing hot plasma that spirals down towards its dance partner, forming a sparkling, twisted cosmic river that flows towards the surface of the white dwarf, where it is captured and compressed. Here, astonishing energies are at work. Even space-time itself can feel them, like waves rising on the surface of a lake due to two boats spinning around each other. The gravitational waves, generated by the dance of the red giant and the white dwarf, create a pulsation that spreads through the very fabric of the universe, a sight that alters space and time, washing over nearby objects. And as you watch them, more and more matter from the giant star falls towards the surface of the white dwarf. And you are not without reason to feel that something extraordinary is about to happen. The white dwarf has indeed gained quite a bit of weight, reaching 140% of the mass of the Sun. The critical pressure threshold in its core suddenly becomes sufficient to trigger a new, astonishingly violent chain reaction, leading the white dwarf to a remarkably spectacular demise. In the blink of an eye, it explodes, an explosion 5 billion times brighter than the sun. An impressive swan song. Such events are called type Ia supernova explosions, and they occur roughly once every 30 years in any given galaxy. They are incredibly convenient for astronomers because they are all very similar, even identical. They always arise when a white dwarf reaches 140% of the mass of the sun after siphoning energy from another star, and therefore they always shine with the same light. 5 billion suns combined into one tiny dot, not much larger than our Earth, but much brighter. They are perfect candles, allowing researchers to explore the farthest corners of our universe and test Hubble's law of expansion. And they are so much brighter than everything else that, unlike Cepheids, man-made telescopes can distinguish them from distant galaxies, knowing their true brightness. Just like with Cepheids, scientists can infer how far away they are based on how quickly they are moving away from us. In 1998, two independent groups of scientists studying such distant supernovae published their results. One group was led by American astrophysicist Saul Perlmutter, and the other by American astrophysicists Brian Schmidt and Adam Rees. Both teams discovered that about 5 billion years ago, after more than 8 billion years of normal behavior, the expansion of the universe began to accelerate. The scientific community was shocked, just as you are. Not only was this conclusion unexpected, but it was radically opposite to the only acceptable result. In large scales, everything is governed by Einstein's general theory of relativity. Einstein's theory of gravity, like Newton's law of universal gravitation, allows only for the attraction of objects to one another. Therefore, no matter what fills the universe, whether it be matter, antimatter, or dark matter, it should ultimately slow down any expansion, not accelerate it. However, the observations of Perlmutter, Rees, and Schmidt indicated the opposite. The only possible way out of such a contradiction was to find something entirely new to explain this acceleration, and that something had to fill the entire universe and possess the exceptional property of acting as an anti-gravitational force, pushing matter and energy away instead of attracting them. For some unknown reason, this new force overwhelmed all other large-scale forces in the universe about 5 billion years ago. Before that, its influence was zero. This highly puzzling energy was named dark energy, and strangely enough, as a result of calculations and observed effects, there must be a great deal of it. According to recent estimates, its quantity is actually 3 times greater than that of dark matter and 15 times greater than that of ordinary matter that makes us up. For their discovery, namely, that the expansion of the universe is accelerating rather than slowing down, the first actors Schmidt and Rees were awarded the Nobel Prize in Physics in 2011, and the entire energy content of the universe had to be completely recalculated. Today, NASA's satellites estimate that the universe consists of the following: dark energy, 72%, dark matter, 23%, and ordinary matter, including light, 4.6%. Everything you have seen so far during all your travels corresponds to only 4.6% of the total content of the universe. The rest is unknown. However, unlike dark matter, The existence of some form of dark energy was acknowledged even 100 years ago by Einstein himself. He even called it his greatest blunder, although today it seems that his blunder was precisely in calling it a blunder. Part 2. You remember that Einstein disliked the idea of a changing, evolving universe. He preferred to think that time and space were, are, and always will be as he experienced them. Unfortunately, his general theory of relativity in its simplest form asserts the opposite. It states that space-time can change and is changing. To allow for the possibility that the universe did not evolve, he believed he could somehow modify his equations, seeing in them a new, uniquely acceptable additional term. At the time, this was a bold gesture. Einstein's equations implied and still imply that the local energy content of the universe is entirely equivalent to the local geometry. So, if one of the two terms can change, the other must too. Adding a new form of energy somewhere in the equation, therefore, altered the formulas governing the dynamics of the universe. By energy, Einstein meant anything that possesses a gravitational effect, which now includes matter, light, antimatter, dark matter, and everything else that carries a sufficiently attractive gravitational nature. But the term added by Einstein could carry this other character, attractive or repulsive, depending on its mathematical value. In a physical sense, it corresponded to energy that truly fills the entire universe. He called it the cosmological constant. Thanks to it, the universe could be static, obedient, conforming to his philosophical views. Comforted, Einstein could once again sleep at night. However, about 10 years later, Hubble's work turned the expansion of the universe into a proven fact. The static universe no longer existed, so Einstein crossed out his cosmological constant and called it his greatest blunder in the equation. Now, 100 years later, it seems rather ironic that what he erased on paper could become such a necessary tool for theorists, required to explain humanity's greatest unresolved mystery, dark energy, which governs the accelerating expansion of the universe. The cosmological constant could make the universe the complete opposite of static, undergoing accelerated expansion. It could solve the puzzle of dark energy. The only issue in this case would be figuring out its own source. We will return to this in the 7th part, but for now, I would very much like everyone to allow for such blunders as Einstein's, whatever dark energy may turn out to be. The idea of it has already changed our view of cosmology. Before the discovery of the Pearl motor by Rees and Schmidt, two possible futures were envisioned for the universe, depending on its ultimate content. In the first case, too much matter would cause expansion to inevitably reverse at some point, and gravity would overcome everything else. In this scenario, the entire universe would collapse, ending in what is called the Big Crunch. This is like a Big Bang in reverse, accelerating over time and not rewinding. The second option is that there will not be enough matter or energy to prevent the universe from running away. The presence of dark energy in the Pearl motor by Rees and Schmidt suggests that this is the most likely future, unless some surprise comes into our telescopes one fine day. That is, the chances that an anti-gravity field will facilitate expansion lead to a future big freeze. Both predictions, the Big Crunch and the Big Freeze, represent rather grim prospects. But, as you will see in the next part, such a freeze may not be the end at all. I reiterate, it is also possible that Einstein's theories are simply not applicable at such vast scales. In that case, we cannot use his equations to conclude the existence of dark energy, just as Newton's theories, tested near a large star, led to erroneous calculations of orbits. Einstein's equations could well have diverged from reality at some point. However, as of today, it is most likely that dark energy is real, and there is even a possibility that it has a quantum nature, a very exciting prospect for all those scientists who would like to connect the micro-world with the mega-world. In any case, whatever dark matter and dark energy may be, they are very important. Newton's law of universal gravitation helped us discover new planets around the Sun, while Einstein's gravitational theory has led us to mysteries far more serious, so serious that they may contain hints or keys that open the door to unknown worlds of our large-scale reality. With the necessary humility, such discoveries are quite impressive. And now, it is time to understand why the general theory of relativity cannot be a theory of everything, and why it predicts its own demise. Chapter 6. Singularities. Remember quantum infinities? Remember the catastrophic consequences for space-time of an infinite number of particles appearing everywhere and all the time in the vacuum of quantum field theory? To study it, scientists had to either discard gravity and treat infinities as if they did not exist, or ignore those in the micro-world. Everything worked perfectly until gravity became quantum. Now let's set aside all the quanta for a moment. What about gravity itself? Is it possible that the matter we know, classical matter, with which we interact daily, exerts the same influence on the fabric of the universe? Could it lead to the collapse of space-time? The answer is definitely yes. And this time, we will even see the result in the sky. A good analogy is a multitude of very heavy marbles thrown onto a thin rubber sheet. Due to the created curvature, nearby marbles will move closer to each other, forming a pile that causes the rubber to sag even more, with each new marble rolling down and joining the group. The rubber becomes more and more concave. At some point, either because all the marbles roll down or because the remaining ones are too far away, the process will end. Nothing strange. But if the rubber sheet is soft, like chewing gum, if it is not strong enough to hold the pile of marbles in equilibrium with its own tension, it may continue to sag more and more, even if no more marbles are rolling in. No material has yet been tested that is strong enough to withstand any weight. Hence the idea of threshold density. If too much weight is placed on too fragile a surface, the surface around that mass will distort until its integrity is compromised. Now, what about space-time? While it is not expected to rupture, space-time reacts to very high densities, perhaps even more dramatically, because the fabric in this case is not rubber, but space and time themselves. Space-time is not flat. It is volumetric. The fabric of space-time bends, curves, and stretches around the objects contained within it, whether they are matter or any other form of energy. This understanding Einstein continued to accumulate, regardless of the form of energy in a given volume. Like with rubber, you will ultimately have to confront a problem. Beyond a certain threshold, nothing can stop the increasing curvature of space-time, even if nothing else is falling into it. As the curvature continues, what began to bend gradually compresses, resulting in increased density, creating a vicious cycle that inexorably leads to the collapse of space-time. The collapse is exacerbated by infinities that the general theory of relativity cannot handle. Such infinities are called singularities. They are not the same as the quantum infinities you introduced earlier. They have nothing to do with quantum processes. They arise when too much mass or energy accumulates in too small a volume. They are localized, and the possibility of their existence heralds the collapse of Einstein's theory of gravity. In the late 60s and early 70s, when nearly everyone was going crazy, listening to psychedelic music or searching for new fundamental particles, English physicists and mathematicians Roger Penrose and Stephen Hawking proved through a set of famous theorems that such collapses must occur in the universe, governed on large scales by the general theory of relativity. With their theorems, they showed that Einstein's general theory of relativity had very modest predictive characteristics regarding its own demise. Just as Newton needed a more complete theory to explain Mercury's motion, it became clear that Einstein's theory needed to be expanded at least to explain these collapses and where they occur. You might ask yourself, can they be found in nature, or are they purely theoretical fantasies? They are real, and I am sure you know where to find them. However, such a singularity, the mother of all others, lies in the past of the universe, when all energy was contained in a catastrophically small volume. In a sense, our universe was born from such a singularity, and since then, space and time have become what they are today. Another singularity lies deep within all black holes, amplifying the universe. Contrary to what many think, black holes are the opposite of emptiness. They are born when, due to some catastrophe, too much matter ends up in a rather small volume. As you will hear later, such a process can cause the death of a giant star. The question that has simultaneously troubled and excited many brilliant minds since the emergence of Penrose and Hawking's theorems is this: since singularities likely occur in nature, how can we even begin to imagine what happens inside them? How can we even think about places where space-time no longer makes sense? What theory can be used to study such catastrophic collapses? A theory that encompasses both the mega and micro worlds, both black holes and the origin of the universe, consists of an enormous amount of matter and energy confined to a very small volume. The answer must include theories that mix gravitational and quantum processes. And regardless of the theory we choose to understand the universe, better than Einstein's, it must incorporate the quantum aspects of gravity, that is, space-time. Penrose and Hawking proved that Einstein's theory of gravity has limitations, that it cannot explain the entire universe. Its past, in which it stands, collapses even before the birth of space-time, even before anyone delves into what lies at the bottom of modern black holes. Given the above, one might think that all the blame for the difficulty of finding a quantum theory of gravity lies with gravity, Einstein's brainchild. But you have seen that this is not the case. There are also problems associated with the quantum view of the world. Nevertheless, no matter how difficult the task may seem, you will now attempt to connect both theories, for it is time to dive into a black hole. Chapter 7. Gray is the new black. Given the situation, you feel extraordinarily well. You are not an ethereal body. You cannot see through yourself, and your arms and legs, and everything else, positively respond to commands to move. You are flesh, bones, and blood, and your heart beats as usual. A slight pain in your neck confirms that you feel the same as on Earth, but you are in outer space. Your guide, a robot with a tin yellow body and a particle ejection tube, flies alongside you, as material and real as you are. You look around. The futuristic airport has disappeared. You recognize nothing, but you suspect you must be inside some galaxy near its center. Billions and billions of stars shine as usual everywhere, except for the patch right in front of your eyes, a black spot of space-time devoid of light. Outpacing the robot, you realize that the dark patch moves against the backdrop of the stationary stars, and it is already close, hanging in space. The void is a dark threat looming over everything and everyone. You know what it is. It is enormous, almost 10 billion times the mass of the sun. But this black hole bears no resemblance to the one you saw at the center of the Milky Way. There is no surrounding ring of flame, nor are there any stars nearby that are about to fall into it. This black hole has already devoured and digested everything that was once nearby, as well as almost all the cosmic debris. Now it is completely clean, with no food except for the occasional meteoroids that stray off course due to distant catastrophes. Some of them are on a path toward it. If there is even a hint of quantum gravity down there, we will find it, the machine announces. This danger is sewn in. You are, of course, this black hole. You look again at the black hole, comparing it to the one you encountered at the beginning of the book. There is no jet of light erupting from its poles. There is only a fairly round, flat black spot of emptiness. You spiral down the created slope of space-time. During the fall, the images of distant stars passing near the edges appear distorted and are not where they were mere moments ago. The source of light becomes small, bright streaks covering the outer edge of the dark disk, and then they disappear as if swallowed by the dark void before reappearing on the other side, where the sequence of distortions is reproduced again, but in reverse, until they once again resemble distant sparkling points. Light seems to distort with this hole, apparently expanding from within, while its edges act like a curved lens. Accompanied by the robot, you continue to spiral down. You are still quite far from what will turn out to be the black hole, but you already feel doomed, and suddenly you want to flee before it is too late. Whatever that means, whatever the robot shows you upon arrival at your destination, look over your left shoulder, says the robot. After a minute of silence, you turn around. Huge chunks are heading straight for the black hole. This rotating asteroid the size of a mountain rushes by at an astonishing speed of about 100 kilometers from you. You focus your gaze on the dark silver surface of the asteroid, the only object moving toward the black disk of the black hole. The true size of the asteroid shrinks as it moves away. Now it is the size of a peach at arm's length, and now it is the size of a small distorted nut. And then suddenly, as your spiraling fall takes you to the other side of the black hole, two images of the asteroid appear at once, one to your left and the other to your right. The distortion of space-time around the dark spot is such that light seems to have the opportunity to reach your eyes by several paths. The asteroid will soon fall in, the robot says, almost regretfully. Fall in? You ask, increasingly worried. What do you mean by fall in? Through what? Through the horizon? Through what? Through the event horizon of the black hole, the point of no return. Will you see it or not? No person or machine has ever been this close to a black hole, let alone been inside one. There is a theory about what is supposed to happen down there, but it could be wrong. Shouldn't we get too close to it? You suggest. Or maybe we should, replies the robot. This is exploration. We will have to accept some possible risks, or else search for the horizon everywhere, directing your tube left and right. The robot alternately points to two opposite spots near the edge of the black hole in the direction of the two images of the asteroid. Between them, now shifting your eyes from one image to the other, you expect that they will both continue to fall and disappear beyond the horizon into the hole. But by the time you complete another full rotation, the small, nut-sized silver-brown asteroid is still hovering over the dark void. Strangely, it seems to have changed not at all since the last time you were above it. Moreover, it appears that it is no longer going to move or spin. It is not falling. You cry out in relief. So maybe you are not in danger today. It seems to be torn apart in the pile of the black hole. It is falling, the robot corrects you. It is no longer there. Very funny, it has disappeared, insists the robot. Only its image remains. That is, the distortion of space-time in the actions of space and time. Our time, yours and mine, does not flow the same way. From the asteroid, it is already beyond the horizon. Its image is still on the horizon. How can that be? Just as you realize this, another object rushes past you through the void, this time a sparkling stone. It looks very much like a huge diamond, and is indeed one. Some stars, when dying, can leave behind diamonds the size of the moon. Watching its fall, you complete another loop around the black hole, realizing that you have gotten much closer to it than before, and are moving much faster. Another series of loops and several images of the asteroid and the diamond are nearby, as if frozen in surreal darkness, becoming more and more distorted. And the same happens with everything you observe. You are not told that your eyes, the robot, is right again. The asteroid and diamond have irretrievably disappeared, and the black hole has grown in size, having absorbed both of them, or at least its horizon has expanded. And what did you want to make me see? You ask the robot. How does an empty hole grow by swallowing things? Black holes are by no means empty, the robot ominously states. In fact, black holes are the complete opposite of emptiness. This is not what happens when too much matter and energy end up in too small a space. Creating one requires colossal energies. As far as we know, only the largest of bright stars emit enough energy to die by collapsing their cores into such a hole. Earlier in your journey, you encountered white dwarfs, and white dwarfs are the results of such collapses, but they are not as extreme as black holes. All types of such residual stars are impressive, but black holes surpass them all. And since we are here, while you spiral down for a couple more loops around the black hole you are inexorably approaching, let me name another reason why they are so frightening and mysterious. If you were to find yourself on any object in the universe, whether it be an asteroid, planet, or star, you could send a light signal from there, determining your position. But the denser the object you find yourself on, the more energy your signal must have to climb up the slope created around that object in space-time. It is just like with a bowl. The deeper it is, the faster you need to accelerate a marble at the bottom to spiral all the way up and get outside. Sitting on a planet, star, or white dwarf, you must successively send more and more energy to send a signal into space to escape its pull and fall back into the black hole. And worse yet, they contain so much matter and energy, and therefore create such a steep space-time slope, that anything unfortunate enough to come too close is doomed to fall in. According to the general theory of relativity, nothing in our universe has enough power to escape the gravitational capture of a black hole, not even light. The point of no return, beyond which nothing can escape, the event horizon of a black hole lies somewhere where the images of the asteroid and diamond seem to have frozen. If you look at them from beyond its limits, the darkness continues to grow before you, like a huge mouth ready to swallow your real essence. Distant stars now look completely different everywhere. You even have a disorienting feeling that what you see before you is actually behind you. Turning your head, you realize that this is not just a feeling, but a real fact. The light emitted by the shining stars behind you, moving at its usual speed, overtakes you and rushes down the slope created by the black hole. All rays spreading to the left of the monster reappear on its right side, as if they are turning 180 degrees on a roller coaster, and then these rays turn toward you, blinding you. Therefore, looking ahead, you see what is behind you. From where you are, it is actually possible to see the entire universe just by looking forward. And as you continue to spiral down, everything becomes even more confusing. The images of the asteroid and diamond have now come back to life as you get closer to them, your time converging, and suddenly they disappear altogether. You just saw them cross the horizon, which you incredibly passed a few hours ago in their own time. The robot, flying alongside you, has turned around, its tube now pointing toward space. You too slowly turn around, fearing what you might find there. What you see lies beyond imagination. All the stars everywhere, which a second ago seemed to be frozen, are now moving. The absence of their stillness is generally imperceptible, even over stretches of human life. Now it is clear to you that starting from the nearest and ending with the farthest, they are all rushing through space and time. Some of them are moving so fast that they even leave a trail on the retina of your eyes, risking to blur the curves of light on your picture of the universe. Just like before, when you sped through the universe, getting closer to the speed of light, you witnessed the lives of the astronaut, his children, and his children's children flying by in the past, and their time accelerated compared to yours. At that moment, your time and theirs were different due to your speed. This time, all of this happens because of gravity, due to the distortion of space-time caused by the presence of a black hole. And here, around the black hole, your time flows more slowly than anywhere else. You see the unfolding future of the universe, and this again implies what space and time practically mean, combined into space-time. Have we crossed the horizon yet? You suddenly ask anxiously. Or do we still have to go inside? The robot turns around again to look at you, and you are greatly surprised to realize that its tube has expanded. In fact, it looks as if it is now intended to eject not particles, but bowling balls. We have not crossed yet, it replies, but you are just about to. If you were more prudent, you would say that you detected a note of pleasure in the robot's voice. But before you can react, it shoots a heavy projectile straight at your chest. You cannot avoid the blow, and you have no choice but to catch the flying projectile. Instantly, its speed pushes you down toward the gaping darkness. You scream, desperately trying to grab onto something, trying to stop your fall, but there is nothing around to hold on to. You fall, the robot drifts away. 1 second of yours corresponds to 1 minute of its time, then to an hour, then to a day, then to a year, as the robot continues to retreat. Millions of years pass before you. Stars explode, new stars are born, and you see it all. Billions of years have already passed. Outside the hole, another galaxy merges with the one you are in. The robot is nowhere to be seen. You are left to yourself, and you panic. You have crossed the horizon of the black hole, stunned. You look into the future, engulfed in fear. It is impossible to focus. You fall into the abyss, gazing upward at the unfolding life of the universe, while you yourself disappear into the abyss of unknown non-existence, at the bottom of which lies a singularity. And now you lower your gaze to look into it, into the mysterious heart of the black hole, where, in contrast to non-existence, the very matter that creates all this nonsense must be formed somewhere. In this absurdity, to your great surprise, you see nothing more, not even your body. No legs, no nose, not even your own hands. Light may fall on you from above, coming from outside, but nothing can rise from within, from any direction, regardless of its proximity. There is no light. There is not enough energy for that. You have crossed the horizon of the black hole and are now doomed to fall eternally toward the surface of many destroyed stars, merged during infinite descent until space-time is stretched too far for Einstein's general theory of relativity with unknown consequences. In fact, if you were truly there, you would be dead. For if even light cannot make the tiny journey from your feet to your eyes, there is no way blood could travel up the slope of space-time you are sliding down to reach your brain. But since there is still much for us to see, we assume you are still alive. Not wanting to look into this bottomless darkness, you decide to gaze upward at the universe and how the images flow down toward you through the now overflowing horizon, but you cannot. Any movement suggesting the relocation of any part of your body, upward, outward, is forbidden. It would require energy that even light does not possess. No upward movement is permitted. As soon as you begin to wonder if there is anything worse than this, tidal forces begin to torment your body. The gravitational influence of the invisible presence of the black hole now begins to pull your legs down harder than your arms and head. The gravity of the black hole stretches your body. You are going to end your life elongated like spaghetti. Even if a treacherous robot armed you with the most powerful rocket engines ever invented, it would change nothing. Regardless of the engine's power, as soon as you tried to move upward toward the horizon of the black hole, you would feel yourself being stretched on the slippery taut fabric of space-time. It is an infinitely working treadmill, whose speed always exceeds yours by a wide margin, dragging you down. According to Penrose and Hawking, you have been pulled into the gully of space-time lying somewhere down there, in the singularity that will never be seen from space. No beam of light is allowed to penetrate beyond the horizon of the singularity hidden down there. The very concept of space-time breaks down, just as it did some time before the Big Bang. No one has ever been able to penetrate the heart of a singularity and come out to tell about it. Such places, it seems, must forever remain shrouded in mystery. According to the general theory of relativity, neither you nor anyone belonging to you will ever be able to escape from there. Sad thoughts, especially now that you are completely torn apart, transformed into a long thread of those particles that make up your body. Sad thoughts, but we should not trust the general theory of relativity down there, for we must remember that the general theory of relativity is not a quantum field theory. And at that moment, hope immediately returns. You transform into a mini copy and wait. At first, nothing happens. And then surprisingly, you see that all the elementary particles that make you up disappear or leap out. To be more precise, they essentially make a quantum leap. And now they are outside the black hole, where, to your good fortune, they reassemble into a mini copy of you. And there you are, greeted by the robot. At that moment, you are very tempted to pounce on it and try to rip the metallic tube from its body, seeking revenge for the shot that pulled you beyond the horizon of the black hole. But before you can do anything, the robot's metallic voice rings out. I have been waiting for you for about 10 billion years. I am glad you recognized me. And suddenly, you lose the resolve to hurt it. Moreover, there are more important things to think about, not least about what you just experienced regarding gravitational and quantum fields interacting with one another. Everything around and the stars are moving again imperceptibly. 10 billion years have indeed passed since you were thrust beyond the horizon of the black hole. You look at the black spot in space from which you miraculously escaped. At first glance, it seems to have changed little, but now that you know what to look for, it is as if another veil has been lifted. Do you really see how particles escaping from it move away? And you get the feeling that the dark monster is evaporating? Perhaps this happens all the time, you understand, but you just haven't noticed. But how can this be? As Richard Feynman once said, only those who can provide many different reasons for something happening truly understand the phenomenon. While you and the robot observe the rain of particles in space, I will give you 4 reasons why particles flow through black holes, all of which are related to a process you have already encountered. The first is the simplest. As you know, quantum particles can borrow energy from their field, and they can do this even while being beyond the event horizon of a black hole. With this borrowed energy, they can move faster than the speed of light for a short time, long enough to make a quantum leap from the black hole's point of no return. This is what you did, being your mini-copy. This quantum process, every way to understand what happened to you, is fundamentally quantum in nature. So they all come with the usual health warning, because, like much of what you have seen in the quantum world, they may seem absurd. The second reason is no exception. One could say that all particles that have fallen through the event horizon of a black hole simultaneously did and did not do something. Among all possible paths, a particle viewed as a wave can choose to fall into the hole, and in most cases, it will miss, because there is much more space outside the black hole than inside it. Surprisingly, this carefully crafted idea causes the black hole to evaporate in exactly the same way as the first reason above. The third reason is as follows. Due to the separating horizon, the vacuum beyond the black hole differs from the vacuum outside. Thus, a certain form of vacuum force, the Casimir effect, causes the horizon to contract inward, resulting in the black hole shrinking and evaporating. This, again, somehow yields the same result as above. The fourth and final reason I will summarize here is that pairs of particles and antiparticles are born near all black hole horizons. These particles tend to collapse into a collision more often than particles, just as there are generally more particles than antiparticles around us. Once they cross the horizon, antiparticles eventually annihilate with the particles present, causing both to disappear. Only the particles remain outside, particles created alongside the antiparticle, the twin of the particle, has annihilated. Inside, again, this ultimately leads to the same result. You have observed all these quantum effects before, but here they apply in close proximity to the black hole, and they all lead to the same conclusion. Black holes evaporate. They flow. So, when you now look at the glow of the black hole, you realize that this cosmic black hole monster, which has consumed entire stars for billions of years, is no longer black, but gray and shrinking. Even more astonishing is the fact that the more particles it emits, the hotter it becomes, and the hotter it gets, the more particles are ejected from it. A vicious cycle, inexorably leading to its demise. The death of a black hole, no matter how incredible it may seem, is that the black hole you are observing is shrinking, emitting some radiation. The energy of space-time, stored within it as a result of consuming entire worlds, is now returning to cosmic space, particle by particle, at every moment, much like radioactive decay. The black holes around burst, giving particles a second chance. All the quantum fields of nature are excited by what is nothing other than the most powerful gravitational object known in the universe. Currently, it is being used to an unexpected golden bottom to fill itself with energy. As the black hole becomes hotter, its fundamental particles, which had been dormant, awaken and emerge. You see this happening, and the smaller the black hole becomes, the stronger the excitement of the fields, the more energetically particles are ejected from it. Gravitational energy is once again converted into matter and light. While the entire process unfolds before your eyes, you understand that it is completely contradictory to earthly laws. Hot water in a mug on planet Earth does not heat up by evaporating. It usually cools down. If it were otherwise, a forgotten cup of hot coffee on the table would lead to catastrophe. Evening news would be filled with stories like, "Another cup of coffee ignited the table, leading to the burning of the entire building." Always remember to dispose of your hot beverages by pouring them into the appropriate containers. Black holes are clearly different from cups of coffee. The more they evaporate, the more they contract, the hotter they become. No one knows what happens at the end of this process. Do black holes disappear with a final explosion, or do strange tiny remnants with special properties remain? To find out the answer, it is necessary to understand the laws governing the singularity hidden deep within. Scientists have been searching for them since 1975. That was the year when Stephen Hawking discovered on paper that black holes evaporate. At first, he did not believe his own calculations. Light seemed to be coming from a place where no light was supposed to be at all. So he repeated his calculations again and again, only to confirm that light particles, indeed, managed to find a way out of black holes. He published his discovery in journals and quickly became known worldwide beyond scientific circles. Quantum effects caused black holes to evaporate so that they would not remain inside, doomed to stay there forever. They emerge, albeit in an unusual way, possessing the ability to evaporate. Black holes behave as if they have a temperature, known today as Hawking temperature. Observing the remnants of energy escaping from a black hole, you realize that what you are looking at tells you that the micro-world and the mega-world can communicate. If they must, of course. Black hole radiation remains the only evidence that our theories may reflect nature in this regard. This is a specific hint that a theory of quantum gravity may indeed be possible. Any serious opponent of such a theory will have to calculate the Hawking temperature of black hole emissions all the way to the death of the black hole. Black holes can die, speaking in a loud sleep. Unable to believe, like everything else in this universe, the robot interjects. But around the end of the 70s, Hawking's discovery also led to a rather strange and quite nerve-wracking statement. With his formula for temperature in hand, Hawking attempted to extract information about what primarily constitutes a black hole from the radiation he found. To simplify the process, he started with a fully formed black hole and threw various objects into it to see how each transformed the subsequent radiation. Surprisingly, there was no difference. Nothing that you throw in revealed anything to him, except for their mass. From what he could tell, it seemed that black holes completely rid themselves of the characteristics of what they absorbed, except for their mass. Regardless of whether people, stacks of books, asteroids, or diamonds fell through the event horizon, if they had the same initial mass, they subsequently evaporated in exactly the same way. So, for black holes according to Hawking, people, books, and stones were identical in taste. For all of us, this means that for black holes, only our mass matters, which may offend the dignity of some scientists. However, this became a philosophical catastrophe. Before Hawking's work, it was assumed that black holes absorbed everything that crossed their horizon and grew. And this posed no problem. Everything that fell inside was not lost. It was simply stored beyond the horizon, and it was difficult, indeed impossible, but who knows, to retrieve it back. With the shocking information about black hole evaporation, we face its troubling realization. In reality, things begin to disappear from reality. The independence of Hawking radiation from what exactly falls into the hole means that these dark monsters become voids of memory in our universe. Both black holes and sparely stored remnants of the past are not only difficult, but impossible to access. They simply cannot be found anywhere else. They have disappeared forever. Science and the rock of theories of everything, the theory of explaining everything in one formula, and the very first result achieved from such an attempt dealt a blow to science as a whole. Science has eternally lost the chance to explain the lost past that ended up in black holes, forced to give up hope of one day describing and understanding the entire history of the universe. Hawking radiation became a bell, heralding the end of quantum physics or general relativity, but the end of physics as a means of understanding where the universe came from. This problem has been duplicated by the black hole information paradox. Today, physicists are more familiar with the rough approximations Hawking used to achieve his results. But even 40 years after his discovery, when Hawking asked me to work on this problem with him, it remained shrouded in mystery. But now, there are hints that a way out may be found if one applies what is known about the quantum world to black holes themselves. And then it turns out that black holes could exist, or they might not exist. Where such reflections have led scientists, you will discover in the next concluding part of the book. However, for now, being an unknown number of billions of years in the future, you suddenly remember the robot's suspicious happiness about your return from the black hole. Didn't it surprise you then, why he was so pleased that you recognized him? Did you think it was sincere? Was it? But probably not. And now you know the reason. The robot was not sure if you remembered anything at all. He did not know whether the black hole would cleanse your body and mind of all the information contained within. When you learned, and you wanted to tear him apart for pushing you, he realized. He realized that you remembered everything, that the information in your case had not been lost. Even if you have no recollection of how you managed to return through the event horizon of the black hole, you remember that you became a collection of fundamental particles, and then that you found yourself outside. in between, a quantum leap or something else occurred. Figuring out how exactly this could happen is precisely what a decent theory of quantum gravity aims to achieve. And since that is what you will be exploring soon, let me emphasize the fact that at the beginning of this part of the book, you entered a purely theoretical world. Dark matter has never been created in a laboratory, just as dark energy has not. The same is true for black holes. Their evaporation has yet to be detected by any experiment, directly or indirectly. Otherwise, Hawking would have received a Nobel Prize. The evaporation of a black hole is a rather difficult example, more difficult than one might think. Let's consider the Sun. To turn it into a black hole, you would need to compress it into a sphere 6 kilometers wide. This is equivalent to about 2/3 of the diameter of London. Most black holes in the universe are born from the death of giant stars, so they must be larger than the Sun. It is not a giant star. Now let's assume that one of these black holes of solar mass swallowed everything nearby. Now it quietly exists somewhere far from everything. Its radiation temperature, the Hawking temperature, should be about 1/10 of a millionth of a degree above absolute zero. And absolute zero is around minus 273.15 degrees Celsius. 1/10 of a millionth of a degree is not much. It is difficult to measure. And separately, this is not the main problem. The main problem is that the Hawking temperature is much lower than the cosmic microwave background radiation, which has a temperature of 2.73 degrees Celsius. It is all in the same universe. As a result, solar mass black holes are not currently considered to be evaporating. In fact, to this day, no one has ever seen them in this state. They are and have always been masked by the residual relic radiation from the Big Bang era. And since the heavier the black hole, the lower its temperature, the worst off are the large supermassive monsters that sit at the center of most galaxies in the universe. Their Hawking temperature is even colder than that of solar mass black holes, not to mention that they are surrounded by extremely hot rings of infalling matter. Therefore, what could bring Hawking a Nobel Prize may lie in the microworld, as tiny black holes should be very hot. Unfortunately, there are still problems. Scientists confidently say they have detected giant black holes, yet they have never seen a single tiny one. Although this is irrelevant, let's assume they exist. Can we practically extract anything from them? To figure this out, let me take a small detour from the topic that will shed some light on what I previously called the Planck wall. In the early 20th century, one of the most impressive scientists of all time founded what we today call quantum physics. He was German, like Einstein, and his name was Max Planck. He received the Nobel Prize in Physics in 1918 for his own discoveries. Planck understood that there exists a scale beyond which quantum effects cannot be ignored. Take a large object, and everything will be fine. Newtonian understanding of nature can be applied to it, and regardless of what is expected from it, it corresponds to the reality we are accustomed to in our daily lives. But compress this object to microscopic sizes, and Newton's laws begin to break down. Newton, let me reiterate, discovered a way to describe the world at a scale familiar to people. This aligns with our common sense. For the megaworld, Einstein's vision prevails. For the microworld, it is Planck's. There, we must consider the quantum world. And there are natural constants that allow us to understand where it begins. It is called Planck's constant. Planck's constant is on par with two other universal natural constants, namely the speed of light and the gravitational constant, which tells us how two masses attract each other. One day, Planck decided to play with these constants, creating three things from them. The first was Planck mass, equal to 21 micrograms, 21 millionths of a gram. Planck length was approximately 10 to the power of minus 30 meters. This is Planck length. Planck time turned out to be about 10 to the power of minus 42 seconds. It is called Planck time. What does not correspond? It does not correspond to the scales beyond which neither gravity nor quantum physics can be used independently of each other. They are thresholds beyond which quantum gravity is required to explain what is happening. Although a number of quantum gravity effects may appear before these scales are reached. What does this mean in practice? What does it mean? Planck scales indicate the size of the smallest possible black hole. So the smallest black hole that modern science can imagine weighs about 21 micrograms. Strangely enough, our minds can accept this weight, but it is not impressive. Although it is enormous when squeezed into the tiniest volume of space-time, a sphere the size of Planck length, such a black hole would evaporate in 10 seconds, Planck time. Let's assume we could measure such tiny, rapidly occurring things. Then we would need to create a black hole of Planck mass for study. But with our current technology, a sufficiently powerful particle accelerator to create such a black hole from colliding high-speed particles would need to be the size of our galaxy. Naturally, this is far beyond our capabilities, and I doubt anyone is ready to start building such a device, except for Hawking, for obvious reasons. Although solace may come from outer space, where such tiny black holes may be discovered, expelling their last energy, and only if some yet unknown phenomenon wishes to inform us where and what to search for, could someone be extremely lucky to discover it immediately. Although no one doubts that Hawking radiation exists, which means that somewhere in the micro-world a new reality is lurking, a quantum reality containing space-time of its own. And it is because of this, as you will now see, that in the minds of some of the brightest living scientists today, the most unusual picture of our universe has emerged. This seems impossible, considering the age of the universe and the speed of its expansion. They are too far apart to ever touch in any way, unless some very strange phenomenon occurred, like something that could move faster than light. Unfortunately, for a signal, that is, anything that can carry some information regardless of its form, from one place to another, this is impossible. We are not talking about quantum processes here, so signals, however they may be, cannot propagate faster than light. This is indeed prohibited. Nevertheless, the temperature of the cosmic microwave background radiation, as it stands, is too uniform everywhere to be a coincidence. How can this be? It may turn out that space-time, the universe itself, in other words, grew faster than light at some point in the past. And that is what you witnessed. Time travel, back beyond the Big Bang, when you entered the so-called inflationary epoch, when the universe was filled with an inflationary field in its modern form. The inflationary model of the early universe was first proposed in the 80s of the last century by American theoretical physicist Alan Guth, Russian astrophysicist Alexei Starobinsky, and American theoretical physicist Andrei Linde. The standard model is that long ago, before the emergence of matter, light, and everything we know, beyond the visible universe, beyond the Big Bang, there existed a field filling the universe, repelling with an anti-gravitational force. This field was so extraordinarily powerful that it caused a period of accelerated expansion, which spread various parts of the early universe apart at speeds far exceeding the speed of light, allowing places that today seem too far apart to actually have contacted in the past. This is why the inflationary field emerged. But is it real? Can we, as with all other quantum fields, detect some of its fundamental particles? If the field is real, then most of its particles must have long since disappeared, causing the hot Big Bang, but it could not have completely erased itself. In any case, the inflationary field must still exist around, filling the entire universe, preserved in one of its forms with the least energy, in a vacuum, which, precisely due to a lack of sufficient energy, is unlikely to ever be excited enough to produce and show us its particles. The inflationary field and its so-called particles are unobservable. Nevertheless, many scientists are convinced that some scenario of the inflationary model with its inflationary field must closely resemble what actually happened. Personally, I find this idea very appealing. So let's take it seriously and see what the history of the universe containing such a field would have to be. Inflation did a very good job of separating different parts of our visible universe so quickly that they have never interacted since, and likely never will again. Then came the Big Bang, with all its fields, particles, and carriers of interactions arising from the colossal amount of energy released once under the influence of the inflationary field, which subsequently became calm. Then normal expansion of the universe began, not super-fast inflation, and the inflationary field did not disappear completely, but too significant a portion of its energy was used to launch the Big Bang, and it thereafter had no effect on anything until 8 billion years later. 8 billion years after the Big Bang, after 8 billion years of steady growth of our universe, the matter that spawned the inflationary field had enough to wake its vacuum up again with dramatic consequences. Its anti-gravitational force caused the accelerated expansion of the universe. The experimental discovery of this acceleration in 1998 was what led Perlmutter, Schmidt, and Rees to be awarded the Nobel Prize in Physics in 2011. Of course, the way the inflationary field influences the behavior of the universe today is nothing compared to how it spread everything apart before the Big Bang during the inflationary epoch. Nevertheless, it may account for what future awaits our reality, antipodes, and parts of the universe as seen from Earth, now too far apart to ever be in contact. But that happened before the Big Bang. Therefore, these distant parts of the night sky have every reason to behave similarly. Is the emergence of a new inflationary field merely a way out of a puzzle, a clever trick to explain why diametrically opposite points in the night sky have the same temperature? Or did inflation actually exist, and is it possible to verify this? Surprisingly, it is possible. Chapter 2. A multitude of Big Bangs. Some time ago, you conducted an experiment with Schrödinger's cat. The goal was to find a method to express the strange microscopic quantum behavior in macroscopically observable reality. We know well that inflation also illustrates this, and there is no need for a cat here. According to the chronological scale, as you have just seen, the inflationary epoch occurred before the Big Bang, and the inflationary field transformed from what was an extremely tiny universe, nothing macroscopic beyond unimaginably small, and time. Then the inflationary field and its fundamental particles decayed into pure energy according to the equation E-ars mc2, releasing an enormous amount of energy, and the universe became incredibly hot. This is how, as it is now understood, the hot Big Bang began. In such a scenario, the excited fields later became what we and everything else existing today are made of. During the inflationary epoch, the rate of expansion of the universe was so extraordinary that all quantum fluctuations, oscillations that could happen, and thus did happen, froze one after another. Even more unusually, these frozen fluctuations can be seen today in the sufficiently precise image obtained by scientists from the relic radiation. Inflation predicted the incredible smoothness filling the universe, relic radiation. But this is one of the reasons why inflation was created in the first place. That is, in reality, it is not a prediction, but it also states that there must be quantum fluctuations captured on this background radiation in the form of tiny directional temperature variations. Such variations are called anisotropies. This was unknown. Nevertheless, such fluctuations were discovered by American astrophysicists George Smoot and John Mather, who shared the Nobel Prize in Physics in 2006 for the experimental discovery of the extraordinary homogeneity of relic radiation and the anisotropies contained within it. This anisotropy is on the order of 1,000th of a degree Celsius. It is important. It is even believed that it later caused the formation of stars and galaxies. Without it, the universe would be homogeneous, and stars would never be able to form. Thanks to these fluctuations, tiny differences emerged between different places in our young universe, and then gravity made those differences even more pronounced, amplifying them, creating stars and all other structures in the cosmos. Thus, inflation again mixes the micro world with the macro world, traversing the entire path from quantum fluctuations at the earliest stages of the universe's development to the birth of structures we see today within it. It even hints at what mysterious dark energy may be, as this anti-gravitational force could stem from the residual energy of the vacuum of the inflationary field. Inflation potentially explains much that is inexplicable in cosmic space, so it should be taken very seriously. And since we have touched on this topic, I will mention the rather puzzling consequences of such a scenario. Here they are. As is understood today, the inflationary field cannot actually remain calm, and it cannot be a one-time field that appeared only once at the birth of the universe. In fact, it is presumed to have caused not one Big Bang, but an infinite multitude. Like all quantum fields, the inflationary field must undergo quantum fluctuations, allowing it to jump from one vacuum state to another on a local scale. Usually, for the fields you have seen so far, this process leads to the creation of particles that can jump from somewhere to somewhere or appear from nowhere. Here, however, it means that the field can create a small universe from itself, or two, or many. And when I say everywhere, I mean just that. Although the time intervals may or may not be enormous, this process is called eternal inflation. It never stops. Bubble universes appear within already existing universes, where the quantum vacuum of the inflationary field has jumped to another state. They are like drops of oil falling on the surface of a lake. They grow and grow and grow. And within these drops, other drops grow. Bubble universes, within bubble universes, within bubble universes. An example of a multiverse, but a different type of multiverse than the one you have seen. In such a scenario, you and I would be living in one of these bubble universes, and there may well be bubbles ready to appear within our space-time at some point in the distant future. Just as our universe may have popped out of yet another bubble that is currently much larger and perhaps a bit damaged or fading. Therefore, the potential demise of our visible universe in the future may be a form necessary for the growth of new bubble universes. We will take another look at these amusing, unexpectedly appearing universes when you travel through the landscape of string theory at the end of the book. In the meantime, eternal inflation may not and should not seem completely crazy to us, as it does to me, but I like it. And yet, compared to string theory, which you are about to encounter, nothing will ever seem more normal to you. Indeed, you should even consider the bubble universes you just met as a prelude to what will become the goal of your final journey. But before getting there, before returning to the visible universe, to see where these famous strings might be hiding, what they are, and what they mean for our reality, let's try to see if we can look beyond the inflationary epoch using the knowledge we have gained. For those who may ask how the universe came into being, the scenario of personal inflation might seem somewhat unsatisfactory, as it truly lacks any beginning. It is always bubbles, but there may be other possibilities as well. I cannot list them all here. I will mention just one, historically the very first. Chapter 3. The Universe Without Borders. Inflation existed before the Big Bang. According to eternal inflation, an infinite number of universes have always been, are, and will be born, and our universe just happened to become ours. Now let us simply imagine one universe with one beginning, whatever that may mean, emerging from one inflationary epoch, and let us rewind time back to the Big Bang. Here is the Big Bang. Boom. And before that, there was inflation. Let's take a look at it during that period. It is a dramatic collapse. And before it, now we have a problem. The Planck wall. The Planck epoch, where and when space and time cease to make sense. The Planck wall is located about 380,000 years before the surface of last scattering, the surface at the end of the universe. We are allowed to make such a supposition somewhere through Planck time, after what we might call the zero moment of time, but we will not allow ourselves to do so. We cannot reach the zero moment of time within our universe. We cannot speak of time where or when it did not exist. Talking about time before or prior to the Planck epoch makes no sense. For that, quantum gravity is truly necessary, with an unknown volume of new concepts to replace space and time with quantum something. It is a difficult task, akin to searching for the initial conditions for the existence of our reality. Difficult, but not impossible. Stephen Hawking and American theoretical physicist James Hartle tackled this very problem about 30 years ago. They were the first scientists to engage with it. Now let's discuss what they achieved. Imagine your mini-copy in a newborn universe, a universe where space and time have just begun to make sense. It is tiny, a little larger than a bank coin, but still small. You are inside it, you are tiny too, and you cannot see much. Everything happening on scales smaller than the Planck length is beyond space and time, and thus hidden from your view. In this minuscule size of an extraordinarily young universe, you are practically blind. But wait, doesn't this remind you of situations you have encountered before when visiting the quantum world? Didn't you also switch to the yogic method, closing your eyes to avoid interacting with anything and gain access to what is hidden from view when studying the inner parts of atoms? To guess what is happening around you, you had to somehow become a yogi. And to understand what was discovered in this way, you learned that in the quantum world, when nature and cats are left uncontrolled, all quantum possibilities occur simultaneously. And that is even worse. This opinion about visible particles is the past of our entire universe, hidden behind the wall that marks the very birth of the space-time we know. This wall is the Planck wall. Now it is everywhere around you. What lies beyond it is inaccessible to your senses. Therefore, according to quantum law, the Planck wall conceals the superposition of all quantum possibilities. Possibilities of what, you may ask? Well, possibilities of the past. There, the young universe is entirely hidden from view by the Planck wall. And such a young universe must adhere to one of the golden rules of the quantum world. As long as no one is watching, all possibilities can occur. And they do. Hawking applied this idea to the newborn universe, but he could not use the time we know and use every day. No one is allowed to use it beyond the Planck measurement system, so Hawking transformed it into something else, more manageable, the so-called imaginary time. With its help, he then considered all possible histories of the universe's past, all past histories that no one can see from the inside. The idea came to him in the 1980s. He had just discovered ways to deal with the quantum aspects of black holes. He learned that they emit particles. He realized that quantum gravity must exist. Then Hawking's mind ventured beyond the Big Bang. Together with his colleague, American theoretical physicist James Hartley from the University of California, Santa Barbara, he wrote a formula that forever changed the universe as perceived by the human mind. Hawking and Hartley proposed that all the universes leading to our current universe must emerge from nothing, truly from nothing. Mathematical nothing, some finite time ago. They accounted for all universes that possess this property, and they considered many of them. The scientists introduced the golden rule of the quantum world. Instead of selecting one for further development into our reality, they accounted for all. On paper, this means they added everything with a plus sign and stated that their sum is what the universe was like in the times before the Planck wall, where no one could look at it. Their mathematical formula is known today as the Hawking-Hartle wave function of the universe, and the initial conditions state that all possible universes under consideration emerged from nothing. This is called the no-boundary proposal. Our universe, from their perspective, with all possible states as a young universe, had no beginning, and then it became ours after some finite time, when space and time gained meaning. What exactly this means is truly irrelevant here. The madness is that they did it. They recorded the mathematical initial conditions for the entire universe. They mathematically solved the problem of creating our universe from nothing. Now, a few words of caution. This is not the end of the story. Tracing virtually any calculations devised within the mathematical framework of Hawking-Hartle is, unfortunately, terribly difficult, if not impossible. Nevertheless, simply by recording them, they became the first people to provide a mathematical formula for the emergence and subsequent evolution of our reality, an unbearable milestone for humanity. Humanity has been trying to decipher the laws of nature for thousands of years. Our understanding of these laws has changed and improved over time. 100 years ago, Einstein unveiled a new concept of gravity, and we all began to understand that the past could be discovered not only beneath our feet through archaeological digs, but also among the stars. Around the same time, many scientists began to uncover strange quantum laws governing the microworld. Then, about 30 years ago, inspired by the results of black hole evaporation, Hartley and Hawking boldly began to connect everything together and develop a mathematical formula for the origin of everything. Of course, their vision may turn out to be deeply flawed in the future, and the same can be said for all ideas that take us beyond experiments. But that does not matter. What matters is that the question of the origin of our universe has entered a new era, where mathematical physics, at least, has allowed us to obtain information about the subject. Although Hawking's idea of considering all possible universes using another imaginary time did not come from nowhere, it is present in the works of some of the brightest minds of the 20th century, namely Paul Dirac and Richard Feynman, who devised such a concept for creating modern quantum field theories. In such a scenario, the visible universe is still a sphere with a radius of about 13,800,000,000 light-years. This is the largest size we can explore. Nevertheless, it is amusing to think, I repeat, that by collecting radiation signals coming to us from space and moving further and further into the megaworld, humanity ends up peering not only into the past, but also into the microworld. Our ancestors did not know this, and as you can now see, the opposite may very well be true. And you are about to visit the microworld again, but this time you will go further than before. Down there, you will find a window opening into an entirely new reality, a reality larger than everything you have dreamed of so far, even more than bubbles within bubbles within bubbles of eternal inflation. In the grand scale, you found little in the small, and now find the immense. But where should you look? Chapter 4. The unexplored part of reality. As you now know, our entire visible universe is a sphere with a radius of about 13,800,000,000 light-years. With such a gigantic perspective, you first see the threads of gigantic clusters of galaxies bathing in gas and dark matter. More importantly, all quantum fields are present there. They cannot be seen from such a great height, but they can be felt. They are the matter that makes up the visible universe. They are the Higgs field, giving mass to everything that has mass. They are the inflationary field, or dark energy, counteracting the effects of gravity and preventing the universe from expanding ever more rapidly. And gravity itself is also present, pulling everything closer to everything else. You observe everything from the outside and begin to zoom in. Now you see galaxies, hundreds of billions of stars, their supermassive central black holes emitting jets of high-energy light and matter. You see the presence of dark matter, witnessing how it prevents galaxies from tearing apart due to their own rotation. Keep zooming in. You are at the scale of stars, enormous balls of hot plasma emitting light that we, humans, use to explore the distant universe. Next are planets, spherical worlds too small to ever become stars. Even smaller are asteroids and comets. Living beings are hidden beneath kilometers of atmosphere on our planet, followed by microbes, cells, molecules. And there are electrons and photons, protons and neutrons, quarks and gluons. Keep zooming in. You have returned to the territory of quantum fields of gravity. Already here, armed with all quantum forces, you continue to zoom in and then stop. Do you remember what went wrong with quantum fields? Do you recall renormalization, the trick that theorists exploring quantum physics use to eliminate the troublesome infinities? And do you remember that attempts to view gravity as a quantum field have completely failed because the infinities that arise in this case cannot be removed by any means, creating a collapse of space-time throughout the universe? It is from these infinities that we now must rid ourselves. Beyond them, you will see a window leading into the grand new reality I mentioned at the end of the previous chapter. Very soon, you will pass through it. But first, it is necessary to eliminate these pesky infinities. How are we going to do that? Well, let's see what we know about space and time. We know that its description through physics at the beginning of the 21st century has its limits in the mega-world, from the limitation of some place with the Big Bang past the inflationary epoch, when the universe was experiencing the Planck epoch. This limit is located 13,800,000,000 light-years from Earth. In the space-time micro-world, the same limits exist, and this happens everywhere. Get close to something, and at some point, you must reach the Planck scale unless something prevents you from doing so. Thanks to Hawking's work on black holes, we know that gravity is not insulated from quantum effects, that quantum gravity exists in some form, although we do not always understand what it may mean for reality. Within its territory, there are boundaries to what we can explore, both in the mega and micro worlds, and it is defined by the Planck scale. Have any experiments reached the limits of size, energy, or time in laboratory conditions? No. None of these limits possess too small an energy size at the speed we have today. This is a theoretical limit, and worse still, there is a practical limit that no one can actually reach. Why? Because a tiny black hole of Planck scale will emerge in the process, which I already mentioned at the end of the last section. To explore the reality beyond this black hole, there will be no choice but to try to send more and more energy into it, more light, with ever shorter wavelengths. Hopefully, it will bounce off something and reveal its existence before our eyes. But that is not the case. Light will be absorbed by the black hole, only increasing its size further, concealing the scale of quantum gravity. In other words, modern science considers that what lies beyond the Planck scale cannot be explored. So what to do? What can we do? Let's try to be clever, for example, by suggesting that nothing prevents quantum gravity or some new physics from going beyond the Planck scale. Using the best modern particle accelerator and observations of the sky, theoretical physicists are confident that they understand how nature behaves almost all the way from enormous galactic scales down to the scale where all quantum fields merge into one scale of the grand unification theory. The energy required for it is about 1% of the Planck energy. Clearly, this is an enormous volume. It corresponds to a temperature of about 100 billion degrees. But that is not the Planck limit. So, you probably remember that energy is related to size. The higher the energy of the wave, the shorter the distance between two successive peaks. The fact that 1/100th of the Planck energy, 1%, corresponds to the scale of the micro-world and is 100 times larger than the Planck length. This means that there is untouched territory of reality extending at least within the bounds from 1 to 100 Planck lengths. Experiments have revealed nothing about what happens there. A good way to imagine what it is like for a theoretical physicist to obtain such an experimental gap is to think about what the world would look like if your eyes could only see it with a resolution of 1 meter. Typically, you see the world with such a high resolution that you can distinguish objects much thinner than a human hair. But imagine that you would be unable to detect anything smaller than a meter in height or width. Exploring the environment, you would not see any detail anywhere. You wouldn't even be able to see small children. Children would suddenly appear before you, reaching a meter in height. I am not saying that these could be children 100 times smaller than the Planck length, but we do not know what nature may be hiding there. Our reality is rooted somewhere in the micro world, in what it is made of. And since no experiment has ever accurately explored these scales, it is possible that space and time begin to differ from what we use somewhere up to the Planck scale. It is also possible that because of this, the nature of gravity, matter, and light also begins to change there, and radically so. For example, it is possible that they all become one. Until now, you have mostly seen the known problems arising from what is known. Now, you are about to venture far beyond knowledge, and we will assume that all of this is real so that you can travel there. But keep in mind that this is pure theory. Nevertheless, some of the brightest scientists of our time have worked for decades to convey this picture to you. Chapter 5. String Theory. A strange haze of blue electricity surrounds the silhouette of your robotic companion, as if inner excitement has burst forth from its electrons. You both float in space surrounded by distant galaxies, far from the point where you escaped complete disappearance into a black hole. You have seen everything that needed to be seen, having fallen out of Tallinn in a super-fast plane. You observed vacuum fluctuations of quantum fields and became acquainted with matter and light. You witnessed stars exploding to create new worlds, saw white dwarfs and black holes, which you, in turn, observed hovering, hinting at the existence of an unknown theory of quantum gravity. It is time to continue the exploration further, says the robot, and immediately you both begin to shrink in size. You see particles flying by, light rushing past, vacuum fluctuations of all known fields, and you continue to shrink. You are at the scale of grand unification, where all three quantum fields are believed to behave as a single entity. You keep shrinking. You are already far beyond the size of your mini-copy. You must squeeze down in relation to your surroundings by billions and billions of times until you ultimately reach the width of a human hair. At first, you see nothing, but then something appears before you, a string. This string is made of nothing, not even of space-time. As you look at it, you get the sense that this vibrating object replaces both of these concepts. You have not yet reached the Planck scale and will not be able to understand, in the theoretical sense in which you are now situated, whether the Planck scale exists. Although you may have thought otherwise, this does not mean that what you have seen so far was incorrect. It means that down here, none of the concepts you have used can be trusted, except for quantum theory. But are they applicable to strings? They are applicable to particles. What is vibrating right before you now may be one of the most fundamental elements. It is a quantum string. It has a chance to explain what you have seen before, including gravity and the existence of our entire universe. The quantum string before you vibrates in a quantum way. You cannot precisely determine its edges, but you can say that they do not exist. Although everything in this string moves very, very quickly, it vibrates beautifully with joyful energy, and you feel its pull, unable to stop. You reach out your hand, and although the string vibrates on its own, you pull it, like a guitar string. Although the string consists of nothing, you see a wave of vibration spreading, similar to musical harmony. The largest standing wave on a real guitar gives the fundamental tone, with the other higher harmonics. As you examine the strings, you see that they are blurred, but without the string itself. The string of nothing, a fundamental string, if you will, is capable of vibrating. Remember that when the word quantum precedes familiarity with everyday speech, it signifies that the concept has nothing to do with it. So here, a quantum string is not a string at all. Its vibrations give rise not to notes, but to particles of light, carriers of electromagnetic interaction. All quantum particles you have encountered before, all particles that make up your body and all the matter of the universe, may be vibrations of such open strings. Something on the right catches your attention. You turn your tiny head to see a second string. It does not resemble a guitar string, but looks more like a closed loop, and also vibrates in a quantum way. Again, its first excitation does not account for light, but for the graviton, the carrier of gravitational interaction. This is about quantum gravity. This loop, the closed string, by its very existence tells you that you are traveling through the quantum theory of gravity. Place such a closed string anywhere you can imagine, and its vibrations will produce the same effect as gravity. You will not see any persisting infinities. The infinities that hindered quantum gravity have vanished for good because you have rid yourself of the views that things happen in space-time. With point-like particles in smooth space-time, it is easy to imagine a specific place where they could not collide. And quantum field theory, despite its inherent oddities, also states that when particles interact with each other, it occurs at a specific position in space-time. With strings, this is no longer the case. The structure of particles is their vibrations. The vibrations of strings are particles. Throughout their length and time, they produce impulses when they interact with each other. This does not happen at a specific location, nor at any precisely indicated moment in time. Interaction occurs across the entire string. No longer does the infinitely small exist, and this is precisely what removes all the infinities you encountered earlier. This loop, the closed string, carries gravity. The fact that it is gravity, and you have light emanating from open strings. Therefore, taken together, they become a theory that unifies gravity and electromagnetism. Thus, quantum strings are more than just a quantum theory of gravity. The quantum theory of gravity simply deals with gravity in a quantum way. It does not concern itself with other quantum fields. This is what works here. What about other fields? Can these strings be the theory of everything, a theory that unifies gravity and all the quantum fields we know? For that, matter must also be taken into account. And where is it? You do not see its presence. So what makes these strings so special? What is strange about their existence? Why are they so exciting to theorists? You have every right to ask. Although with these two strings, you have seen the open and the closed. You can already say a lot. Much remains unknown. Let's go further, the robot announces, and you both begin to shrink even more. Now the open string is enormous compared to you. As you closely examine it, you begin to see more than at first glance. What you are about to undertake can never be done by any being made of matter. But right now, you can. Although remember, when venturing beyond the known, something always has to be sacrificed, and you will have to leave behind the special position of your universe that you may have considered unique. And not only on the path from Newton to Einstein did you have to give up the idea that the universe is static, that it has always been the same, that gravity is a force. You needed to become familiar with space-time, with its 3 dimensions of space and 1 of time, all 4 intertwined into a whole enveloping matter and energy, to transition from it to a sign. You, physicists, had to abandon the notion of particles as points. You had to learn about waves, fields, uncertainty, and other things. Now, to transition from gravity to quantum field theories, you must struggle to transform everything fundamental into the theories of closed and open strings. But that would be easy. What you need to relinquish is the idea that reality consists of only 4 dimensions. Strings cannot exist in 4-dimensional space-time. They require more room. They live in a 10-dimensional universe. As you approach the string with the robot, you begin to notice that above all points, which you thought were contained in our universe, 6 new dimensions of space emerge, forming their own world. Presumably, it is from these tiny additional dimensions that all the matter that constitutes us originates. If you find it very difficult to imagine 4 dimensions, let alone 10, do not worry. All you need to know is that 6 of them are additional extensions in different directions from the ordinary. Left, right, up, down, forward, backward, in our 3-dimensional world, and they are too tiny for you to feel their existence or travel through them in real life. Robots, you have now shrunk to such sizes that you can imagine what they look like, but it is impossible to describe. There are so many of them, so many possible ways to add an additional dimension, to obtain a string, so many ways to wrap these additional dimensions around themselves, giving with each new wrap a different basis for reality. Theoretical physicists have even guessed how many possibilities there might be, and the number has reached roughly 1 followed by 500 zeros. All of them are potentially capable of leading to the emergence of a universe, although not necessarily our universe. An enormous number of possibilities, 1 accompanied by 500 zeros. The universe where you were born may just be one of them, or many could have been ours. No one knows yet. It is quite possible that all these possibilities exist at some stage within the bubbles created by eternal inflation, which you have just heard about. But only a few of them can create a universe where the laws of nature are compatible with the known form of life. For humanity to exist in the form of a human, a specific set of forms of additional dimensions must have been selected. Otherwise, the laws of nature would not have allowed it. How such selection occurred, no one knows, except that they had to be chosen for you to exist here in our universe. Such an argument for selection is called the anthropic principle. It states that out of unimaginably many possible forms of additional dimensions, we must consider only those that are compatible with human existence. Otherwise, we would not be here to speak of them. It is an appealing idea, and it gets even better. Instead of all dimensions remaining tiny, 1 or more of these additional dimensions may be enormous. "Come with me," says the robot, gesturing for you to follow. "We may never see this again." And the most unusual things happen. Until now, you have always been taught that you cannot look at the universe from the outside, so talking about edges or boundaries is nonsense. If the universe is everything by definition, then it makes no sense to even try to imagine what it might look like from above or below. Yet, moving in a direction that is neither up nor down, neither left nor right, neither forward nor backward, the robot leads you out of the universe. And edges, it seems, now truly exist. but they lie beyond the dimensions that ordinary senses can perceive. You are outside. You see your entire universe from another dimension. You see that the open strings, these shoelaces and vibrations, lead to the emergence of light. Now they vibrate differently depending on the hidden dimensions in which they exist. And you also see that at the ends of all these open strings, they are attached to our universe, which you have just left, while the closed strings, those vibrating like gravity, can freely move out, exiting the universe. And you feel something behind you. You turn around and, in astonishment, find another universe, parallel to yours, that is, ours. And you see how the closed strings move from one universe to another, showing that they can communicate through gravity. This is the fourth type of parallel universes, the most impressive of all. Such objects are called brains. They sound similar to membranes, but without the mem to show that they are larger than a sheet and have more than two spatial dimensions. What lies before you is one such brain of another universe. There may be many of them, and they can also be of various sizes, and all of them can transform into one another, behaving like strings. When physicists and mathematicians studying them change the way they all interact with one another, they can be either separate objects or different aspects of the same reality, a reality viewed from different perspectives. All of this may also be one aspect of a broader reality, regardless of what reality may mean in this context. Some scientists, led by the brilliant Argentine theoretical physicist Juan Molina Sinai, have even shown that all of this could be understood without gravity, and each individual universe here could be imagined as occurring somewhere on its boundary. The truth reaches your consciousness. You are outside the universe. Everywhere and around you are other universes with various sets of dimensions. There are tiny spatial dimensions where strings wrap around themselves within these universes, causing them to vibrate into matter, light, which is forbidden from crossing beyond its brain, its universe, your universe. Their ends can move freely within the dimension in which you were born, but they are not allowed to leave. From where you are, seeing closed-loop strings transitioning from one brain to another, you realize that some amount of energy may be capable of leaving your universe. You even see what you believe to be black holes connecting neighboring brains. And through the curled and distorted space-time via gravity, each brain attracts other brains. You begin to wonder, what if other people live in these brains? Could black holes be a passage between your world and theirs? Could a singularity that you have not reached open access to another reality? Could the birth of our brain and our space-time be related to collisions with other brains that existed before? Could dark matter and dark energy be explained by the existence of brains? Looking back at the universe you just left, you suddenly notice that something has happened to the flow of time, and you see bubbles of new inflationary universes appearing everywhere in your universe, your brain, spreading within what was your world like droplets of oil on the surface of a lake. "We must go back," you shout. "All right," replies the robot. Nowhere else is he seen, and you slip inside the nearest brain, hoping it is the one you came from, and begin to grow. The other brains become invisible again, and the strings that could create your reality disappear into the distance. Now around you are quarks and gluons, now protons, then electrons, atoms, molecules, dust, sand, the sea. You open your eyes. You are on your deserted beach, in the same place where you began your journey. The stars shine, A gentle breeze carries the scent of exotic flowers to you. Friends are around, smiling. "He is awakened," says one of them. "Pour him a drink." A glass appears from the parent sand. You feel sick. You take a sip, looking at the sea, the trees, the stars. The outlines there, in the night sky, take on the features of the faces of Newton, Maxwell, Einstein, Planck, Schrödinger, Dirac, Feynman, Hawking, Weinberg, Mulder. The scene, the view, the tones, and many others. They all smile, all look at you. You want to talk to them, but instead, they turn away to gaze at the grandeur of cosmic space. And then they all dissolve into the stars. You alone, the stars disappear, and with them, the sea. In Margarita, you are home again, on the couch. The window is open. You sit up, look around. Your coffee is still there. You touch yourself again. It still hurts. You take a sip to awaken your mind. Coffee. Your living room has reached temperature equilibrium. You spit out the cold coffee. "I'm perfectly fine," you say aloud, but glance at your phone and call your cousin grandmother just to confirm it. And then you are back in Margarita. Epilogue. Throughout history, philosophers, and now theoretical physicists, have tried to envision a picture of the world to decipher its laws, the laws of nature, the existence of which is evident to all of us. The night language remained hidden for a very long time. They imagined themselves in impossible physical or experimental situations. Such experiments are called thought experiments, experiments of pure reason. Just such a sequence of thought experiments you experienced in this book. They allowed you to travel solely by thought through the known universe and beyond, one sphere. Hare used this method to show how strange quantum rules should emerge when not tied to macroscopic everyday events. He concluded with a cat that was neither alive nor dead, but dead and alive at the same time. Seemingly strange things, but it turned out they were correct. Einstein also gained much from his experiments. He envisioned what reality would look like if the speed of light had a fixed limit. To do this, he descended to the level of a photon, and looking at the world from there, a special theory of relativity was born in his mind, particularly stating that a plane flying at the same speed as yours would ultimately find itself 400 years into the future. It was later proven to be true. Intuition, although not based on common sense, has allowed humanity to survive until now, guiding discoveries over the past century. As Einstein famously said, imagination is more important than knowledge. The universe you introduced to yourself in the starry sky, right after waking up on the beach, was the faces of the giants of thought from the past and present. Of course, I cannot name them all. There are too many. But those whose legacy continues to make our world better are known. My pains are vast. With each minute, they created the history of humankind. Page by page, they wrote the book of what we currently know about our reality. Most of them are not known to the general public, but that does not make them any less significant. Remembering how your journey began, you may realize that you did not find a way to save Earth from the future explosion of the sun. You didn't even devise a method to protect the planet from all sorts of disasters that may occur before that moment. But you did discover tools that allow humankind to cope and survive. And our brain, our mind, our imagination, science will help us. You saw that there exists an infinite number of other planets, worlds in the cosmos that may one day come into contact with us. As for today's knowledge, it is impossible to move from one part of the universe to another within 1 or even 1,000 lifetimes. You can only do this in your mind, But just a few generations ago, one could spend months sailing from Europe to Australia. Now it only takes a few hours of flight. We do not know what will make the technologies of tomorrow possible. We do not know what will one day allow us to realize the general theory of relativity. Today, as I mentioned, it has given us GPS and only GPS. Tomorrow, it may allow us to find the shortest path in space-time, known as wormholes, which could connect two distant places without the need to traverse vast distances. So far, we, humans, have been able to send missions beyond the clouds to the moon. We have sent robots to the edges of the solar system. What lies beyond it, humanity has seen, but has not visited. And you have explored all known and unknown series of thought experiments. Through these flights of thought, we have gathered together the sum of knowledge of theoretical physics at the beginning of the 21st century. Some of what you learned during these journeys may turn out to be false. Dark matter, dark energy, parallel worlds, and realities. These are all ideas that scientists may ultimately abandon. Nevertheless, they are the most powerful ideas of our time. They correspond to how humanity is currently trying to make sense of our universe. In a few centuries, all of this may be discarded or accepted. We do not know, but living today means being surrounded by these extraordinary ideas. So, before allowing you to glimpse your own perspective, here is the final summary of what you have seen, plus a little extra. As you know, Einstein did not discover the general theory of nature, the so-called elusive theory of force, which I mentioned some time ago, and for which string theory may prove to be a competitor. Newton's theory did not even explain the strange orbit of Mercury, let alone the expansion of space-time. So in a sense, his theory is incorrect, yet it is brilliant. It could even be called perfect. We know where it works, and we know where and why it fails. We are allowed to use it in approximate scales that can be grasped by our human brain, somewhere between the mega and micro world, at not excessively high speeds, where the energies involved are not too intense. The world of evolution that we perceive, which has allowed us to discover it through our senses, is contained within the permissible limits of Newton's theory. There lies our common sense, but there are things beyond its limits. The world of superspeeds, the micro world, and the mega world, along with super energies. In these worlds, Newton's laws make no sense, and the senses do not help. Yet, remarkably, humanity has managed to decipher the laws of nature, applicable even where we cannot see them. Quantum field theory is used in the micro world, while general relativity takes on the mega world. In the interval between these two worlds, Newton is king. Where Newton's theories fail, strange new phenomena begin to emerge, hinting at new, mysterious realities bordering our own. Both theories, the quantum field and general relativity, have opened our eyes and minds to a universe far more extensive than any of our ancestors could ever have imagined. But still, these theories also have limitations. However, unlike Newton's theory, no one knows for sure what lies beyond their boundaries. In this book, you have journeyed through these extraordinarily successful theories, and in the last part, made a timid, tentative step beyond their limits. You entered a universe whose fundamental components are strings, tucked away in a universe made of numerous realities, possibilities, quantum vacuums, leading to strange laws in universes that are not our own. Einstein's extraordinary vision was to understand that gravity is not what Newton thought it was. Einstein showed that it has curves and slopes. gravity, matter, and energy are connected in a very simple way. Our universe has, however we call it, space-time, curved forms conditioned by its content, what is inside. The effect of these curves on nearby objects and light is what we perceive as gravity. This is what general relativity is about. It has been 100 years figuring out the local shape of the universe beyond a star and how gravity affects surrounding objects. It is simply necessary to know the energy contained within the star. Many scientists have made these calculations, starting with the German physicist Karl Schwarzschild in 1915, the very year Einstein published his theory. At a time when only a handful of people worldwide understood what was at stake, Schwarzschild figured out the exact geometry of space-time outside a star. He was 43 years old at the time. He achieved success during combat on the Eastern Front during World War I. He died a few months later from an illness contracted there. Wars have deprived humanity of too many people, including those like Schwarzschild, who could have helped us understand the world better and faster. Pursuing Schwarzschild's work made it possible to hypothesize how objects and light move around stars. He calculated the correct orbit of Mercury and showed that light itself must bend around the sun. In 1919, an expedition led by British astronomer Sir Arthur Eddington discovered such wounds, noticeable deviations. Photographs taken during a total solar eclipse that year showed that stars near the sun were not where they were supposed to be. Instead, they appeared exactly where Einstein's theory predicted they should be after their deflection due to the sun's influence on space-time. Light itself is suspended by gravity. Soon after Schwarzschild's death, the same mechanism was applied to larger objects, galaxies, and predicted that strange cosmic mirages, arcs, or orbs of light floating in the center of the distant universe exist. These were images of even more distant galaxies, whose light was distorted on its way to us. Galaxies, accordingly, acted as cosmic lenses, allowing us to see through them even further, deeper into the history of our universe. Such lens mirages were discovered more than 60 years after Einstein's work was published in 1979. Now they can be seen in almost every deep space image obtained with telescopes. Along the way, this shows that Einstein's geometric interpretation of gravity works not only in the immediate vicinity of the sun, but throughout cosmic space. General relativity has given us a new vision of the universe. You, I, everyone, and everything are surrounded by all that information reaching us now, at this moment, from the past. We are located at the center of our visible reality, and everything in this reality obeys the laws of Einstein, except for the inner contents of black holes. The same applies to our understanding of matter and light. The entire visible universe is governed by the same laws that apply in our cosmic surroundings. The matter we are made of, the light reflecting off our skin, all obey the same quantum laws as everywhere in the visible universe. The linking of the laws of distant galaxies and the laws of nearby galaxies led to the discovery that our universe has a history, that in its past it experienced a Big Bang, that past cosmic epochs can be read in the stars up to the point where light completely ceases to propagate. This moment is a place in the past of the universe when space became vast enough to allow light to move freely. We called this the surface of last scattering. When it disappeared, the universe had a temperature of 3,000 degrees. Before this moment, the entire universe was light-proof. After it, it became transparent. What remains today of the temperature it emitted is called cosmic microwave background, or relic radiation. It carries the imprints of what existed before. Beyond this, observations of the night sky can only lead to indirect conclusions about what once was. One day, we may be able to use light-independent sensors, working, say, on gravitational waves, and then we will have the ability to directly receive more distant signals. But we are not at that level of development yet. Until then,